A revolutionary floating bridge in Washington sinks to the bottom of a lake.
Nobody knew if it was going to survive.
A beachfront high-rise in Texas that has to be destroyed.
Mistakes were made. This building was not safe.
An engineering disaster in the Gulf of Mexico causes a global crisis.
Oil was spewing all over the deck. There were a series of massive explosions.
And a collapsing dam unleashes a toxic tragedy.
Se retiraron 7 millones de metros cúbicos de tierra contaminada.
With big builds, even the smallest mistake can be a huge disaster. From miscalculations to misunderstandings. Some with deadly consequences. These catastrophes are every engineer's worst nightmare. With big builds, engineers often push the envelope when testing new methods. But sometimes that can lead to disaster. Like this catastrophe in Washington state that destroyed a vital transportation link, cutting off hundreds of thousands of daily commuters.
Unfortunately, this was a disaster just waiting to happen.
An unexpected Thanksgiving storm that ruined the holidays for tens of thousands.
An old supervisor gave me a call, and he said, "Bridge is sinking."
And fundamental flaws that brought down a 2,000-meter bridge.
It was a race against time, and time won.
Seattle is one of the fastest growing and most innovative cities in the US. Founded in 1851, over the last century it has prospered around the banks of the majestic Lake Washington.
Seattle is the home of grunge, coffee, and some serious tech giants.
Hundreds of thousands of commuters cross the lake every day, and its bridges are their main thoroughfare. But building a bridge across this vast expanse of water isn't straightforward. As Seattle reporter Jim Foreman explains.
Seattle is a water city. Water is our lifeline, from the fishing to coming out for an evening cruise on one of the lakes. But the problem is you have to get across the lake in order to connect the communities. Big challenge for the designers of these bridges was just how deep this lake is. There was no way traditional engineering was going to work. So they had to come up with an ingenious plan: floating bridges.
This wasn't just an ingenious plan. It was the only plan, as structural engineer Patrick Clark explains.
Lake Washington is very deep. The solid bottom of the lake that was carved out by glaciers is 400 feet deep, and then it filled in with volcanic ash. So you have 200 feet of very soft material, which is not very good bridge foundation material.
Lake Washington is simply too deep and the lakebed too soft to build a conventional bridge. So, in 1940, after 18 months of construction, Lake Washington became home to the largest floating structure in the world, called the Lacey V. Morrow.
The bridge was named Lacey V. Morrow after a highly decorated World War II bomber pilot who went on to become the director of the Washington State Highway Department.
And he drew upon his military experience when it came to this new project. The 2-kilometer bridge is made up of 22 hollow concrete boxes called pontoons, each about 90 meters in length. The pontoons are bolted together and then tethered with heavy cables to giant concrete anchors that sit on the bottom of the lake and help stabilize the bridge.
Pontoon bridges have long been used by the military and played a vital role in the Second World War. If they can carry tanks, then in theory, they should be able to easily carry a Chevy or a Cadillac.
The mind really takes time to wrap around the fact that you're not driving on a bridge, you're basically driving on a boat floating in the middle of the lake.
At the time, it was a true engineering marvel. But when another floating bridge in Washington, built during the same era as the Lacey v. Morrow, failed spectacularly, concerns arose about the safety of the 1940s construction method.
In 1979, a very large storm sank the Hood Canal Bridge. And everybody started questioning our floating bridges and how viable the technology was.
Even so, the Lacey v. Morrow bridge design was so effective across Lake Washington that in 1989 a parallel bridge, the Homer M. Hadley, was opened alongside to increase capacity. Lessons were learned from the Hood Canal Bridge disaster that guided engineers when building the Hadley. But unfortunately for the Morrow, 50 years of heavy traffic had taken its toll.
Engineers analyzed the Lacey v. Morrow and decided it needed reinforcing. While they were at it, they planned to widen and resurface the road to meet new highway regulations.
The idea was to blast away the existing deck and then cut holes on the north side of the pontoons, which would be sealed with watertight hatches to allow for future access and maintenance of the pontoons. The bridge was closed and renovation work began on June the 23rd, 1989. In November 1990, on Thanksgiving weekend, the bridge was still under construction when a heavy storm began making its way towards Seattle.
In the middle of Thanksgiving week, it started to rain. And it rained, and it rained, and it rained. The rain just didn't stop. It was like a fire hose coming off the Pacific. Not only did the rain keep coming, we had the wind.
Strong wind and rain began battering the bridge. On Sunday, November the 25th, reports were coming in that the Lacey v. Morrow Bridge was in trouble. Structural engineer Patrick Clark was alerted as the disaster was unfolding.
I was at home. An old supervisor of mine gave me a call real early in the morning, and he said, "The Lacey v. Morrow Bridge is sinking, and I need you up there immediately."
Seattle reporter Jim Foreman rushed to the scene.
I jumped in my car and finally got here, made our way to the edge of the bridge. What I could see was these giant concrete pontoons bending and twisting. It was something I've never seen before.
The center pontoon began to sink, pulling some of the others down with it.
Hour after hour, more and more the bridge was falling apart and finally doing the death roll as they go down to the bottom.
By the end of the day, after half a century of safely carrying commuters, Lake Washington's original floating bridge, the Lacey v. Morrow, sank. But the danger wasn't over yet.
We were already seeing the one bridge go down, but the bridge right next to it, the new bridge carrying all the traffic, that was in danger too. 110,000 cars used the bridge every day.
The sinking left a massive part of the Lacey Bridge at the bottom of Lake Washington. That was bad enough, but as it went down, it seriously damaged the new bridge next to it, which was already carrying traffic for both roadways.
Because of the close proximity of the two bridges, the support cables holding the adjacent bridge in place were sustaining heavy damage from the sinking pontoons on the Lacey v. Morrow.
As the old pontoons were sinking, they were slicing the cables holding the new bridge in place. It was shut down to traffic, and nobody knew if it was going to survive. So engineers came up with a quick solution to save the new bridge. They brought in tugboats. Those tugboats were hooked up to the new bridge and were able to keep it steady against the howling winds.
With one floating bridge being held in place with tugboats and the other one at the bottom of the lake, Seattle had lost its lifeline across Lake Washington, and its residents wanted answers.
So they wanted to know why it went down, and they were demanding those answers fast.
With one of the largest floating structures in the world at the bottom of Lake Washington, an investigation discovered that it wasn't just the storm that had caused the titanic destruction of the Lacey v. Murrow Bridge. It turns out that the problems could be traced back to the ongoing renovation work designed to safeguard the bridge's future.
During the remodel, they were actually using something called hydroblasting. They were using water to break apart the old deck, and they were going to replace it with new concrete.
Hydro-demolition or hydroblasting uses high-pressure water jets to controllably demolish or clear concrete from a structure.
One problem with hydro-demolition is all that water has to go somewhere. But because the water was blasting concrete from beneath a grungy old road bridge, there were serious worries about contamination. So under environmental law, it wasn't allowed back into the lake.
Instead, engineers decided to store the water inside the bridge, adding considerable weight that had never been calculated for in the original plans.
The pontoons were designed with a safety margin, but pour in tons of heavy water, and it's clearly going to have an impact. Throw in a massive storm, and it's a recipe for disaster.
But it wasn't just the hydroblasting that had left the pontoons increasingly vulnerable in a heavy storm. It turns out there was another fundamental factor in the renovation work. The watertight hatches were never installed, as consultant Donald Dusenberry explains.
During construction, there was a time when these holes were cut, the frames were not yet in place. And in that instance, the contractor put sheets of plywood over the lower portions of the openings. So basically, we had openings that were about 10 inches above the water, covered with plywood to prevent wave splash and water from getting in.
As the storm raged on, the open holes that were intended to hold the watertight hatches were allowing water in instead of keeping it out.
No one knew that a massive Pacific storm was coming in. They hadn't planned for that, and so the water kept coming in. This was a real catastrophe.
In the end, the weight of the water from the hydroblasting and the heavy storm was more than the bridge could take. The upgrade was meant to save a 50-year-old bridge, but instead, it was an engineering blunder that caused its demise.
This is one of those disasters which seems obvious in hindsight, but at the time, the engineers believed that the pontoons had capacity to spare. But in the end, it just wasn't the case.
In September 1993, the new Lacey v. Murrow Bridge opened, replacing the original floating freeway. For 3 nights, crews drove 8 flatbed trucks loaded with concrete slabs across the new floating bridge to prove that this time it could hold its head above water.
Luckily, the bridge was closed for construction, or this disaster could have been a whole lot worse.
When tasked with building big, engineers must start from the ground up. Getting the foundations wrong will almost always mean a structure is doomed to fail. Like this miscalculation in Texas with a beachfront tower that just couldn't stand up.
Padre Island is just sand.
We had a structure with a failing foundation.
A condo building reduced to thousands of tons of rubble.
This tower broke records for all the wrong reasons.
In southern Texas, on the Gulf Coast just north of the Rio Grande, sits South Padre Island, boasting some of the longest beaches in the United States.
South Padre is what's known as a barrier island, a long, thin, sandy strip separated from the mainland by water. In this case, by the narrow, shallow Laguna Madre. It's basically a gigantic sand dune, stretching 130 miles, or about 200 kilometers, along the Texas coast.
These seemingly endless beaches have long been a draw for tourists. In 2006, to accommodate more visitors, construction began on a new 135-meter beachfront high-rise, aptly named Ocean Tower.
The plan was to build a 31-story tower with 134 luxury apartments with marble floors, jacuzzis, and amazing views over the Gulf of Mexico. It would be the pride of South Padre and the tallest tower for miles around.
Yet there's a reason tall towers are rare around here. South Padre sits right in the path of hurricanes. So engineers had their work cut out. Foundation engineer B.J. Ariel knows this part of the Gulf Coast well.
So in the Gulf Coast, we see that there are more of 10 to 15-story buildings rather than very tall, high towers. If we look at this resort here, that's probably about 15 stories high, and look at how spread out it is.
Historically, most development on the island was relatively low-lying. Building tall comes with massive technical challenges, and it costs a fortune. Throw in the threat of hurricanes, this sounds like an engineering nightmare.
The plan was that Ocean Tower would consist of two connected yet very different structures. A main 31-story tower, heavily reinforced with 3 concrete cores. Directly attached around the base would be a much lower, wider parking garage. The big challenge here for engineers, the foundations.
The Gulf Coast of Texas is mostly sand and gravel, dumped there over thousands of years by rivers. The ocean then molds the coast, constantly moving and shaping the relatively loose ground. It's a very dynamic landscape.
Geologist Tim Dukes knows what it takes to build on this coastline.
Anywhere in the Gulf Coast is similar to what we have here, with relatively young, soft, unconsolidated materials, and they're relatively wet. So they're easy to erode, and they don't have a lot of strength to support buildings. Foundation is essential to any building, and in a soft environment, one that is easily maneuverable by natural forces, it can be a problem. Padre Island is an island that is actively evolving. The shoreline is not stable just about anywhere in the world. And in an environment like that, where you have a barrier island, it's just sand with a little bit of lagoonal mud in some areas and no firm rocks to support buildings.
When it is spread out, the foundation is also spread out, and there is less likely of differential settlements. That's why in the Gulf Coast, we see more of this kind of buildings rather than high towers, which has more concentrated load, and the foundation is very small.
When you build anywhere, solid foundations are crucial. But on a shifting, sandy island surrounded by water, in the path of high winds, even hurricanes, you have to get it right.
Although this build would be tricky, the engineers were confident that they could overcome challenges of the unstable terrain and hurricane-prone area. Engineering professor John Brigham explains.
So sand, you really might not think you can build too much on this besides a sand castle, but you can, as long as you have the right engineering solution. As long as we can find a way so that our loads from our building can be distributed sufficiently into the soil, we'll be okay. One good option oftentimes is just to go deep, right? If we're gonna drill in here a pile foundation into our sand, if I go deep enough into this system, I can distribute that load both vertically, and if I go even further, I might be able to hit something solid that also provides us additional support.
For the foundations of the tower, engineers chose friction piles. Long steel rods driven into the ground, deep enough that the friction from the surrounding material secures them in place.
One potential solution for building on something like sand is to use a pile foundation. Now, those are going to be long, thin structures like this that are going to support our building, and the thought is that the deeper into the ground we go, the more strength we're going to provide. Now, just like this umbrella, right, if I just stick it into the ground, it's not doing much for me. It's pretty easy to move up and down, and it's pretty easy to move side to side. But as I drive it in, it's both going to become more stable from wiggling, but also harder to move up and down, giving us that vertical strength. Even though as I'm going down, the sand itself is not necessarily providing a lot more strength. It's about the sand all along the sides that's providing that frictional resistance as I'm driving this into the ground.
The friction pile method is well established. But during construction, it became clear that something was seriously wrong. And in November 2008, developers realized that South Padre Island's groundbreaking ocean tower was suffering from major structural issues.
Before construction was even complete, the tower had started to sink.
A small drop is expected and planned for, but that wasn't what was worrying people.
Nearly all buildings settle. It's no problem if the structures go straight down. But here's the rub. The ocean tower started to tilt.
Although engineers had anticipated the settling, no one had foreseen that Ocean Tower would lean. An investigation revealed that the problem lay in connecting the tower and the garage.
One of the key problems with South Padre Island was you had these two buildings that were connected to each other, and they were quite different, so they settled at different rates. You have one building that's quite tall and thin, being spread over a small area, and another building that's quite short and fat, so it's being spread over a much bigger area. So as they're pressing down, this thin building, this tall one, is getting dropped down quite fast, whereas the short one isn't. And because they're connected, they ultimately tilt instead of just dropping straight down separately.
If you stand on sand with a regular shoe, for example, you'll barely sink. But if you put the same weight on a stiletto, the heel will go straight in. In this case, the parking garage was the shoe, and the tower was the stiletto. They were always going to sink at different speeds. In fact, the tower settled twice as fast as the garage and didn't just sink into the ground, it damaged the foundation columns.
In September 2009, instead of attempting to save the building, the decision was made to demolish Ocean Tower. But it wouldn't be easy.
Even demolishing it was no simple task because you have a very large structure with a very stiff core. This is designed to be able to take high winds. It's designed to be able to stand under an extreme environment. So taking it down in and of itself is not going to be easy.
Engineers faced an unprecedented demolition nightmare. How to bring down 50,000 tons of concrete and steel without damaging the neighboring properties.
One option for taking down a building like this is to use a high reach, essentially a demolition crane to chew the building down.
On South Padre, strong winds were a constant threat, so that ruled out the high reach. It was just too dangerous. Instead, they went for explosive demolition.
The biggest challenge was preventing the tower's 3 hurricane-resistant concrete cores from toppling sideways. To ensure they crumbled safely, the tower was strategically rigged with more than a ton of explosives, positioned at key locations on 8 floors between the 1st and the 26th.
The key to successful explosive demolition is bringing the building down on itself. So you use a sequence of charges to remove key supports and basically collapse it like a layer of pancakes.
On Sunday, the 13th of December 2009, crowds gathered to watch the spectacle. And at 9 a.m., the explosives were detonated. Thankfully, the demolition was flawless, with no damage to surrounding properties, setting a record in the process.
At the time, this was the tallest reinforced concrete structure ever demolished with explosives.
I think you have to conclude with this that mistakes were made, that this building was not going to be safe, and the right decision was to take it down.
With massive engineering projects, safety must be a primary goal in order to prevent disaster. If the measures put in place fail, the scale of the catastrophe can be massive. Like this devastating incident in the Gulf of Mexico that caused a global crisis.
A catalog of failures led to a truly huge disaster.
An oil drilling catastrophe that shocked the world.
Deepwater Horizon was a wake-up call for an industry.
Across the world, global economies have an insatiable need for oil.
Oil and its derivatives are in plastics, fertilizers, lubricants, credit cards, phones, even toothpaste and contact lenses. Our thirst is huge. We get through around 100 million barrels every day.
We have been taking oil from underground for centuries, but over time it has become harder and harder to find, and extracting it safely is no easy task.
The deeper the oil and gas are found, the higher the pressure in the reservoir. Drilling into them isn't like tapping a water well. This is breaking into a massive pressurized cocktail of explosive gases and flammable liquids.
Innovative engineers push the boundaries with new techniques and technologies in order to safely obtain the precious black gold. Bryce Merrill has worked as a rig diver on deep-sea drilling rigs like this one.
What you see behind me is the Mr. Charlie offshore drilling rig. It was designed, built, and launched in 1954. It was the first one in the world that was movable and reusable, and it drilled for 36 years here in the Gulf of Mexico.
Exploratory oil drilling deep under the sea is a complex task. A rig is positioned on the surface over a proposed oil well. Piping is extended to the seabed, through which a drill bit can descend and drill deep into the rock. If oil or gas are found, it can be brought to the surface through the riser pipe.
Our drill pipe is 30 feet long, threader in each end. It's hollow, and they pump the drilling mud, which is a clay that's ground up into powder. They pump it down there, and it brings the drilling returns back to the surface.
One of the most important elements in the entire process is the drilling mud. It helps lubricate the drill head, helps wash metal and rock out of the way. But most crucially, it acts as a physical barrier to prevent oil from rushing up the pipe.
From the seafloor, it comes up to the surface below the rotary table here on this white piece of pipe called a riser, so that it can go into the pipes that run into the beaches to the refineries.
To prevent explosions, it's crucial to stop oil and gas from rushing to the surface uncontrolled. So, in addition to using mud, engineers install a safety device called a blowout preventer, or BOP, that can close the wellhead at seabed level. This tried and tested method of deep-sea drilling has been practiced successfully for decades around the world, until 2010, when an incident in the Gulf of Mexico became worldwide headline news.
Deepwater Horizon was a mobile exploratory rig, basically a massive floating drilling machine that could tap into oil reserves in deep water far beneath the seabed. In fact, it had recently drilled the deepest well ever, at over 6 miles deep.
On April the 20th, 2010, Deepwater Horizon was drilling an exploratory oil well in an area of the Gulf of Mexico known as the Condo prospect. Investigative reporter David Hammer knows the story.
So there were 126 people on the Deepwater Horizon in April 2010. Most of them were from Transocean's drilling crew. They owned the rig, drilling it to try to get the riches out from about 5,000 feet below the surface of the Gulf of Mexico.
Having discovered oil, Deepwater Horizon successfully established a wellhead so that the oil could later be drilled and processed at the site. Suddenly, at around 8:45 a.m., the rig experienced what is referred to as a kick. A surge in pressure from a pocket of oil and gas.
Well, on April 20th, 2010, high-pressure gas came careening up this mile-long riser pipe from the well up to the rig, and oil was spewing all over the deck.
Within moments, the gas and oil rushing up the riser pipe found a source of ignition, causing an explosion. Deepwater Horizon was consumed by flames.
There were a series of massive explosions. 115 people were able to survive. There were harrowing stories about some of them actually having to jump 100 feet or more down from the deck and into the water, and then they had to be saved by life rafts. The captain of the vessel actually had to use a knife to cut loose from the side of the vessel in one of those life rafts to be able to go and pick up some of the survivors who had jumped into the water, and the water had burning flames on the surface. It was really a horrible scene.
Firefighters fought the blaze on the rig for 2 days before it finally sank.
As Deepwater sank, it ruptured the well pipe near the seabed. Tens of thousands of gallons of oil gushed uncontrollably into the ocean all day, every day for 3 months. It was the worst oil spill in US history.
Tragically, 17 workers were seriously injured and 11 people lost their lives. Now it was time for engineers to deconstruct what had gone wrong and determine how to plug the leak at the bottom of the ocean. As the Deepwater Horizon tragedy unfolded, the whole world looked on as oil and gas continued pouring into the ocean. The big question was what had gone wrong. Initially, there was little to go on.
The explosion scattered most of the evidence across the ocean floor.
Having discovered oil, Deepwater Horizon's team had poured a concrete plug into the well, a standard practice to contain the oil and gas.
The plug is the first line of defense against oil leaking into the environment, like a cork in a shaken bottle of champagne. If it's not sealed properly, the contents will fly out uncontrollably.
But creating this concrete plug deep under the ocean bed isn't straightforward. Structural engineer R.N. Silapan is a concrete specialist.
Right now, the concrete is pretty plastic, and as you can see, it's sort of in a flowable stage, and we want it flowing freely to go down the well hole and plug at the intended depth. But concrete in this state will not do the job. In order for it to plug effectively, it has to harden. We refer to it as curing. This is how a cured concrete would look. And in order to accelerate the curing process, they use nitrogen in that mix.
But in this case, deep beneath the ocean, with mud, seawater, and oil pressing in from all different directions, getting the mix and the plug just right was crucial.
The official investigation concluded that the concrete had failed to properly seal off the well, although it stated that it may never be able to identify the exact reason why. But investigators did discover another engineering fail that was present at the well head. The blowout preventer, or BOP, had malfunctioned. It contained a safety device called a blind shear ram that, in the event of an emergency, would automatically cut and seal the wellbore. Experts believe that the pressure of the blowout had caused the pipe inside the BOP to bend, preventing a clean seal. The oil pipe rupture created as Deepwater Horizon sank to the seabed was reported to have leaked nearly 5 million barrels of oil into the Gulf of Mexico. It took engineers 87 days to securely cap the broken pipe under the ocean. Lessons were learned by the oil industry worldwide, and there is hope that a catastrophe on this scale will never happen again.
This was one of those disasters that defined an industry, and a reminder for everyone of just how dangerous drilling for oil can be.
When innovating for industrial progress, engineers often take risks. When those gambles pay off, the benefits can be great, but if even one factor is overlooked, a disaster could be inevitable. Like this calamity at a Spanish dam.
This catastrophe was an ecological nightmare.
There was a real sense of dread.
An engineering oversight that threatened a national park.
It was a really toxic tragedy.
Andalusia, a region of southern Spain famed for its beautiful landscapes. And there is none more stunning than this UNESCO World Heritage Site, called Doñana.
This part, in particular, the Doñana National Park, is a renowned area of natural beauty.
Environmental journalist José María Montero Sandoval knows Doñana well.
Doñana es uno de los puntos calientes de la biodiversidad europea. Es una zona húmeda por la que transitan todos los años cientos de miles de aves en su viaje migratorio entre África y Europa. Por tanto, una zona valiosísima, tan valiosa que es patrimonio de la humanidad por la UNESCO, y además hay una notable comunidad científica que acude aquí todos los años a trabajar con toda la biodiversidad que hay en este territorio.
Andalusia is not only rich in natural beauty, it also has hidden riches underground. Lawrence Dollimore is a local journalist.
Andalusia is a very historic mining area where people have been mining for thousands of years.
This is the Los Frailes mine near the Doñana National Park. The mineral ore extracted from here contains valuable metals, including zinc, copper, lead, and silver.
The Los Frailes mine has been an important part of Spain's economy. It's provided jobs in the region, and the silver and zinc extracted here supplies the whole of Europe.
Mining in this area goes back thousands of years because it sits on what is known as the Iberian Pyrite Belt. It was formed by volcanic activity around 350 million years ago and is mineral rich. Geologist Dr. José Manuel Canto Romero explains.
En la faja pirítica tradicionalmente se ha aprovechado precisamente la pirita, que es el sulfuro de hierro, sobre todo en la época de la industrialización, como mena para el ácido sulfúrico. Pero en la actualidad, en el siglo XX, el aprovechamiento se ha hecho específicamente para cobre, plomo y zinc.
The mining process involves the extraction and separation of metal ores from underground.
Once the ore is out of the ground, a cocktail of chemicals is used to help extract the metals.
Sí, para obtener un aprovechamiento adecuado, con un rendimiento óptimo de esos metales, varían en función además de cada tipo de metal los rendimientos. Para obtener, por ejemplo, 1 kilo de cobre hay aproximadamente que tratar en torno a 100-140 kilos de mineral.
The extraction and refining of metal ores creates a range of byproducts in both liquid and solid forms.
The trouble is, the leftover sludge known as tailings is highly toxic. It can't be allowed back into the environment.
The solution at Los Frailes, as with many mines, was to create a dam in which the tailings could be buried.
A tailings dam is essentially a raised, man-made reservoir, surrounded by dam walls, in which the toxic byproducts from the mine can be safely contained.
The dam formed a lagoon above that contained water used in the mine. In effect, another byproduct of the process. This water was highly acidic.
All of these toxic materials were safely held within the dam until one day disaster struck. On April the 25th, 1998, at the Los Frailes tailings dam, one wall catastrophically crumbled to the ground.
Once the dam's integrity had been compromised, the pressure of the water held in the lagoon above was only going one way.
The land surrounding this section of the dam gave way.
The earth around the dam moved quite dramatically. One section of the dam was pushed 67 meters, that's almost 220 foot, in a lateral direction. This reduced the height of the dam crest significantly.
As the crest of the dam wall sank, it began overtopping.
Tons and tons of waste and toxic acidic water gushed down towards the town and the villages and the farmland. There was a real sense of dread.
The tailings from the Los Frailes mine contain traces of lead, copper, zinc, cadmium, and sulfides, and the water from the acidic lagoon. This toxic mix headed downstream into the Guadiamar and Agrio rivers.
As the toxic sludge continued to spread, the nearby Doñana National Park was now under threat.
Todo esto era, en aquellos días era un mar de lodo, ¿no? El río, el Guadiamar, se había desbordado por el agua contaminada y por los lodos, y todas estas riberas estaban cubiertas de lodos cargados de metales pesados, cargados de lodos tóxicos. Los árboles, por ejemplo, yo recuerdo que estaban cubiertos de lodo. Los pies de los árboles estaban cubiertos de lodo porque el lodo además se extendía muchos metros.
The scale of the catastrophe was shocking.
More than 2,000 birds were killed and tons of dead fish were found downstream.
Por tanto, el impacto en un primer momento era evidente, era muy fácil de ver y era fácil imaginar también qué impacto iba a tener en el futuro si no se hacía nada.
In the wake of the disaster, answers were demanded as to what had caused the dam to collapse.
Geotechnical experts suggest that the dam's foundation failed due to the chemical impact of toxins contained within the dam.
The foundations consisted of clay and calcium carbonate, which were exposed to a chemical attack from the acidic and pyritic slurries contained within the dam. With the foundations compromised, the pressure from the water within the dam caused a 20-meter section of the wall to collapse. Billions of liters of toxic slurry were released.
El agua que hay detrás en la balsa pues es la que ha empujado toda la pirita flotada que ha avanzado, desgraciadamente, hacia el Parque Natural de Doñana. Pero puede decirse que la causa de la rotura es simplemente una superación de la capacidad portante del terreno, en este caso de esas margas azules, y ese fue el gran fallo técnico que aquí se produjo.
When the dam breached, engineers had to act quickly to minimize the threat to the local ecosystem.
With toxic sludge and acidic water on the move, the race was on to stop it in its tracks. A temporary dam was quickly constructed downstream. It prevented the national park from being completely decimated, but a great deal of damage had already been done.
Now it was up to emergency workers to clean up the toxic waste and save Doñana.
La obra de restauración del Guadiamar fue una obra faraónica, que se hizo en gran medida gracias a la presión de la comunidad científica, ¿no? Hay que imaginarse que en pocos meses, en poco menos de un año, se retiraron 7 millones de metros cúbicos de tierra contaminada, 500 camiones operando prácticamente las 24 horas del día, recorrieron 17 millones de kilómetros y fueron muchas personas trabajando constantemente en todo lo que era el río, en todo lo que eran las márgenes del río.
The cleanup operation was huge. Over 4 million tons of this toxic sludge had to be removed, along with 400 million cubic meters, so that's 106 billion gallons of acidic water. All of this had the hefty price tag of $100 million.
Worryingly, some experts have speculated that it could take up to 40 years for the affected farmland and wetlands to fully recover.
Following the incident, the Los Frailes mine was closed for 17 years. To resume mining, engineers had to come up with new, safer ways of dealing with tailings.
Lessons were learned so that hopefully this type of disaster will never happen again.
A Chicago skyscraper hides a deadly flaw.
These problematic windows led to outrage.
A fuel storage depot goes up in a fiery inferno.
There was a scene of devastation.
Smoke could be seen from space.
A championship stadium suffers a devastating collapse.
Many people knew of someone who was involved, so the impact was grave.
And a major Canadian bridge reveals signs of catastrophic failure.
There were cracks and fissures that seriously imperiled the bridge.
With big builds, even the smallest mistake can be a huge disaster. From miscalculations to misunderstandings. Some with deadly consequences. These catastrophes are every engineer's worst nightmare. When it comes to building big, engineers have to carefully consider every material they use. If a single one doesn't do its job, a catastrophe could be on the horizon. Like this bold build in Chicago that became famous for all the wrong reasons.
The tower was never in danger, but the same couldn't be said for the people below.
A standout structure with a fundamental flaw. And an engineering catastrophe that quickly turned to tragedy.
People wanted action, they wanted it to be fixed, and they wanted it to be fixed now.
Chicago. The Windy City is famous for its extreme weather and extraordinary skyline. Boasting some of the tallest and most iconic buildings in the US.
When you think about epic architecture, you may think New York, but Chicago is actually considered as the birthplace of the skyscraper.
As local journalist Lee Bay knows well.
But Chicago has more than a century of fine buildings, particularly downtown. The downtown is relatively compact. The lake on the east side, the river and railroad tracks on the west. So there's no place to go but up. So 3 of America's tallest buildings are right here in Chicago.
In 1972, insurance company CNA Financial opened its brand new headquarters in downtown Chicago. To stand out in an already crowded skyline, architects came up with a bold plan.
This building comes in the 1970s, so it's, as a modernist building, it's pretty late. So to make the building stand out in a city of great architecture, they did an unusual thing. They painted it this shade of red.
Dwarfed by some of its neighboring high-rises, the plan to get the CNA Tower noticed by its eye-catching paint job earned it a catchy nickname. Big Red.
You know, Chicago has one of the most distinctive skylines in the world, certainly in America, built out over the course of 100 years or more, actually more than 100 years. And as a result, you want your buildings to stand out. So there's high-rise buildings, low-rise buildings, and most of them are gray and maybe a little bit of white, maybe black. But occasionally, to make your building stand out, you put in a splash of color. So this is a great example.
It earned the name Big Red, and it's pretty obvious why. Its striking crimson paint job was designed to emulate the sun setting over Lake Michigan.
Big Red became an instant landmark, as architecture historian Rick Keel explains.
The architecture is modern architecture. Think steel and glass box. It is 600 feet, 44 stories tall.
The building was a box design made up of heavy steel beams with thick frames and around 3,000 recessed windows set back 38 centimeters into the frame. And it's these unique windows that would give Big Red a reputation. Because the dazzling paintwork wasn't Big Red's only defining feature. Each of the 2-meter by nearly 3-meter recessed glass panels was given a grey tint, designed to give the facade the ability to play with light and shadow.
Big Red has 3,000 windows, all sitting in recesses between the thick beam structure. It's simple, yet stunning.
Big Red had achieved its goal of standing out from the crowd, but within months, it stood out for very different reasons.
Almost from the beginning, there were problems with its windows. There are 2,900 windows in this building.
There were complaints about windows cracking. There were actually 2,000 complaints in those first two years.
The complaints weren't just from tenants within the building. In 1994, a passerby was hurt by glass falling from the 36th story. Several years later, on June 7th, 1999, a large crack was discovered in a window on the 29th floor. A white adhesive film was applied as a temporary measure to the entire pane to prevent pieces from falling out. This was covered with a piece of black plywood that sat inside the frame to be fixed at a later date. But on October the 8th, 1999, the unthinkable happened. A piece of jagged glass, about the size of a cafeteria tray, fell from the 29th floor, hurtling down from over 100 meters in the sky.
A young lady is walking downtown to a job interview. In fact, she gets off the L that's roaring behind us. And one of these windows, one on the 29th floor, falls from the building, floats over the L track, and strikes her as she's walking across the street on the west side of the street, holding her young daughter's hand.
Tragically, the young mother died. In the wake of the disaster, engineers investigated why so many of Big Red's windows were faulty, so they could prevent this from ever happening again. The reason at first seemed simple: the Chicago climate.
Chicago experiences some pretty extreme weather, from hot summers to freezing winters. And as every engineer knows, materials used in construction of a building will always respond to changing temperatures.
But why, in a city skyline filled with high-rises, was Big Red the only building apparently failing to cope with the climate? Forensic structural engineer David Drengenberg explains.
If you look at any skyline in any major city, you'll notice that the majority of buildings are clad with some type of curtain wall made of glass, which lets light in. Glass expands and contracts with changes in temperature. So if a building is exposed to direct sunlight, you'd expect the glass panel to uniformly expand in all directions.
In an effort to make Big Red stand out, setting the glass panes so far back into the frame may have caused this catastrophe.
When a window is installed in a place that receives only partial sunlight, the portion of the window that is exposed to sunlight will heat up faster than the shaded portion. So now you have the condition where one part of the glass is heated, the other part of the glass is cooled, and that tug of war between the expansion effects of the heated glass can create internal stresses that can sometimes form a crack.
Big Red's windows were being subjected to a phenomenon known as thermal stress.
Thermal stress occurs when heat causes an area of one piece of glass to expand against the cooler piece, resulting in cracking.
The warmer area of the glass which wants to expand begins to push against the cooler area which doesn't, creating thermal stress. If enough thermal stress builds up, the glass will crack.
The center core of the window would heat up faster than the perimeter of the window. As it heated, the center core expanded, the perimeter of the window stayed the same, and so between the two, something had to give.
Because all the panels were set back, the glass that was in direct sunlight was heating up and expanding. But the glass in the corners that was shaded was receiving much less sunlight and contracting, causing the glass panels to crack. David Drengenberg demonstrates.
We've assembled here a demonstration model to show how cracks would be expected to propagate under these kinds of environmental conditions. The window is installed into an aluminum extruded frame, and the effects of the expected temperature conditions have been replicated by a heat lamp in the middle a fan on the edge. We've used a time-lapse camera to record the development of a crack. Okay, let's run the test and see what happens here. Light on.
David's experiment exposes one side of the glass plate to warm air and the other to cold, similar to how Chicago's winter weather affected Big Red. It's not long before the thermal stress causes the glass to fail.
As you can see, we have developed a crack after exposing the window panel to a number of heating and cooling cycles. And as expected, the crack propagates from the exterior, and as is common in brittle materials, continues to propagate all the way through.
Glass is a brittle material, and once it begins to crack, catastrophic failure isn't far behind.
In Chicago, the eye-catching skyscraper Big Red had a catastrophic design flaw. Its unique setback windows were putting unexpected stress on the panes. Engineers realized there was nothing they could do to salvage the existing ones.
With such a tragedy, engineers were left with only one choice: to replace all 3,000 windows on the building, but this time with glass that could handle Chicago's diverse climate.
But swapping out 3,000 windows couldn't happen overnight, so a temporary safety measure was initiated.
Replacing all those windows was a time-consuming task. To prevent more of them from breaking before they could be replaced, a stick-on protective film was applied to hold the glass together in the event of a failure.
This thick, adhesive safety film is made up of micro-polyester layers and is often used on buildings in places prone to hurricanes. If the glass breaks, it remains securely attached to the anchored sheet until it can be replaced. Big Red's windows were replaced with new, thicker, heat-tempered glass designed to stand up to thermal stress. In addition, they introduced a new safety measure.
To this day, Big Red's windows are each inspected on a monthly basis to ensure that glass will never again fall from the sky.
When designing a new structure, engineers have to consider its surroundings, as well as what it's intended to contain. Get that equation wrong, and all hell can break loose. Like this fuel storage depot outside of London that went up in flames.
This was a truly explosive engineering disaster.
It was absolutely extraordinary. I've never seen anything like it. It was just such a huge wall of flames.
This was a disaster just waiting to happen.
With hazardous substances like these, there is simply no margin of error.
Across the world, every major economy relies on oil, massive amounts of it. And in order to ensure that supply is constant, it needs to be stockpiled.
Oil makes the modern world go round, but it's not just sitting there on tap 24 hours a day. It has to be extracted, refined, and crucially stored. But it's dangerous at every stage.
Storing oil safely isn't easy, as fire safety engineer Fatih Tarada explains.
Storing fuels, especially on a large scale, requires constant monitoring of how much fuel you've got, and also not just the liquid fuel, you also have to think of the volatiles, the gas as well, the vapor, where that's going. Because the vapor can actually be a lot more dangerous than the liquid fuel itself.
Around an hour outside of London lies Buncefield, a facility especially designed to safely store dangerous liquids.
Buncefield is one of the largest oil storage depots in the UK. It was designed to safely store up to 60 million gallons of oil and petrochemicals.
Like any facility of this type, safety is the primary goal.
All of the storage cylinders are surrounded by bund walls, physical barriers that contain the contents of the cylinders in the event of a spillage.
The bund walls are designed to have a greater capacity than the storage containers they surround. In the event of a spillage, all escaped liquids will stay in a controlled area. In addition, all storage containers are equipped with an array of level monitors and safety valves. However, even the most secure facilities can suffer from catastrophe. On Saturday, December the 10th, 2005, a routine delivery of fuel arrived at the Buncefield facility for storage.
The filling team started to input petrol into the storage tank 912 as evening set in. And we're talking about a lot of fuel, so this was going to take some time.
The process seemed to be going smoothly until the early hours of the morning when something went wrong.
By 5:37 a.m. on December 11th, the level within the tank exceeded its ultimate capacity, and the petrol started to spill out of vents on the tank roof.
No safety alarms were triggered, and the highly flammable liquid continued to overflow unnoticed. After spotting an unexpected vapor cloud, a member of the Buncefield team hit the alarm, which activated the emergency water pumps.
A vapor cloud explosion occurred almost immediately.
After this terrifying explosion at one of the UK's largest fuel storage depots, the blaze rapidly spread throughout the facility. David Mitchell lives near the site and remembers the horrors of that night.
My wife and I were in bed when we heard a huge explosion, which really made us jump. All the alarms started going off, smoke alarms and things, and my first thought was that a plane had crashed on us. It was so loud, and the whole house was shaking, literally shaking. I could see the curtains dancing around. And then the ceilings come down, and the walls started to crack. All the plasterwork was cracked, and all the ceilings in the kitchen had collapsed. At this point, I was in total shock because it just looked like the house had been destroyed. But my real thought was to, because I had a young family, was just to get out of here. When I came out into the back garden, all the windows looked like they were going to fall out any moment. And the top half was leaning over, and there was a huge crack across the top of the house there, and tiles would come off the roof. And in fact, you know, there was actually a hole. You could stand in one of the bedrooms and look up, and you could see through to the sky.
Chief Fire Officer Roy Wilshire and his firefighters were called to the scene.
They describe approaching the site and seeing trees blasted, dead animals, birds in the road, cars abandoned, a scene of devastation. And as I say, there was almost 300 buildings damaged on the Maylands estate alone, and very severe damage.
The ensuing fire was the largest seen in the UK since World War II.
So I remember looking at Buncefield over there and thinking it was absolutely extraordinary. I'd never seen anything like it. It was just such a huge wall of flames, because this is seconds after the explosion, so all the petrol had only just gone up.
The smoke cloud could be seen from space. The smoke cloud blacked out central London, so Victoria was like midnight at midday.
40 people fell victim to injuries, but fortunately there were no fatalities. The fire lasted 5 days, with massive amounts of water and firefighting foam required to bring the blaze under control. In the aftermath, investigators had to uncover what had gone wrong. They first examined the automatic safety features on the faulty cylinder.
The tank had two forms of level control: a gauge that enabled the employees to monitor the filling operation, and an independent high-level switch, which was meant to close down operations automatically if the tank was overfilled.
It was clear that the initial level monitoring gauge had malfunctioned.
There was no way to alert the control room staff that the tank was filling to dangerous levels.
Further investigation revealed that the independent high-level switch had also failed due to a missing component. The compromised switch mechanism, combined with a defective monitor gauge, caused the fuel to overflow and fill the area within the bund wall. However, the liquid fuel itself wasn't what actually caused the explosion. As the fuel came into contact with the air, molecules on its surface started to evaporate, forming vapor which began to rise.
The bunded wall you can see there is there to contain liquid. It's not there to contain vapor. So vapor would spread over.
A vast combustible cloud now filled the air.
This was a powder keg ready to go off. All it needed was a tiny spark.
Investigators believed that tiny spark was created only after fire alarms were manually activated. As members of the public and tanker drivers noticed the vapor cloud, they alerted site workers who hit the alarm, automatically triggering the firewater pump. Ironically, it's thought that a spark from this pump is what ignited the vapor cloud. With the fuel ablaze, another failure came to light, this time in the bund wall itself.
The bund wall contained another engineering oversight. Plastics and silicon had been used in its construction. The heat of the explosion caused these to melt, allowing fuel to escape the bund wall and subsequently the fire to spread.
Fatty Tarada was part of the investigation team that uncovered this catastrophic failure within the bund wall joints.
If you have a bund for a hydrocarbon product, you expect it to operate, especially in the case of fire, because that is the primary risk that you're designing against. So if it doesn't operate, if you have a fire, what's it there for?
The legacy of the Buncefield disaster prompted many questions when it comes to the safe storage of fuel.
What should have happened, there should have been electronic alarms, there should have been computer alarms, there should have been human intervention, and none of those worked to stop that petroleum being pumped down.
All this has been factored into the rebuild of the facility, with particular focus on the bund wall containment system.
It was realized that not only did they need to contain liquid, any material used in the joints would have to be able to withstand explosions and fire.
After such extensive damage from the explosion and fire, the facility needed to undergo a lot of reconstruction. Not only that, repairs were needed across the surrounding areas.
Although the facility is once again up and running, the long-term impacts of the explosion at Buncefield still linger to this day.
The environmental, social and economic toll was considerable. While no one lost their life, some have yet to fully recover from the effect of the explosion.
Whereas before, it was a catalogue of errors, and I can't believe that anybody would allow that sort of lack of safety to ever occur again. However, I'm hoping that everybody learned from the experience last time and that everything now is state-of-the-art and all the proper procedures are there.
When engineers get their calculations wrong, the consequences can be instantly catastrophic. However, sometimes it can take decades before an oversight comes to light. Like this bridge in Canada that hid its lethal design flaw in plain sight.
This engineering issue was overlooked for years.
There were cracks and fissures that would collapse the bridge.
A vital transportation link that put commuters at serious risk.
This bridge just wasn't built to stand the test of time.
Montreal was founded in the 1600s, a hub for fur traders, built up on the side of a small mountain that gave the city its name.
Named after the triple-peaked hill in its center, Mount Royal, the city of Montreal is sandwiched between the St. Lawrence River to the south and the Rivière de Paris to the north.
Montreal is actually an island surrounded by waterways. The only way on and off is by bridge. Local journalist Teddy Elliott explains.
Bridges are perhaps the most important element of the city because it connects the city to There's the United States. It connects the city to the northern part of Quebec.
In 1957, work began on the first Champlain Bridge, connecting the island of Montreal with the South Shore suburbs. The massive crossing would stretch for more than 7 kilometers, with long approaches leading to a steel truss cantilever center span, just over 3 kilometers long. The epic structure cost $52 million and incorporated a bridge deck design that made it truly cutting edge.
This bridge was designed in the 50s, and the material of the moment was pre-stressed concrete.
Pre-stressed concrete is made with tensioned steel members in or around it. These steel tendons significantly increase its tensile strength.
This allows architects and engineers to design and build lighter and shallower concrete structures without sacrificing strength.
The original Champlain Bridge opened in 1962. By the 1970s, it was the nation's busiest crossing. It ushered traffic to and from the city of Montreal for decades without any problems. But by the turn of the century, it began showing signs of failure.
In the late 2000s, they found that within the actual superstructure of the bridge itself, there were cracks and fissures that seriously imperiled the lifespan and potentially collapse the bridge if they continued to proliferate.
Cracks in the concrete and rust on the reinforcing steel cables were telltale signs that the bridge could be in serious trouble.
A thorough inspection revealed that severe deterioration was occurring across the entire structure. A worrying thought, given how many cars used the bridge daily.
Of particular concern was the degradation of the pre-stressed concrete decks on the bridge approach. Engineers investigated and discovered the cause of its untimely demise.
Montreal gets hot summers and very cold winters. Water finds its way into the smallest crevices, and as it freezes and thaws with the climate, it expands and contracts. And this process over time causes cracks to grow and the concrete to break.
The cracking concrete exposed the steel rebar inside to water. But the runoff from the bridge above wasn't just pure water. Engineer Steve Stelzer explains.
In our climate, we have a lot of salt that's used on the roads to clear off ice. We have a lot of freeze-thaw. We have very inclement weather. The weather can change drastically in a matter of a few days.
When you have cold, icy winters like in this part of Canada, roads and bridges are regularly salted to make them safe for motorists. When that salt dissolves into snow and rainwater, it runs off the deck and down the structure of the bridge. Once it comes into contact with any exposed steel in the pre-stressed concrete, it can only mean one thing: rust.
Rust occurs when oxygen and water react with the steel rebar, forming iron oxide. When salt is added to the water, it accelerates the corrosion by up to 10 times.
Over time, freeze-thawing in the concrete and rusting of the steel caused integral parts of the bridge to crumble and fall at a pace not foreseen by the engineers that built it.
And this process was made even worse by a flaw in its design. Professor of Structural Engineering Lotfi Guzani explains.
In this bridge, elements were integrated together, but there was not proper drainage system. Also, there were no waterproof membrane like in today's bridges. So salty water comes through the deck and attacks and infiltrates within the concrete and attacks the steel tendons, which pre-stress the concrete.
The long-term results of this slow decay can be extremely hazardous, as concrete surveyor Mark Vandry explains.
There started to be cracks and corrosion forming in the post-tension cables, in the rebar, that could have, over the long run, caused a catastrophic failure.
The way the bridge was constructed, the elements are integrated together. So if one beam fail, there's a large part of the bridge which will fail.
Montreal's Champlain Bridge was deteriorating much faster than engineers had ever anticipated. With the corrosion advancing, a solution was urgently needed. Plans were made to replace the bridge, but that would take years to complete. In order to keep traffic flowing, the pre-stressed bridge approach decks were reinforced with what was dubbed a super beam.
The super beam was a large steel beam that was placed over the concrete beam on the bridge deck, which allowed them to keep it stable.
You're basically creating a structure to support another structure. So they created these super beam trusses to support parts of the deck. Now, the problem with this type of fixing with super beams and trusses, fixing parts of the deck, you're redistributing the load patterns of the way the structure was meant to act. And what happened is that it caused cracks and other structural problems in other parts of the deck.
To maintain the old bridge until the new crossing could be built, it also had to undergo regularly scheduled repair work.
Ultimately, choosing concrete for the deck and girders proved to be the wrong choice. Concrete is difficult to repair effectively, and patching it up will never last.
One reason that concrete was chosen was that it could be pre-cast, speeding up the bridge building process. But although pre-stressed concrete was innovative for the time, it turned out to be a maintenance nightmare.
The steel would have been a better option because when they chose pre-stressed concrete, this technology was not mature, and they have a lack of knowledge about the durability issues.
It's just not suitable for our climate for bridge work, where there's lots of salt, lots of drainage problems, there's corrosion. With pre-stressed concrete decks and girders, once it's in, it's very hard to reinforce it and go in and actually fix it.
Steel can be easily cleaned, reinforced, and have extra strengthening elements welded to it.
With the old Champlain Bridge scheduled for demolition, back in 2015, work began on its replacement. The new crossing opened to traffic in July 2019, a 168-meter asymmetric twin cable stay bridge. Costing $4 billion, this epic piece of engineering carries 6 lanes of traffic, and with a width of approximately 60 meters, it's one of the widest bridges in the world. With the use of cutting-edge design and, crucially, the right choice of materials, the new Champlain Bridge is designed to survive Montreal's tough weather for 125 years.
Hopefully, Montreal's new crossing will keep traffic flowing smoothly and, more importantly, safely for decades to come.
With big engineering, careful planning in both design and construction is usually the secret to success. But get either wrong, and it can be a recipe for disaster. Like this catastrophic collapse in Holland, which exposed critical flaws in construction.
Fundamental engineering errors and communication failures led to a fatal collapse.
A stadium tragedy that shook a city to its core.
It gets emotional when something happens, and why us?
The lessons learned from this failure serve as a reminder of the importance of coordination, communication, and checking.
In the central region of the Netherlands, known as Twente, lies the medieval and picturesque city of Enschede. With a population of just over 150,000, the beating heart of this town is its soccer club, FC Twente.
FC Twente from Holland are a top-flight soccer team based in the Dutch city of Enschede.
As local journalist Bart Hinke explains.
FC20 is a club that's deeply rooted in this region. They have about 28 supporters, fan clubs in the region, and you can see the loyalty of the fans in times of success, but also in time of worry and trouble.
Soccer, or football, is the most popular sport in the world, and FC20 is no exception. The club regularly attracts crowds of over 26,000, which for a city this size is no mean feat.
Founded in 1965, FC20 was a small-town club with big ambitions. And in 2010, those dreams were realized when they won the Dutch Championship.
They were excellent times, something that we could only dream of. It was just a crazy day for every fan.
Winning the league championship meant FC20 also qualified for the biggest cup competition in Europe. And their owners decided they needed a stadium to match.
The work was part of the club's development to create a stadium capable of holding more than 30,000 people. This would catapult them into the big league.
The plan was to extend the existing L-shaped section into a U-shape that was more than 45 meters long to accommodate nearly 7,000 additional fans. The cantilever-style roof would consist of 11 load-bearing frames, all linked together and supported by coupling bars connected to each frame at various points. Construction began in February 2011, with the assembly of the steel roof scheduled to start on May the 23rd.
The only problem was that the roof and the entire extension had to be completed for the start of the soccer season just over 2 months away. This was an ambitious project right from the start.
Professor of Building Engineering Robert Neese believes the impending deadline was adding extra pressure onto an already tight schedule.
Well, the usual thing in football stadiums, they take a long time to find all the money. And when they've done that, they want it finished tomorrow. It's always hurry, 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 because they have started the new football season. And when people start to work quick and there's no good supervision, which is very severe on the people, things go wrong.
With construction running behind and the beginning of the new soccer season quickly approaching, the unusual decision was made to work on separate parts of the stadium simultaneously.
When you're carrying out a construction on this scale, or any scale for the matter, there's a logical order in which things have to be done. But in the rush to get the project completed on time, that basic rule seems to have gone out the window.
People were doing things together in the same time while it was dangerous. There should always be some external supervision who says, no, you may not work on the stands while they're working on the roof.
Because the concrete staircases hadn't yet been completed, the main contractor abandoned the original plans and had people working directly underneath the roof while it was still being constructed. This sounds like a recipe for disaster.
On July the 7th, 2011, as work on the steel roof at FC20 continued, and with workers still on top and underneath it, the entire roof collapsed onto the seats below. Photojournalist Eric Brinkhorst was one of the first on the scene.
I received a phone call when I was editing my pictures in my office. So I grabbed my gear and I drove.
Rescue workers were already on site trying to free people trapped in the wreckage.
There were some ambulances, there were people helping. The complete tribune was, of course, completely collapsed, so it was a harmonica of material.
Despite their best efforts, tragically, 2 construction workers lost their lives.
He gets emotional when something happens. Why us? It really hurts, and of course, it stays with you.
Many people knew of someone who was involved, working on the terrace or on the roof at the time of the collapse. Apart from the 2 casualties, there were many injured, and a lot of the boys on the stands are, also working in construction. So the impact was grave.
The tragedy sent shockwaves across the city and throughout the entire soccer world, and questions were being asked. Had the rush to get the stadium completed led to fundamental and fatal engineering errors? An independent report discovered that basic engineering rules and safety had been overlooked.
There's no actual problem with the structure of the stands and the roof itself. It's okay, it's well done, good executed, no problems. The real problems are during building up. It's not like by magic everything stands together. You have to work out the structure in a careful way, taking care that stability in all situations is guaranteed.
The main problem lay in the temporary support to the cantilever roof. Like any cantilever structure, the stadium roof requires temporary support, known as falsework, to hold it up until complete. In this case, they used temporary bracing in the form of steel cables to maintain stability during construction. The problems began when some of the supporting cables were removed to allow for work to simultaneously continue on the staircases and stands below, causing it to become less stable and, crucially, less strong.
They started adding the finishing touches when the steel roof structure was still very much under construction.
To make matters worse, they began adding considerable weight to an already unstable and incomplete structure.
And in this case, they made this big cantilevering roof on which they hang a television screen of 3,000 kilos at the end of the cantilever. So it's a big force blowing down.
The roof was subjected to an extra load of a video wall, suspension bridges, roofing sheets, and 10 workers. It simply couldn't take all that extra weight while it was still under construction.
The lack of stability combined with the massive overloading caused 2 central load-bearing frames to buckle and collapse, taking the rest of the roof with it.
This was one of the biggest failures, that they didn't make the precautions necessary to make the building stand up or the roof stand up during constructions. They did not do that, things collapsed, and then you got the progressive collapse. They wanted a big roof. And they got a big roof, only they built it in the wrong way.
The new section of the stadium was finally opened in early 2012. And new rules about safety and the use of temporary works were put in place to prevent any repeats of this tragic disaster.
Many of the construction workers were very proud of actually working on the club, working on their stadium, and as they said at the time, working on the dream. And obviously when this tragedy unfolded, their dream collapsed as well.
I know a famous architect once said to me, a building is built twice, once on paper and once in reality. And if you don't do it right on paper, the reality won't work. And that happened in Twente.
In a rush to get ready for the start of the soccer season, it appears that vital things were overlooked. But a tight deadline must never be allowed to overrule safety.
In Boston, a deadly flaw brings traffic to a screeching halt.
That epoxy gave out and the concrete fell down.
A river crossing collapses in Wales, devastating the local community.
So I picked the phone up. She said, the bridge has come down. Well, it's just unbelievable.
In Milwaukee, a bridge begins crumbling in broad daylight.
The fear was that the entire structure might come tumbling down.
And a dam collapse in Spain changes the course of history for one town. With big builds, even the smallest mistake can be a huge disaster. From miscalculations to misunderstandings. Some with deadly consequences. These catastrophes are every engineer's worst nightmare. When engineers go big, every last detail must be checked and double-checked. Because the most innovative builds can be undone by the smallest oversight. Like this interstate tragedy in the capital of Massachusetts.
This was a structural project on a supersized scale.
A massive infrastructure upgrade to a city's road network.
At its peak, the project was employing upwards of 5,000 people.
A disaster that revealed a weakness hidden within the system.
There was a lot of talk about whether this was a safe project.
Boston, Massachusetts, was founded nearly 400 years ago beside the Charles River and has grown to become one of America's most visionary cities. Tim Logan is a local journalist.
Boston is one of the oldest and most historical cities in the United States. The beginning of the Revolutionary War was here, and it's always been an innovative city. It prides itself on that.
Boston is home to the Red Sox, the Revolution, and radical thinking. So when it comes to testing boundaries, this city doesn't hold back.
However, in terms of urban infrastructure, Boston was stuck in the past.
With a street plan devised in the days of horse and cart, for decades, Boston was one of the most congested cities in America.
This was a clear obstacle to progress, as transportation reporter Tom Palmer explains.
A lot of the streets and paths in Boston that are still here today were basically formed by cows walking around, and they're narrow. After World War II, Boston, like many American cities, was a crumbling city. People didn't want to come here, nothing was being built.
At the center of Boston's urban decline stood a particularly troublesome freeway. Although it wasn't very old, it came to symbolize a city unwilling to change.
This stretch of highway was built in the 1950s, and it was hopelessly out of date. The elevated freeway, which had been built as a solution, had effectively cut the city in half.
It divided the city from its waterfront.
Boston was gridlocked. Entire neighborhoods were cut off, and the elevated freeway was in serious decline.
It was never designed to cope with the huge amount of traffic. This city was going nowhere fast.
It was stall and crawl all the way through town at rush hour and sometimes all day long. 90,000 cars is what it was designed for. 180,000 cars was what it was taking toward the end, and it was crumbling and needed to be replaced.
In 1991, work began on an engineering project that aimed to catapult Boston's transportation infrastructure into the future. It was called the Big Dig.
To open up the city and reconnect communities, the bold decision was taken to go under the very heart of downtown.
In the early 90s, a construction project began, the Big Dig, to replace the old elevated central artery and to put it underground, right in the middle of the city.
The project would reroute the section of I-93 that runs through the heart of the city. It would include a new tunnel and a new bridge, complete with additional green spaces in the center of Boston.
This was one of the most ambitious engineering projects ever undertaken. 6 huge sections of highway, tunnels running 1.5 miles or 2.5 kilometers right under the heart of downtown, and on top of that, the widest cable-stayed bridge in the world.
The idea was to get the cars out of sight, out of mind, and to put something really good on the surface, and that's the park.
They were going to turn a once desolate space into a beautiful park and reconnect the city with the river and the people with each other.
The scale of the dig was enormous, and it wasn't going to be easy.
The biggest challenge for engineers was that throughout the entire construction, they had to keep the city moving, however slowly. So the tunnels needed to be built under the city while the old elevated freeway remained open.
Engineer David Beck worked on the project.
It was always a high priority to keep the existing traffic flowing as smoothly as possible while maintaining progress on the construction.
And if that wasn't enough, it all had to be done in unstable conditions because most of Boston was built on reclaimed land dating back over 200 years.
Digging on a scale like this, directly underneath a bustling city and through precarious reclaimed land, presented engineers with a huge challenge. And the city with a hefty price tag.
This was the most expensive highway project in US history. It went 14 years and more than $12 billion over budget.
But an ever-increasing schedule and spiraling costs weren't the only issues with this project. In 2006, after all of the main bridges and thoroughfares had been opened to the public, tragedy struck.
There was a 3-ton piece of concrete used for ventilation that fell and killed a lady, unfortunately.
A project that had initially brought hope to the city sent a shockwave through Boston.
There was a lot of fear about driving in any of the tunnels. There was a lot of talk about whether this was a safe project, whether it had been done safely.
After the collapse, there were real concerns about the overall safety of the entire project.
In the wake of the disaster, a federal investigation was launched to uncover what had caused the collapse. The answer lay in a material used in the construction called epoxy.
Epoxy is a structural adhesive which is widely used in the construction of everything from aircraft to automobiles, anything where a high-strength bond is needed.
The tunnel design included an overhead ventilation system suspended from the ceiling, but one 90-meter section of the tunnel lacked the necessary support structure, so a retrofit solution was needed. Holes were drilled overhead and long anchor bolts inserted, secured with epoxy for extra strength.
The investigation concluded it had something to do with the epoxy that those heavy panels were hung in and the bolts that went into them.
The concrete roof had been poured before they designed the ventilation system. And in that area of 300 feet, they had to go ahead and drill in inserts, and they used grouted, epoxy grouted inserts into it rather than mechanical sections. And that, over time, that epoxy gave out and the concrete fell down.
The investigation also revealed that the epoxy-secured anchor bolts used in this section were incorrectly installed. Not only that, but this retrofitted solution was an inadequate choice for the ventilation system that weighed hundreds of tons. Concrete expert Gary J. Klein was part of the investigation.
We're going to test the pull-out strength of an anchor that's of the same size as the anchors that was used in the connector tunnels for the big dig and is embedded the same distance into the concrete.
This test shows the load-bearing capacity of anchor bolts that have been properly installed. The concrete has been drilled and cleaned, and the epoxy correctly applied.
This pump is pumping the hydraulic ram, which is extending this larger rod, which pulls out, if you will, the smaller rod that's embedded into the concrete. The concrete failed, as expected, in what we call a breakout failure. So the epoxy held, but the concrete itself was only so strong, and we got a breakout failure.
In this instance, the concrete itself failed before the epoxy anchor bolt joint. In this second test, the anchor bolts have been installed incorrectly, similar to what happened during the Big Dig. The results are clearly different.
So these test results are quite different than compared to the first test. And the first thing you'll notice is that the epoxy is failing. The rod is literally pulling out of the concrete without damaging the concrete itself. In the first test, where the epoxy was properly installed, it was strong enough to force the concrete to break out. In this case, it's nowhere near strong enough.
The correctly installed anchor bolts are more than 4 times as strong as those installed incorrectly.
The failure mode was the same type of failure that occurred at the Big Dig. It slowly pulled out without having enough strength to cause a breakout failure of the concrete or a failure of the rod itself.
But what could engineers do to solve this problem and salvage the entire Big Dig project for the city of Boston? After the deadly tunnel collapse of 2006, all of the incorrectly installed anchor bolts used in the ventilation system were closely examined. 242 were highlighted as potentially dangerous. As a fix, a new type of anchor bolt was proposed. Concrete expert Gary Klein explains.
They insert this entire assembly into the hole, but then there's a second step in which they rotate the outer portion of the assembly such that these flanges are forced to spread out around the bottom, such that these flanges give direct mechanical attachment, if you will, between the anchor and the concrete. They should provide excellent performance for the lifetime of these tunnels. You would not expect to see any kind of pull-out over time.
All the anchor bolts had to be replaced with these new, stronger, expanding versions. After the upgrades, Boston's tunnel ventilation was deemed safe again for commuters.
Despite its problems, the escalating costs, and the massive overruns, the Big Dig definitely worked.
The Big Dig was an engineering marvel in many ways. Most people recognize that Boston would not be the booming city it is today if it didn't have this highway put out of sight, out of mind underground, and a really nice park on the surface.
Running the freeway underground has given the city and its people a chance to reconnect.
While this project at times nearly fell apart, it ended up putting the city of Boston back together again.
When it comes to massive engineering projects, double-checking even the smallest detail is crucial. Getting it wrong can result in devastation. Like this engineering disaster in Wales, where a tiny miscalculation led to a catastrophic failure.
An error in the design drawings brought down a 5,000-ton structure.
A tragedy that shocked an entire community.
The whole bridge line at 45-degree angle straight across the road. Well, it's just unbelievable, you know.
And a deadly disaster that forced an immediate change in the way bridges were built.
Lessons were learned so that hopefully this type of disaster will never happen again.
In southwest Wales lies the quiet port town of Pembroke Dock. Soaring above the town is the imposing Cleddau Bridge. It spans more than 800 meters and connects this peninsula to the rest of the country. But it wasn't always so easy to cross this divide, as retired police officer Phil Lloyd explains.
We couldn't have a better place to live. You've got this glorious waterway which stretches 10 miles down to the open sea and 10 miles further up to the county town. There's only 2 ways to cross the river in the years gone by. You either went by ferry boat, and if you missed the ferry boat, then you had a 28-mile trip right around the main road.
Once a vital Royal Navy dockyard, in the 1960s the military shipped out, and the townsfolk had to look across the water for work.
The ferry could only carry 24 vehicles and around 250 pedestrians per crossing. The construction of a large oil refinery in Milford Haven in the 1960s on the north side of the estuary meant a more practical solution was needed to connect these parts of the country.
So back in the late part of the 60s, it was proposed that a high-level bridge should be built. It was a godsend, really, for the majority of people because, you know, you never had to take this long journey again or go on the ferry boat, especially in rough weather.
Construction of the Cleddau Bridge began in 1969 and was due for completion in 1971, taking a very direct route.
On the southern end, the bridge would cut right through the heart of the village, going between houses and across gardens.
Construction took place simultaneously on both sides of the river and was made up of 7 spans built in self-contained sections that would then be moved or trundled along the partially completed bridge and lowered into place in what's known as a box girder design. This is a tried and tested technique that's both time and cost efficient, as engineer Brendan Walker explains.
This is a cross-section through a box girder bridge. Now, you could build a road by creating lots of layers of solid material all the way through, but engineers realised that a lot of this material in the centre is pretty much unused. So you're using a fraction of the materials, it's very light, and particularly in long-span bridges where you've got wind whipping over the road surface, it's actually a pretty efficient aerodynamic shape.
Box girder bridges have been around since the 1800s. They're a relatively simple but very effective way to build a very strong and sturdy structure. At least that's the theory.
To give the bridge added strength and support to the piers, the design called for using 3/4 inch or 1.9 centimetre thick steel diaphragms.
What these diaphragms do essentially, they sit on top of these piers and they transmit all the force of the traffic directly through the diaphragm and into the piers below. So they do an incredible, important job inside the bridge.
On a warm summer's day in 1970, local residents were going about their business as the Cleddau Bridge was being constructed directly above their heads. Former police officer Phil Lloyd was on his way to work.
On June the 2nd, Tuesday, June the 2nd, 1970, it was extremely hot, one of the hottest days we'd had for years. I went into work into Permanent Dock, which is just over the hill there. And I went into work at 2 o'clock. And I'd only been in work about 20 minutes when the switchboard operator said, "Your mother-in-law's on the phone." So I picked the phone up. She said, "The bridge has come down." Now, mother-in-laws do tend to exaggerate a bit, and I thought that's what she was doing.
But Phil's mother-in-law was stating the facts. At 2:16 p.m., as the 75-metre second section of the southern end was being lifted into place, disaster struck. The entire span buckled and came crashing down through the middle of town. Phil Lloyd was first on the scene.
So myself and my sergeant, Bryn Phillips, we jumped in the van and we came down this road. It comes all the way down here, which leads into the village. And if you can imagine, you come here to find that structure at a 45-degree angle going across the road, which, well, it's just unbelievable, you know. And of course, everybody is out of their houses wondering what is going on.
Despite tons of steel and concrete falling more than 30 metres onto the town, amazingly, it missed both houses and residents. But those working on the bridge weren't so lucky. 5 construction workers were injured, and tragically 4 lost their lives in the disaster.
It was only the fact that they had been careful to avoid building directly over the top of houses that prevented this disaster from being a whole lot worse.
People wanted to know, you know, what had happened, why had it happened?
The construction site was immediately shut down and questions were already being asked. How had a seemingly simple box girder failed so catastrophically? An investigation into the Cleddau Bridge collapse was immediately launched, and it appeared that the fault came down to a miscalculation made on the drawing board. As bridge engineer Kevin Lowther explains.
Here we've got the original design drawings for the bridge, and we can see here on the drawing that it shows a 3/8 thickness of plate, which should have been 3/4, which would have made all the difference.
It might not sound like a lot, but this was crucial to the integrity of the entire structure.
It's a big, big difference from that to that, twice the thickness. And as an engineer, you look at something which is 3/8 of an inch thick and think that isn't very strong, not particularly when it's got to support all of the load that it's got.
Although the difference in width for a structure of this size might seem tiny, we're only talking about 3/8 of an inch or 9 millimeters. It actually made all the difference, and the consequences, as we now know, were catastrophic.
Here we are. This is where the buckling of the bridge happened. Here's the diaphragm, and we can see here that it's 19 mil or 3/4 of an inch thick. This is what the original design asked for.
This seemingly tiny error meant the structure didn't have enough strength to support itself before it was fixed in place, and the whole thing came crashing down.
As the 75-meter span was lowered into place above the town, the diaphragm that was meant to keep it stable simply didn't have the strength to handle the load, causing the support to buckle and collapse.
The further the span stretches out unsupported, the more strength it needs, and this proved to be the fatal flaw in its design.
You know, this tremendous construction, I think it's 5,000 tons altogether going across there. And eventually they found, of course, that on where it bent over Pier 6, there was insufficient strengthening.
One final piece across the river, it was sticking out, it was cantilevered from this final pier. The weight of the bridge wanted to pull this end of the bridge down. And if this support isn't strong enough, this is exactly what happened. The whole thing bent around this pier point here, with the diaphragm inside failing catastrophically.
In 1972, after the 2-year investigation was completed, work restarted, with the Cleddau Bridge finally opening on March the 20th, 1975.
In its first year, nearly 900,000 vehicles used the bridge, and today around 4 million cross it every year. The old ferry would need to make 400 crossings a day just to keep up.
As a result of the disaster, new regulations were established for both the design and construction of all box girder bridges in the UK.
If there is a silver lining, as a result of this disaster, new and much more rigid standards were brought in. So hopefully, a tragedy like the Cleddau will never be repeated.
Nearly 50 years later, the Cleddau Bridge catastrophe remains the last major bridge disaster in the United Kingdom.
This bridge was a much-needed and vital connection to bring these two parts of the country together. This time, it looks like engineers have got it right.
Thankfully, for the last 49 years, it's been as safe as houses.
With big engineering, disaster can strike while the paint is wet and the welds are still warm. But sometimes problems can lie hidden until Mother Nature intervenes. Like this iconic crossing in Wisconsin.
This structure came dangerously close to a catastrophic failure.
The flaw in this bridge almost caused a tragedy.
The bridge was clearly cracking and buckling.
The fear was that the entire structure might come tumbling down.
The city of Milwaukee takes its name from an indigenous American word meaning good, beautiful, and pleasant land. Structural engineering professor Chris Rabel is a local.
One of the great things about Milwaukee is that we have all 4 seasons. We have spring, summer, fall, and winter. Falls are fantastic, beautiful leaves. We have great resources like Lake Michigan.
Over the years, this stunning city has invested in its growth, particularly by developing its infrastructure. One project that was a source of pride was the construction of a bridge over the Milwaukee River, named after one of the city's longest-serving mayors. The Daniel Hohen Memorial Bridge opened in 1977 and has become a key element of a larger transportation system. Local journalist Jim Nelson explains.
The Hohen was part of a system of road projects that created a network of freeways around Milwaukee County.
The Hohen Bridge has become an iconic part of the city's skyline, and that is down to its streamlined design.
It's a bridge of 3 sections. At either side, there is an approach section with what is known as a tied arch bridge at the center.
So the Hohen Bridge is actually 3 bridges in one. It has south approach and north approach, which are just girder span beams, but then the main span that goes over the water is actually a tied arch bridge. So this is an example of a tied arch bridge. The arch, if we didn't have the bottom ties, which are the rubber bands at the bottom, it would want to thrust horizontally at the base of this arch. But because I put these rubber bands in there to hold it in place, that takes the tension and the thrust that wants to go laterally such that it can just sit on my hands. And that's, in essence, what's happening with the middle span of the bridge.
In a tied arch bridge, the arch supports the deck, and the deck stops the arch from pushing outward. The arch and deck balance each other, which reduces the need for supporting abutments, making these bridges easier to build. Engineering professor Farhad Ansari explains the advantages of this design.
So imagine this could be the same analogy like a bow and arrow, where you have a bow and your arrow is applying the force, and it actually transmits all the forces within the structure itself. It doesn't let any forces coming externally. So by having a tied arch, we are increasing the force carrying capacity. We don't need a large abutment. We can prefabricate the arch and bring it by barges and just basically put it in place.
The Hohen Bridge carried traffic safely for decades, until a hidden engineering flaw came to light in a big way. On December the 13th, 2000, a commuter using the Hohen Bridge witnessed something alarming.
A motorist who was driving over the northbound section noticed that something wasn't quite right and called 911.
Drivers noticed that an important segment of the bridge unexpectedly started sagging, and pieces of debris and chunks of concrete and so forth from the bridge fell on Jones Island, and the fear was that the entire structure had been compromised and might come tumbling down.
The bridge was clearly cracking and buckling, and the bridge deck was sagging down by around 4 feet, or over a meter.
This happened in the morning time during the rush time. No one was hurt, but the bridge was immediately shut down due to safety concerns, obviously, and the bridge remained closed for quite a bit of time so they could inspect the bridge and find out what the reason for the collapse was.
It's kind of fortuitous that the portion that failed did so in a relatively limited way, and they caught it in time, because if they hadn't, I mean, many of us who travel the bridge frequently can only imagine the kind of catastrophe that that would have caused if any or all of this bridge had failed.
Over the years, the bridge was forced to carry heavier loads.
The past decade's traffic has increased greatly. There's no doubt that over time, growing traffic had an impact on Hohen Bridge. For me, this is the responsibility of engineers to predict and take into account.
The investigation revealed the problem was not the increased load, but something that lay in the bridge's support beam structure. 2 of the 3 steel girders supporting one section of the southern approach span exhibited a series of full-depth fractures.
The actual failures occurred at the connections of these K bracings, where we had a through the depth crack in these 3 sections, another one right here, and this connection in the middle, and the last one was not as severe, and the cracks didn't go through the whole depth of the web. And actually, because we had sufficient redundancy, if this girder also at this connection had a through the depth crack, the whole section would have failed. However, this redundancy helped the structure. The structure failed, but it didn't collapse.
Analysis of the cracked steel under an electron microscope identified the failure as a brittle fracture.
Brittle fracture is often caused by low temperatures. If the steel temperature is at or below its brittle to ductile transition temperature, then it will be susceptible to brittle fracture.
The ductile to brittle transition temperature is the point at which the strength of a material is significantly altered and often compromised by the surrounding air temperature. For steel, this occurs around 0 degrees centigrade, so when the temperature falls below freezing, which is common in Milwaukee's winter, steel can become brittle.
There's no doubt that stresses from extreme weather contributed to the failure.
But while Mother Nature played a part, it wasn't the only factor. On closer inspection, engineers noticed the cracking had originated from the joints of the bridge's lateral bracing. These connections were deemed too close together and too rigid, leading to a reduction in the bridge's overall fracture resistance. Elements of the bridge that had been installed to give it strength had actually made it weaker. Reopening the crossing would take some major engineering.
The fix was that they demolished, through controlled demolition, several segments of the bridge, brought it down and rebuilt them with a less constraining cross-bracing detail that we see in the bridge on the southbound area today.
The failed section of the bridge had to be completely removed, and a thorough inspection of the remaining parts was conducted.
They did find that they didn't need as much bracing as was put in the original details, so they were able to remove quite a bit of the bracing in the bridge.
The Hohen Bridge is now a lot more flexible and a lot safer. Crucially, it's also better suited to the elements, but this came with a hefty price tag.
The repair budget for this fail was more than $12.4 million.
Despite the high price tag, important lessons were learned.
We were able to change some of the bridge codes such that we could introduce details, especially for the cross bracing, that are not constraining and can work better in this sort of an environment with a steel bridge, so that we don't have this sort of brittle failure with the cracking propagating through the bridge girder all at once.
Understanding failures in engineering projects could ultimately save time, money, and lives by changing design philosophies and helping engineers understand the situations when mistakes and errors can be very costly.
The age-old battle between engineers and Mother Nature isn't always a fair fight. Even though a structure seems indestructible, a simple fail can have catastrophic consequences. Like this Spanish dam that was pushed to its breaking point.
This was a brutal clash between engineering and Mother Nature.
Estamos justo sobre el río Júcar, sobre el devastador.
An engineering disaster with a lasting legacy.
The first 13’s dam only managed to stand up to this region's turbulent weather for 4 years before disaster struck.
The picturesque province of Valencia lies on the southeast coast of sunny Spain.
Spain's Mediterranean coast is known for long, very dry periods, punctuated by brief spells of heavy or torrential rain.
Local journalist Isabel Domingo knows the weather in this region well.
En esta zona, en la comarca de la Ribera y también en la comarca de la Safor, uno de los principales problemas es que cuando llueve, llueve mal, que es la expresión o no sabe llover, que es lo que solemos decir aquí. ¿Por qué? Porque cae una gran cantidad de agua en muy poco tiempo.
All that rain ends up in the Yukar River. It flows from its source more than 1.5 kilometers up in the mountains. And although it may appear tranquil today, heavy rainfall can result in a raging torrent.
With high elevations, water only wants to go in one direction and fast, down.
The engineering solution to this problem? The mighty 13’s dam.
Conocido como el devastador, y que obligó a construir esa presa de Tous para 3 funciones: evitar las riadas, como la de 1982, generar un canal para todo el regadío de la zona y luego también para el consumo humano, porque esta presa de Tous también abastece tanto a la comarca de la Ribera como al área metropolitana de Valencia.
Standing more than 90 meters high, this concrete gravity dam is built to cope with anything the unpredictable region throws at it. José María Benlliure is in charge of dam operations.
La función de la presa es fundamentalmente la laminación de las avenidas. El río Júcar es un río Mediterráneo que puede multiplicar sus caudales por 1000 en las épocas de las grandes avenidas. La función, por lo tanto, fundamental es evitar las inundaciones de las poblaciones y del territorio que hay aguas abajo de esta presa.
The 13’s dam is an epic piece of engineering designed to protect hundreds of thousands of people from dangerous flooding brought on by torrential rains. So whatever happened behind the dam, by regulating the output, the people living downstream should stay safe.
The 13’s dam is the perfect fit for Valencia's unpredictable climate. But this isn't the first dam to stand here. Its predecessor, built in 1978, hid a major engineering fail that was dramatically revealed soon after construction.
The first 13’s dam only managed to stand up to this region's turbulent weather for 4 years before disaster struck.
On October the 20th, 1982, a freak rainstorm hit southern Spain.
In just 24 hours, the region experienced 22 inches or almost 56 centimeters of rain around here. That's the average for an entire year. Water levels rose behind the dam and started to reach dangerous levels.
When the first operator reported for work the next day, water was already approaching the crest of the dam.
Water spilling over the top of the dam or overtopping is one of the worst things that can happen. So nearly all dams have safety release valves called spillways. By opening gates at the top, water can be released in a controlled way.
The dam operator attempted to open the spillways to lower the water level, but they were stuck in place and wouldn't budge.
With the gates stuck shut, the water level continued to rise, and by early evening, water gushed over the crest.
Suddenly, the 13’s dam collapsed. A raging torrent headed downstream, leaving a path of destruction in its wake. An emergency evacuation was called for the 100,000 people living in surrounding towns.
Aquí en Gavarda la Vieja apenas quedan 4 casas, la iglesia. Esta es la vieja iglesia de Gavarda la Vieja. Aquí hay una placa que recuerda aquel hecho fatídico del 20 de octubre de 1982, una placa que nos marca hasta dónde llegó el agua, unos 6-7 metros.
Across the region, tragically, more than 20 people lost their lives. Survivors were left asking, what exactly had gone wrong? After the drastic floods, the 13’s dam lay in waste. Experts immediately began to investigate how this disaster had spiraled out of control. One obvious flaw was in how the spillway gates were operated.
The problem was that the storm knocked out the power, but the spillway gates, the emergency release valve, needed power to open.
There was an emergency generator, but it was located near the base of the dam.
The emergency generator had been swallowed by the flood early that morning, and by the time a replacement made it through the floods, it was too late to do any good.
And yet, the power source alone wasn't to blame for this disaster.
Even if they had opened, an investigation concluded that the spillways had too low a capacity to cope, so the overtopping may still have occurred.
Engineer Don Vicente Fulana, who managed the rebuilding of the dam, explains.
Y al resbalar por el faldón de agua abajo del azud, se lleva las piedras, porque al ser el azud construido con materiales sueltos, no tiene coherencia y por lo tanto se lleva la presa poco a poco.
Once the water breached the dam, disaster was inevitable downstream, as Professor Ignacio Escuder demonstrates.
So what it's useful to see here is how the water behaves. Now we see a very calm water here, but what's going to happen here is going to help you to understand the power of water in order to create destruction. So just have a look to this. Carlos, adelante.
The water pressure is increased to demonstrate what happened as the dam began to overtop.
Let's say we are now at the toe of the dam, and the energy has to be compensated. And it's going to be a very turbulent area, and it's going to be an increase in water level, and the energy for erosion and destruction is going to look like this.
Increasing the water pressure further reveals what happened downstream when the dam had failed completely.
Still, we would see something like this in the river, going downstream the valley. Very high velocities, the need of energy dissipation, high water levels, and all this energy available for erosion and destruction downstream.
With the Tous Dam well beyond repair, future flooding was a constant threat to the region. The only option was to build a new dam.
Para eso, yo exigí que se dotara a la presa de la capacidad de resistir un caudal que fuera el máximo probable en aquel punto.
The new and improved dam was finally completed in 1996, more than 10 years after the disaster. Today, the Tous Dam is safer than ever, making flooding in this region a thing of the past.
El volumen de agua retenido por la presa de Tous moderna es del 20% de esa cifra. De tal manera que el 80% de su capacidad queda esperando una avenida.
Although the area is now safe from flooding, the Tous Dam disaster still resonates with engineers worldwide.
If there is any redemption in this disaster, it is the fact that the Tous Dam failure has improved dam safety procedures and construction techniques.
A tragic fail in Houston that shocked the entire nation.
Several of my neighbors didn't move back. It was just total devastation.
A bridge in Washington state plummets into a river.
This section of the bridge was missing.
can't even believe it.
A television tower that just wasn't built to last.
There was incredible rumbling noise. Something was seriously wrong.
And a building full of priceless relics is completely destroyed.
I saw the ruins of a collapsed building.
With big builds, even the smallest mistake can be a huge disaster. From miscalculations to misunderstandings. Some with deadly consequences. These catastrophes are every engineer's worst nightmare. Wherever they build, engineers always have to consider the elements. Underestimate Mother Nature and the consequences can be disastrous. Like this engineering oversight in Texas that put thousands of lives at risk.
The water sat here for 12 days, destroying the houses.
A catastrophe that ended in real tragedy.
They lost everything.
With destruction of epic proportions.
It's easy to point the finger at Mother Nature, but this was a disaster on a city-wide scale.
Houston, home to 6.5 million people, is America's fourth largest city, situated on the flat, swampy Gulf Coast. The Buffalo Bayou runs right through it.
Houston is world famous for its part in the oil industry and as NASA's mission control. The city's official nickname is Space City. But thanks to many winding waterways that crawl through town, it's also known as Bayou City.
For nearly 3 months of the year, Bayou City basks in 90+ degrees of sunshine. But it also lies right in the path of hurricanes rolling in from the Gulf of Mexico.
In terms of tropical storms, it's only North Carolina and Florida that have suffered more.
As well as high winds, hurricanes bring huge amounts of rain. Houston has a problem, as flood scientist Sam Brady explains.
Houston is one of the most flood-prone cities in the country. It's a low-lying coastal landscape with clay-based soils that drain poorly, and the area is afflicted by 2 types of flooding, rainfall and also tidal flooding from storm surge coming off the Gulf of Mexico when hurricanes hit this area.
With the Buffalo Bayou winding its way through residential areas, this risk is an ever-present danger.
Houston's problem is compounded by its elevation. The city is barely above sea level, and there's only around a 4-foot or just over a meter difference between the highest and lowest points of downtown. This means when a storm hits, it's just like a flat roof. The water has nowhere to go.
The city has been devastated by floods before. In 1929 and 1935, Houston suffered such horrific damage that Congress responded by authorizing the construction of the Addicks and Barker dams in 1940 as part of a flood defense system along the Buffalo Bayou. Their primary goal was to protect the center of the city around 30 kilometers downstream. Unlike traditional dams that are positioned between a natural change in elevation, the Addicks and Barker dams were built on gently sloping ground along the line of levees, at a low level and dug into the ground. In a storm, they would collect and then slowly release water into the bayou through a series of controlled spillways. Originally surrounded by prairie land, it was anticipated that as the city expanded, a third dam could be constructed nearby if needed. But in recent decades, that land set aside for this third dam was repurposed for housing developments. In fact, the area is one of Houston's most sought-after suburbs.
When you're developing an urban area anywhere, understanding the hydrology of the landscape is key. But when you're talking about a city the size of Houston, in an area known for heavy rain and tropical storms, engineers and city planners really have their work cut out.
With flooding inevitable, Houston planners built drainage channels, sewers, and off-road ditches in case of emergency to hold or move water away from residential areas.
The idea of all these defensive measures was to make this city storm-proof.
On August the 25th, 2017, a Category 4 storm was heading towards Houston. Its name? Hurricane Harvey. It packed a double punch, with winds of over 200 kilometers an hour and torrential downpours.
Hurricane Harvey was global news, and wow, it was a disaster. Around 9 trillion gallons of rain fell into Houston in just 2 days.
The storm stalled over Houston and dumped around 1¼ meters of rain in just 4 days. The National Guard was called into action as thousands of residents fled their homes. Local attorney Vuk Vuzinovich remembers it well.
The streets were rivers. You had families and their kids and pets in canoes, paddling out of here, getting rescued by boats, getting pulled off the rooftops by firemen, by helicopters. It was crazy.
As both dams reached their breaking points, the unprecedented decision was made to open the spillways. This released a torrent of floodwater downstream at a rate of more than 180,000 liters per second from each reservoir. And it was heading directly toward these heavily populated neighborhoods.
This was catch-22 for the engineers. Release the water and businesses and homes would be flooded. Don't release the water and the reservoirs overflow, destroying the dams, making things much worse.
Local journalist Alex Stuckey explains.
Reservoirs were built to hold a lot of water, especially during heavy rains and flooding. But Hurricane Harvey dropped so much water, they just couldn't contain them and they had to be released. At certain points, they were releasing it at almost the rate of Niagara Falls.
Residential areas were already struggling to protect their homes and themselves from the storm waters. So when the overflow from the dams poured downstream, they were completely overwhelmed.
All these houses were underwater during Harvey. The water sat here for 8 to 10 to 12 days, destroying the houses. People had to leave their houses for months and months, over a year in some cases.
Logan Reed's family had just bought a house in one of the residential areas most affected.
My family, we just got our dream house. It wasn't even the rainwaters that flooded us. It was the dam. It was just totally devastating to our family. We lost everything from childhood pictures, books. I mean, those are just memories that we can never get back.
Logan caught the full extent of the devastation on camera.
Well, guys, today's Wednesday. I haven't been to my house since Sunday, and I'm coming up to my house now to see what kind of damage or whatever kind of flooding there is. But as I was coming through here, the devastation was obvious. This right here is our living room. Here's our couches right here. They just got picked up when the rainwaters came in. You can see roughly how high the water got. We did have to cut maybe 2 inches above the water line, but as you can see, it's just crazy how high the water really got in here. Here's my mom's room, actually. Her bed is absolutely ruined. Her desk got picked up. Walls, ceiling caved in. And this right here is the bathroom. It just looks like a total mess. We were lucky that the water didn't get actually up to our second story, but still, we got almost 9 feet of water in here. This is crazy. Yeah, I knew it was gonna be bad. This is the first flood I've ever gone through, and this is really devastating.
By the time the storm had passed, Hurricane Harvey had damaged or destroyed more than 200,000 homes. Even more tragically, it also claimed the lives of at least 88 people. Now the city was forced to ask the question, how could they keep this from ever happening again? In a city known for weathering tropical storms and flooding, Why was the devastation so dramatic?
Any urban development reduces the natural drainage of the land, but here, building so many homes so close to the dams may have compounded the problem.
Vegetation and soil naturally help soak up water like a sponge. But as more and more of the area was concreted over, the ground lost its capacity to absorb, putting extra pressure on the dams. And Harvey dumped more water in the dams than they were ever designed to handle. Alex Stuckey explains.
There were tons of properties that had made it all the way through Hurricane Harvey without getting any water, no flooding at all. And then once the rain had stopped, they woke up and found water in their house.
Although the network of canals and reservoirs was in place, engineers had simply underestimated the potential scale of the problem. They just weren't prepared for a storm of the magnitude of Harvey.
One study claimed that the huge amount of development in the metro area increased the chances of extreme flooding by as much as 21 times.
But how far developers built into the floodplains may not have been the only problem. How high up they went also created challenges.
A study by researchers from 2 major universities suggested that Houston's skyline might have added to the intensity and the amount of rainfall that fell in the city. Far-fetched as it sounds, the theory is that the storm literally got snagged or caught on the downtown skyscrapers, and the rain just poured and poured over the city.
While the study is not conclusive, if this is found to be true, engineers and developers really need to rethink not just where they build, but how high they build in hurricane hotspots.
While no city can absorb more than a meter of rain in such a short amount of time, it seems flood defenses put in place over 70 years ago could not keep up with the needs of an ever-expanding and demanding city.
A third dam might have proved vital in preventing this catastrophe, but there simply wasn't the capacity to build one on this site anymore.
In the wake of Hurricane Harvey, officials are strengthening flood controls in and around the Addicks and Barker reservoirs. And any new development within specific areas will have to build detention ponds, which hold water and slowly discharge it into nearby rivers and streams. Flood scientist Sam Brady explains.
The federal government spent about $500 million in engineering solutions to widen the bayou, increase its ability to channel, hold, and remove water. But an alternative strategy can be 2 things. Vertical, where we're elevating structures high enough so that even when it does flood, the structures aren't impacted, or avoidance. Before we enter an area with construction or impervious surface, we find the most vulnerable areas and we avoid them.
Sometimes the safest option is to accept that certain places are just not for building on in the first place.
When it comes to engineering, sometimes the tiniest margins of error are enough to cause catastrophic consequences. Like this next disaster in Washington state that literally divided 2 nations.
This was a major catastrophe that destroyed a vital link between the US and Canada.
A devastating collapse that left locals reeling.
We couldn't understand how anybody could survive that fall, and it just looked like people had died.
An engineering disaster that led officials to immediately rewrite the rules.
This one disaster made authorities rethink the way that hundreds of bridges across the US were built.
In the Pacific Northwest lies the winding Skagit River, which flows 240 kilometers from British Columbia into Washington state. In 1955, the Skagit Bridge was built over the American stretch of the river, creating a vital link between the 2 countries. Local resident Alex Goines explains how important this crossing is.
This is the lifeblood of Seattle, Vancouver, Portland. This is the one major highway that goes north and south.
The bridge crosses the river between Mount Vernon and Burlington in Washington state on Interstate 5 and is the main transportation route between Seattle and Vancouver.
Carrying around 70,000 vehicles a day, like most crossings of its time, the main span is a truss design stretching 195 meters across the river. Structural engineer Stephen Ressler explains.
This was a truss bridge, a simple truss bridge consisting of two trusses. Those two parallel trusses are then held together by systems of secondary members. Down below, the members that connect the two trusses together are called floor beams. That's what actually holds the deck of the bridge up and supports the traffic loads that are applied to the bridge.
Despite not bearing the brunt of the load, the secondary bracing across the top helps to hold the bridge in place.
There was a particularly important characteristic of these secondary bracing members, and that is, as you look at the bridge from the perspective of traffic, you would see that the horizontal element running from truss to truss had a curve.
The curved design of the bridge meant the overhead clearance ranged from 5 meters 46 centimeters in the inside lane to just 4 meters 50 on the outside, a difference of nearly 1 meter.
Most of the haulage trucks towing large trailers across the US are up to 14 feet or just over 4 meters tall. But the load they're carrying can be much higher. So they always approach anything with a height restriction, like tunnels or bridges, with extreme caution.
The standard procedure with any oversized load was to have a pilot driver take the lead. A pilot driver uses a vertical pole set around 12 centimeters above the height of the semi's trailer, so that if the pilot pole strikes the top of the truss, the semi and its heavy cargo trailer have time to stop. On Thursday, May the 23rd, 2013, a semi and its trailer were on their way from Alberta, Canada, to Vancouver, heading for the Skagit Bridge. The truck and its load had a vertical height of 4 meters 80 centimeters, and the pole had been set to around 4 meters 90. Lower than the inside lane, but more than half a meter higher than the outside.
The semi did have just enough clearance to drive safely across the bridge,
as long as it didn't deviate from the inside lane. At 7:05 p.m., the truck, traveling at over 100 kilometers an hour, hit the overhead braces. Alex Goines was driving home at the time.
We got down into Mount Vernon and we were stopped on the freeway. And that's when we were told that a section of the bridge had fallen away. So this is where I parked and we scrambled up this berm so we could get a better view of the bridge. At this point, we could see everyone was out of their cars and the rescue craft were down there, and we could totally see this section here of the bridge was missing. And all we see, the bridge is collapsed, and it's just devastation is everywhere. We can't even believe it.
An entire 48-meter span collapsed into the river below. But it wasn't just the bridge that had fallen. 2 vehicles traveling south also went down with the bridge.
The one truck that we saw was just destroyed. I mean, that's the only word I could use to describe it. We couldn't understand how anybody could survive that fall. We didn't think anybody had lived through that. It just looked like people had died.
Incredibly, all 3 occupants survived. So why had a tractor-trailer striking a small section at the top of an otherwise stable truss bridge caused such a catastrophic failure? In the aftermath of the Skagit Bridge disaster, investigators began to examine what had gone wrong. It turned out the truck was on a collision course from the moment it entered the bridge. Attorney Chris Davis explains.
The pilot driver was in the far right-hand lane. Unfortunately, the pilot car driver was talking on her cell phone and did not communicate anything to the Canadian truck driver behind her. He stayed in the right-hand lane. The difference between the distance of the center clearance versus the right-hand clearance is about 2.5 to 3 feet.
The truck driver stayed in the lower outside lane where there simply wasn't enough clearance and hit the overhead braces. But why did dislodging the overhead brace, which is non-load bearing, cause the entire bridge section to collapse?
So you might be wondering why the destruction of secondary braces could result in the collapse of the entire structural system. After all, the main load-carrying elements of this bridge are the two trusses, and neither of the two trusses were damaged by the truck when it struck that overhead bracing system. Well, to understand that, let's first look at my model, and I'm going to take some heavy weights and hang it from the center, and you'll see that it carries load quite acceptably with very minimum deformation. Now I'm going to do what the truck did. I'm going to start removing these secondary braces that tie together the top cords of the two main trusses. As you can see, the structure itself is still intact. The main trusses are still in the proper alignment. But now when I take the same weight and apply it at the same point on this bridge, you'll notice that the top cords of the bridge buckle sideways. And as a consequence, the entire structure collapsed.
In modern engineering, structures are frequently designed to include so-called redundant components for safety. But older existing structures without redundancy are called fracture critical, meaning that if one single part fails, the whole structure can potentially collapse.
Even a small crack in just one essential part can trigger a chain reaction, leading to a total failure of the entire structure.
The Skagit Bridge was a perfect example of this unfortunate domino effect.
Skagit River Bridge only had two main load-carrying elements, the two trusses, so the loss of any one element in any one truss resulted in a total collapse.
The collapse of the bridge caused chaos across the entire region.
When this bridge went down, it really stopped commerce and business and commuting. I mean, it impacted everyone.
And it turns out the Skagit Bridge wasn't the only fracture-critical bridge in Washington. Some estimates suggested that there were between 300 and 400 in the state alone, and a mind-blowing 20,000 across the entire country. In the wake of the disaster, Skagit Bridge was strengthened and retrofitted with reinforced steel, while the curved braces were replaced with a uniform vertical clearance.
One of the recommendations following the disaster was that all future bridges should be constructed so that vertical clearance is uniform across their entire width.
This time around 5.5 meters high across the entire bridge. The Skagit Bridge reopened to traffic less than a month after the collapse on June 19, 2013. Across the country, the goal is to make fracture-critical bridges a thing of the past.
Today, we try to build structural systems such that they are redundant, such that the loss of one main load-carrying element will not result in the progressive collapse of the entire structural system. That category is, for all intents and purposes, obsolete in modern engineering practice for precisely this reason.
While there's been some effort to retrofit the bridges up to current engineering standards, there's still a long way to go. It's a mammoth task, but at least it's a step in the right direction.
In the desire to make all bridges truck-proof, some states have installed warning signs to reduce the number of high-level strikes. And some are also using the latest laser technology to let drivers know whether they can safely clear the bridge.
What was astonishing to me was that 4 months later, we had the permanent bridge replacement section in. I mean, that just seems like a really quick amount of time to get a permanent structure back in.
It looks like lessons definitely have been learned. So if a 40-ton truck ever does strike again, this time the Skagit River Bridge is going nowhere.
Just a couple of inches higher, and this whole disaster could have been averted.
In big engineering, when you're pushing the boundaries, it's sometimes difficult to know what you're pushing against. Get the calculations wrong and the results can be catastrophic. like this engineering fail in the UK, which exposed a hidden weakness on a supersized structure.
A tower almost as tall as the Empire State came crashing down in seconds.
A disaster that caught everyone by surprise.
Incredible rumbling noise led me to the fact that something was seriously wrong.
And a catastrophe that literally no one saw coming. Just outside the tiny and picturesque village of Emley in northern England lies one of the most important structures in all of the UK. The Emley Moor Tower, which beams TV to around 4.5 million people across the north, covering an area of over 25,000 square kilometres.
There have been transmission towers at Emley Moor since the earliest days of television. The location is ideal. It's remote, so there's little chance of interference from other radio sources, and it's high, so the transmissions have an unobstructed path, so a clear line of sight to as wide an area as possible.
But this isn't the first tower on this site. The original tower was built in 1956 and stood at 135 metres tall. By the 1960s, as the number of TV sets across the country skyrocketed, and to prepare for the broadcasting of colour images, a more powerful transmitter was needed. Alan Redgrove worked as a transmission tower engineer for 33 years.
It was really sort of an innovation to build tall masts out of cylinders, and you can see that the mast is constructed out of a cylinder which is 9 foot diameter, and these cylinders are all joined together, bolted together.
Built in 1964 and towering above the landscape at 385 metres, the Emley Moor Tower was the tallest structure in the entire UK.
It was taller than the Eiffel Tower. In fact, it reached as high as the roof of the Empire State Building.
To pull off this titanic television tower, engineers used curved steel segments to form a 275-metre long, 3-metre wide tubular tower, with a 107-metre steel lattice transmitter mast on top. The steel sections were bolted together, and the whole structure stabilised using steel cables tied to the tower and sunk deep into the ground, known as a steel guide mast.
A guide mast is a tall, thin structure that depends on wires or cables for support. So while it has the strength to support its own weight, because it's so tall, the cables are essential to keep it stable, especially in strong winds.
The only problem was, standing in a remote, exposed location leaves the tower at the mercy of the elements.
The high location is great for transmitting, but it's also exposed to extreme conditions. The tower was in Yorkshire, which is in the north of England, which I know can experience some very cold and windy weather.
Right from the start, large blocks of ice would form on the support cables, putting them under enormous extra strain.
The ice was forming on the guy wires from about 1,000 foot up, and it was probably around about that sort of diameter.
During winter, ice falling from the tower was so common that warning lights flashed when falling ice was a hazard, and nearby roads were frequently closed. But it wasn't just ice that was a problem. As structural engineer Dr. Lee Cunningham explains.
With any tall structure, the main issue from an engineering point of view is the wind and the wind force. A building presenting an area to the wind is trying to move that building and trying to overturn that structure. The greater the area that you present to the wind, the greater the wind force.
On the 19th of March 1969, Alan Grove was on his way to work at Emley Moor.
It was a very cold, wintry day. This road across was closed off because of ice was falling across it, and there was a danger to life and limb. At 1 minute past 5, and I was in the basement checking things over, when a incredible rumbling noise led me to the fact that something was seriously wrong.
Alan rushed outside to discover that the entire 385-meter steel tower had come crashing to the ground.
We could see the structure of the mast laid across the car park. Bits of the mast ended up all over the place. And the biggest thing to come out of it all, of course, was that the whole of Yorkshire had no TV.
Working in a basement just a few feet away from the tower, Alan and his team were lucky to escape unharmed. Instead of transmitting the news, the Emily Moore Tower was now making it. The 385-meter tall tower had dramatically collapsed. But had extreme weather and high winds brought the UK's tallest structure crashing down to Earth? Or was faulty engineering to blame? Initially, it was thought that the collapse was simply down to a combination of strong winds and a thick coating of ice. But structural engineers like Dr. Lee Cunningham believe the tower's design may have left it dangerously exposed.
So my pen is representing a circular tower, and we have the wind load coming in. As the wind hits the tower, it tries to move around the tower, and as it moves around the tower, we get circular motion of the wind. In other words, vortices. And what those circular motions of the vortices do is cause the tower to vibrate at 90 degrees to the wind load.
Like a flagpole or a streetlight on a windy day, as the wind blows across the tower, it creates swirling flows of wind alternately on either side, called vortices. The taller the building, the more vortices form around it. And the more vortices that are created, the more likely the building or structure is to vibrate. These sustained vibrations are known as vortex shedding.
Vortex shedding can cause a tall building to shake violently. If it's bad enough, it might damage or in extreme cases bring the whole structure crashing down.
A study found that in very tall buildings, the effects of vortex shedding can do more damage than earthquakes. After the catastrophic failure of Emily Moore, engineers realized that steel transmitter towers all over the country were at risk.
The collapse of the 1969 Emily Moore mast was a bit of a watershed moment in structural engineering in terms of our understanding of the dynamic behaviour of these types of structures and also their vulnerability. Following the collapse, a number of similar structures were retrofitted with damping devices and additional mass.
Damping devices reduce potentially dangerous vibrations, like the ones that proved fatal for Emily Moore, and add extra weight for stability.
Two almost identical towers were modified by hanging 150 tons of steel chains from each tower, and both are still standing today. So in hindsight, this fix just might have prevented Emily Moore's collapse.
While temporary transmitters began to restore normal service for TV viewers, a more permanent solution was needed for the tower itself.
Engineers learnt the lesson from the first tower. Instead of steel and guy lines, they opted for a reinforced concrete tower with a much wider base and thicker walls. This gave it much greater stability in high winds.
Construction began in 1969, and this time, instead of 3 meters, the new tower is now 24 meters wide at its base, tapering to around 6.5 meters at the top. The foundations go down 6 meters into the ground, and the whole structure weighs over 11,000 tons, with an ability to withstand winds of up to 240 kilometers, greater than a Category 4 hurricane.
The tower as it is today is about 85% in reinforced concrete. It's essentially a reinforced concrete tube with a much wider base, and in doing so, we have created a structure with much less vulnerability to the phenomenon of vortex shedding.
The new and improved Emily Moore Tower resumed service on April the 21st, 1971, and nearly 50 years later, it's still going strong.
The new transmitter at Emily Moore isn't going anywhere and should keep the viewing public happy for years to come.
Sometimes in big construction, engineers must not only focus on their own structure, but everything else around them. Get it wrong, and the results can be catastrophic. Like this construction calamity in southern Germany, and a subway that nearly destroyed centuries of history.
This disaster left a massive scar on the city.
Destruction on an epic scale that struck without warning.
This catastrophe happened in the blink of an eye.
Something very big happened. I was astonished, frightened.
And a fatal flaw that could potentially have been avoided.
The earth was sucked into this subway building, and that's why it collapsed.
Cologne in Western Germany has a rich history. The city thrived in the Middle Ages, and its famous cathedral is still one of the country's most visited landmarks. Since the 1400s, Cologne has been home to some of Europe's most valuable historic documents, including the writings of world leaders and even orders passed down from Napoleon Bonaparte.
This collection was unique. The documents were irreplaceable. They provided a window not just into Cologne's history, but the whole of Europe's past.
In 1971, to better preserve the priceless collection, a new archive building was constructed in the center of town. Historian and journalist Gunther Otten explains.
This was the state of the art. It was a very modern building at that time. And it had a 6-story building, 30 kilometers of space, which was huge and should have lasted for centuries.
The archive building contained around 65,000 documents and around 500,000 images, with the oldest items dating from the 10th century. In 2004, work began on a new subway system, which would include a station right beside the existing archive building. However, building a brand new underground transportation network in such an ancient city was never going to be easy.
Cologne doesn't sit on a firm geological foundation. In fact, the city was built on sand and pebble. So if you're tunneling below the city's surface, you need a solid construction technique.
The tried and true technique chosen for this huge project is known as a diaphragm wall construction. 2 parallel trenches are dug and filled with reinforced concrete to form walls. The earth in between is excavated. A concrete floor and roof are then added, forming a tunnel.
When the concrete sets, you have a solid watertight wall with no joints exactly where you want it.
The 90-centimeter thick, reinforced concrete diaphragm walls hold back the earth, allowing construction to begin.
One problem with diaphragm walls is that if anything is left in the way when you pour your concrete, the wall doesn't form a perfect seal. When it sets, any cracks can let water and mud seep into your tunnel, and the ground around it subsides.
On the 3rd of March 2009, 5 years into construction, work was continuing directly underneath the city archive. Freelance photographer Joe Schwartz was in the area.
I was having lunch, and suddenly I saw dust outside of the window. And I see a big wall of dust. The sun was almost hidden.
Joe's first photos capture the disaster minutes after the collapse.
Something very big happened. I was astonished, frightened. Then I stopped thinking, and I started to shoot.
Emergency services were quick to respond. Former Chief Fire Officer Stefan Neuhoff remembers that day well.
The nearest fire station arrived after 2 minutes, I think, they arrived at the scene. And they gave the first information from the scene that the building really has collapsed.
Cologne's archive building was reduced to rubble, and Joe was just meters from the scene.
And I arrived over there, can you see, to the place. I saw the ruins of a collapsed building. I was worrying about the students at this junior high school. At this time, 2 o'clock around, there are a lot of students. There will be dead people. I made a call to my newspaper and said, big thing happened, big thing. So about 1 minute without fire brigade, shooting. And then fire brigade came, they started to block the area, to block it, and to throw us back to the place. Police, ambulance, fire brigades, they arrived en masse, and all were confused and trying to find out really what was happening.
When we arrived, the earth was still moving, and we said every people have to leave this area, and then we could start to work.
Not only had the archive building disappeared into the ground, 2 neighboring apartment buildings were also reduced to rubble.
I worked 34 years for the Cologne Fire Brigade. 25 years I was the chief of the Cologne Fire Brigade, and I'm sure it was the greatest disaster what we saw. We didn't know the reason why this had happened.
Luckily, the archive building was evacuated in time, but 2 people in the adjoining apartments weren't so fortunate. Tragically, both were killed in the collapse. In the days that followed, rescuers worked around the clock to salvage the priceless relics from the rubble, fitting a temporary roof to prevent the precious archive from being destroyed by bad weather. As the crews dug through the wreckage, the people of Cologne demanded to know how this had happened. Investigations pointed to the subway beneath the archive building, and attention turned to the diaphragm wall. It turns out that on the day of the disaster, construction workers underground noticed water flooding into the tunnel. They quickly alerted their management, and the archive building above was evacuated. Shortly afterwards, an underground landslide caused the dramatic collapse.
The earth underneath the archive building was sucked into this subway building, and that's why it collapsed.
In September 2005, during construction, workers hit a large block of natural stone beneath the city. Rather than remove it, it was decided to build the walls around it. Some believed that this stone had compromised the diaphragm wall.
What they found out is that there was a mistake in building this concrete wall. So there was a stone left, and under this stone there wasn't concrete where there should have been.
At a district court in Cologne, it was ruled that the collapse was caused by an error in the construction of the diaphragm wall, and that this error was solely to blame. Most of the archive was painstakingly recovered, and as with all engineering fails, it cost not only time but money too, with the bill for this one coming in at around €1 billion. The archive was known as the Memory of Cologne, and this is one engineering catastrophe that its citizens will never forget.
It's a reminder that in construction and engineering, every detail counts.
A tragic collapse strikes a Florida landmark.
A mouth just dropped open. 1,200 foot, the bridge is gone.
In Germany, a groundbreaking design crashes to Earth.
And all of a sudden, a big crash happened, and the roof collapsed towards the street.
A troubled bridge in the capital of Denmark.
The engineering of it simply didn't work.
And a California dam threatens an epic flood.
Water was shooting out in multiple directions, so the whole face of the dam just looked like white water.
With big builds, even the smallest mistake can be a huge disaster. From miscalculations to misunderstandings, some with deadly consequences. These catastrophes are every engineer's worst nightmare. Gravity is one of the biggest enemies for engineers. And the larger the project, the greater the threat. Like this deadly catastrophe in Florida that no one saw coming.
This disaster was a reminder that you have to prepare for any eventuality.
A fatal flaw with devastating consequences.
You see wreckage hanging, you can see cars on the bridge.
A tragedy that left an entire community in shock.
The outside world had finally reached Tampa Bay. This was a monumental catastrophe.
And forced a change in the rules.
Lessons were learned so that a tragedy like this should never happen again.
Florida's Sunshine Skyway Bridge has stood as a proud reminder of the state's engineering prowess for more than 30 years. The bridge is the third and most successful span over these waters and marks the entrance to a 1,000 square kilometer sea inlet, Tampa Bay.
Tampa Bay is a large natural harbor connecting the west coast of Florida to the Gulf of Mexico. It's one of the longest shipping channels in the world and one of the most treacherous.
Not only is the channel busy and narrow, but bad weather can appear out of nowhere.
Florida is known as the Sunshine State, but it also experiences some of the worst storms in the U.S. In fact, 40% of all hurricanes hit the Florida coastline.
Something locals like author and reporter Bill DeYoung are all too aware of.
Well, it's a beautiful day out here on Tampa Bay. It's like this, I would say, 360 days a year. And what happens on the other 4 or 5 days of the year that it's not like this is weather comes in off the Gulf of Mexico. These squalls build up on the Gulf of Mexico.
That dramatic weather is the exact reason this third bridge was built. Its predecessors had long hidden a fatal flaw. The first Skyway Bridge was built in the 1950s, with a twin structure joining it in 1970. Both had long causeways leading to dramatic spans over the bay.
The first Sunshine Skyway Bridge went up in 1954 to cross 15 miles of South Tampa Bay. The overwater part of the bridge, the really scary part, is just over 4 miles. It did feel like you were going up into the clouds. It was so high.
To allow huge ships to pass beneath, the ski ramp approaches raised traffic 45 meters above the water onto the central span. Like many bridges of their time, the span consisted of a tried-and-true design known as a cantilever truss. Structurally, Boston's Tobin Bridge works the same way as the original Skyway. Engineer David Beck explains.
Both of those bridges were cantilevered truss bridges to create one big wide span. You have 3 main components: the cantilever section to the right, to the left, and then you have the center span which is coming up and supported off the cantilever trusses.
The 4 legs on a cantilever bridge, known as piers, provide support to the 2 bridge arms and the road above as they extend across the span. These 4 piers each serve a crucial role in balancing out the massive forces at play within the structure.
If you take a look over here, you can see the pier, that's the main pier onto it. It's got 2 columns coming up and then a cross brace just to keep the pier, giving it lateral resistance onto it. But it's basically those columns that are taking the load of the bridge and transferring it down to the bridge pier foundation.
From 1971, the twin skyway bridges of Tampa towered over the water, carrying thousands of cars a day across the busy shipping lane. Although no one realized it, the bridge had a fundamental weakness. On the morning of May the 9th, 1980, the MV Summit Venture, a 185-meter-long freighter, was heading from the Gulf of Mexico to port in Tampa Bay. Using a simulator, Captain Ted Morley is accurately replicating the treacherous conditions the pilot was facing.
So we're seeing almost exactly the view that the pilot would have seen as he approached Sunshine Skyway Bridge. Tampa Bay is notoriously difficult to navigate because it's shallow, a lot of shallow areas around it. The channel itself is a deep cut, but the bay itself is very shallow. So you get a lot of tidal effect, a lot of current effect, and you also have a lot of weather coming off with rain, sleet.
Like all ships heading into Tampa Bay, the Summit Venture needed to make a 13-degree turn to navigate safely between the Sunshine Skyway's central span. This might not sound like much, but this ship is the length of 2 football fields.
Even on a clear day, navigating the channel isn't straightforward. But as it approached the bridge, the ship encountered an intense and localized storm known as a microburst.
When Summit Venture was coming in on the 9th of May of 1980, this black cloud literally followed it in from the Gulf, just hung over its head. It's what they call a macroburst storm. It's a little intense storm inside a squall.
So right now, as the rain intensifies, we're actually seeing the echo of the rain on the radar. And right now, it's still light. The rain is not super intense yet, but you can see how the rain itself is creating these echoes and this noise and clutter on the radar. That will actually get worse and worse. And modern radars have a better way of handling that than the older ones do, but that can actually obscure the entire view of the radar, rendering it absolutely useless.
The storm reduced visibility to 0 and was strong enough to blow the 20,000-ton freighter off course.
This pilot was effectively steering blind, and he had no idea he was on a catastrophic collision course.
Remember, this is 1980. There was no GPS yet. You have shipboard radar in case your visibility goes out. Well, the radar stops working, too. He's 7/10 of a mile from this bridge. It takes a mile for these ships to stop.
As soon as he realized the danger, the pilot dropped anchor and put the ship's engines into full reverse. But it was already too late. The Summit Venture rammed the southernmost pier of the bridge.
Much like, say, the Kennedy assassination or 9/11, people remembered exactly where they were when they heard about it. This is Tampa Bay's version of those horrible, horrific events.
At the time of the accident, Michael Rosselet was a volunteer rescue diver when the call came in.
So I got the pager call at about 7:30 in the morning, and we were told that a boat had hit the Skyway Bridge. So we were expecting, I think, just your average boat, maybe trawl or fishing boat, had run up against the bridge. We made that turn down toward the Skyway, and it's just gone. I mean, it's 1,200 foot, 1,500 foot of bridge is gone. Our mouths just dropped open. We thought, wow, this is much more than we were expecting.
With this vital support gone, a 400-meter section of the deck twisted and fell 45 meters into the bay below.
Several drivers were able to stop their vehicles in time before dropping into the void. One skidded to a stop barely 14 inches, about 35 centimeters from the edge.
Others hadn't been so lucky. 6 cars, a pickup truck, and a Greyhound bus had already fallen into the water. Michael and the rescue team quickly realized that the odds of any survivors were slim.
We see wreckage hanging, we could see cars on the bridge. But at this point, we just realized we had to kind of go into action. Saw the bus in the water. At that point, it was pretty obvious that it wasn't rescue, it was recovery.
In all, 35 people died in the disaster, with only one very lucky survivor.
Incredibly, one man survived when his pickup bounced off the deck of the ship below, breaking his fall into the bay. Those tiny margins were the difference between life and death.
This thing was sort of like the outside world had finally reached Tampa Bay. This was a monumental catastrophe that nobody could believe had happened because everyone drove over that bridge all the time.
So, was this just a tragic accident, or could more have been done to avert one of the worst catastrophes in Tampa's history? The official report into the disaster concluded that a complex series of factors, from the severe weather to human error, caused the accident. But, crucially, it also highlighted a flaw in the bridge: the lack of protection on the supporting piers against ship impact. And it turns out the Summit venture hit the worst possible pier. Engineer David Beck explains.
Hitting one pier resulted in the collapse of actually 3 spans of the bridge. The reason why you had 3 spans collapsing on the Sunshine Skyway Bridge, the center piers were pretty hefty. The back pier, since it was never designed to take on a collision with a ship, it had smaller piers into it, and when that back pier went out, the whole cantilever section of the bridge fell into it. When you lost the cantilever section on the one side, then your center span totally collapsed.
With the potential for such catastrophic consequences, not protecting the bridge itself would seem short-sighted, especially given this was not the first collision here.
Turns out the old Skyway Bridge had been hit 13 times by vessels before the Summit venture crash. So it seems incredible that at the time of the collision, there were no requirements or standards for protecting bridge piers against ship impacts.
The bridge had survived the previous incidents with relatively minor damage. But a ship this large, striking the end pier, delivered the fatal blow.
I think it was an accident waiting to happen. It never occurred to them to protect this bridge from ship traffic. We were taking our lives into our hands every day by crossing this thing. It was a miracle it didn't happen before.
With the risk of another collision looming, the decision was made to replace the old bridges with a safer, more modern design.
Historically, bridge engineers have focused on making big exposed bridges safe from the forces of nature: earthquakes, hurricanes, tornadoes. But ship collision is a much greater threat than any natural disaster. So for the new bridge, they brought in one of the world's leading experts on bridge protection.
With safety at the forefront, the new Sunshine Skyway replaced the cantilever with a more robust cable stay bridge. To reduce the risk of collision, the bridge was positioned away from the treacherous 13-degree bend in the shipping lane.
The new bridge has been moved to facilitate an easier approach for the ships, so the ships can line up better to the bridge and be square to it before they proceed through it, and it gives them a little more lead time.
But it's what's going on beneath the deck that's turned this bridge into one of the safest in the world. An impact protection system made up of concrete islands known as dolphins.
Dolphins are usually made from steel or reinforced concrete. You have a number of poles driven into the bedrock, rising above the surface of the water and filled or connected to create large concrete islands. In effect, they're like bumpers or fenders for bridges.
The new Sunshine Skyway has 4 large dolphins, 60 feet or 18 meters in diameter, to protect the 2 main piers, and 32 smaller dolphins protecting the smaller piers, stretching beyond the edges of the shipping lane.
Each set of dolphins combined can withstand the impact of an 87,000-ton ship. around 4 times the size of the Summit venture. And crucially, they're designed to stop a ship, not sink it.
As you see now, we have all these large dolphins or circular concrete abutments to deflect any traffic that would hit any of the spans. And I can't imagine anything hitting the Skyway now and not being deflected first.
In hindsight, it seems like an incredibly simple solution. If you want to stop ships from hitting the bridge, put something in their way. And they didn't stop there. 2 small rock islands surround the 2 main piers, so if a ship somehow manages to get past the dolphins, it will be grounded before it can do any damage.
There's also a guidance system for ships passing under the bridge, an early warning system for motorists, and sensors to detect even minor collisions. And the central span is now 50% wider, with a clearance of over 55 meters.
When designing a new bridge, the investigation's findings were clearly taken on board, and now the new Sunshine Skyway is one of the most well-protected bridges in the world.
Rising out of Tampa Bay in 1987, this stunning new design was a perfect addition to the Sunshine State coastline. With groundbreaking architecture, designers aim to make an impression on the outside world. But they can't overlook what's on the inside. Like this Congress Hall in Germany that suffered an epic failure.
With this build, they pushed the boundaries way too far.
A world-famous building destroyed in seconds.
Half of the whole roof was completely collapsed.
In 1980, Berlin is a city divided by the Cold War. Capitalism rules the West, communism the East. And a powerful icon of democracy is about to fall. In 1957, the Eisenhower administration offered to build a new cultural center in West Berlin. It was to be called the Congress Hall. Ann Meyer has worked here for over a decade.
The Americans wanted it to be seen as a bastion of the free speech, and it was their education program to teach Germans after World War II again free speech.
Unsurprisingly, the location was to be a stone's throw from the Berlin Wall.
It was a strategic decision to have a building that is as high as the Reichstag, that could be seen by the people from the West as well as from the East.
The building itself was a cultural statement. Its shape was unique and much admired.
For those entering the building, it must have felt like walking into the future. Inside there was a concert hall, galleries, a cafe. Conversation, culture, and ideas just circulated within its walls.
Berliners adored the building from the beginning onwards, and Berliners have the tendency to make nicknames for buildings, and they called this building Schwangere Auster, translates the pregnant oyster.
The architect, wanting to ensure the Congress Hall's signature curved roof was visible across the city, used a cutting-edge technique known as pre-stressed concrete construction. Many structures use concrete poured over steel bars or rebar to give it strength.
Engineers can make the concrete even stronger by stretching the bars tight before the concrete is poured. When it hardens, the steel is released, essentially compressing and strengthening the concrete.
Pre-stressing allowed architects to build bigger and bolder designs. Dr. Bound Isake, who later consulted on the iconic structure, explains.
The technique itself was fantastic at that time. The structure could not have been erected if post-tensioning or pre-stressing steel would not have been available at that time.
The pregnant oyster stood proud, hosting concerts and events for over 20 years, until one night disaster struck. On May the 21st, 1980, Berlin's famous Congress Hall began to crumble.
It was night and it was dark. And all of a sudden, a big crash happened and the roof collapsed, and it collapsed towards the street.
Filmmaker Carsten Krug raced to the scene.
I heard on the radio, a big accident happened at the Congress Hall, a famous building in Berlin, well known to all over the world. So I took my super 8 camera, my bike, and I went here to film all what happened here.
Carsten's footage captured the carnage.
I learned more and more here. I saw a red car, which was pulled from the accident to the street here. Many people were shocked, and it seems to be ghostly quiet here. It was unbelievable. All the people was so calm and quiet.
It wasn't just those who witnessed the catastrophic scene who were left in shock. The whole of West Berlin was in disbelief.
It had an incredible impact on Berliners, as it was the first collapse after World War II. And it was, hard to say, it was like an open mouth, an open wound.
Earlier that evening, the venue had been packed with concert goers. Although the crowds had left the building, tragically, one man was killed by the collapse. In the wake of the catastrophe, engineers needed to find out what had brought this iconic roof crashing down. Parts of the damaged structure were brought here to Germany's Federal Institute for Materials Research and Testing. Dr. Isaki and his team of experts discovered not one, but 2 types of corrosion.
This is an original post-tensioning member. When you look at it, you see there is the duct, and in the duct there are the high-strength steels. The steels were attacked. After the duct has been rusted through, hydrogen occurred, and the hydrogen was taken up or picked up by the steel, and the hydrogen embrittlement led to fracture of the steel.
With the pioneering roof, 2 decades of exposure to wind and cold, combined with internal stresses, triggered a form of corrosion known as hydrogen embrittlement. This phenomenon is caused as hydrogen atoms are absorbed into steel. They combine to form gas molecules, making the metal brittle. A failure of this type is very hard to detect and can result in a sudden and unexpected failure in a structure. However, in the case of the Berlin Congress Hall, there were visible signs that another form of corrosion was taking place.
There was just a little bit of rust staining on the surface, but people didn't expect that. Today, you know, every structure of this type is monitored. People go there, look at it, study the behavior, check it, and then make a decision if the structure still is safe or something has to be done for rehabilitation of the structure.
Rust is much more common than hydrogen embrittlement. And once it takes hold of the steel in pre-stressed concrete, if left unchecked, the material will fail. With the Congress Hall out of action, engineers were tasked with its repair. It took 4 years, but eventually the iconic roof was rebuilt in all its glory. To avoid a catastrophe like this from ever happening again, Dr. Isaki's team is responsible for keeping a close eye on Berlin's pre-stressed concrete.
When we find cracks on such a kind of steel that is removed from a structure, this structure is unsafe because the cracks that have a small dimension at the time when we remove it from the structure may grow. And therefore, we make the decision and say, no, close the structure, otherwise you will see problems in the future.
Today, the pregnant oyster stands proud, hosting more than 50 large events a year.
While the building may have suffered a terrible collapse, it has outlasted the regime it was built to challenge.
Through urban development, engineers dream of making their mark on a city's skyline. But focusing on form over function can be a recipe for disaster. Like Denmark's troubled bridge over calm waters.
There's something inherently wrong in the design and the engineering of this bridge.
This bridging beauty just wouldn't come together.
They just couldn't meet in the middle.
Copenhagen, a city with a rich history that today takes pride in its modernity.
Copenhagen has everything from striking historical architecture to cutting-edge contemporary structures.
When it comes to design, the Danes are famous for uniting form and function in the most innovative ways.
Local journalist James Clasper has lived here for 4 years.
Copenhagen is the capital city of Denmark. It's one of the most livable cities in the world. It's incredibly sustainable, it's incredibly green, it's a delightful place, it's beautiful. The name literally means in Danish, merchant's harbour. Why? Because there's loads of water since the 17th century. It's been a bustling city full of ships, full of boats. And now it's a sustainable city that's trying to get its people around by bicycle. And on a city built on water, the best way to do that is on bridges.
And it's Copenhagen's newest bridge that has everyone talking.
We're coming out of Nyhavn, the new harbour. It's actually from the 17th century, but we're coming into the main port of Copenhagen. And here is the inner harbour bridge. It's also known as the Kissing Bridge. The bridge was part of an ambitious plan to connect the entire city by cycle, lane, and bridge.
In 2016, the eye-catching Inner Harbour Bridge opened to pedestrians and cyclists, connecting the city centre with the Christianshavn district. Urban consultant Mikael Colville Anderson works with cities worldwide on cycle-friendly projects.
It's the most obvious location for a bridge. Right to the heart of the city is where this leads. The best thing about it is you can actually look around the city, look at the harbor front, see all the action. Quite nice.
The innovative design tackled an age-old problem for the city's bridges: water traffic.
The bridge crosses the inner harbour, so it has to be able to open for tall boats to pass through. Instead of a lifting or swinging bridge, the engineers opted for an innovative sliding bridge called a thrust bridge, with 2 retractable arms that meet in the middle.
Engineer Brendan Walker explains.
Some bridges open and close, like this. There are other types of bridges which can swing open. But what they decided to do was to create a new mechanism, which is why it's called the Kissing Bridge. The 2 halves slide in and back out again, just like a kitchen sliding drawer.
We're coming under the bridge now. You should be able to see part of the rolling mechanism, which allows these 2 retractable parts to move backwards on each side, while a larger ship with its huge mast, of course, is able to pass through.
This simple concept on a huge scale was designed to create clear passage for shipping when open, while appearing as a seamless crossing when the arms are closed.
To ensure that the decks are perfectly aligned when the bridge is closed, architects used a very simple bolt and hole arrangement, with 1 large bolt on each side, working much like dowels in woodwork.
So this is really the epicenter of the bridge. This is the entire concept right here. The nickname was the Kissing Bridge. It would sort of grind backwards and open and grind back, but gently kiss right here in the middle.
Although everything looks good today, construction didn't go as smoothly as planned.
This bridge was supposed to open in 2013, but there was a problem. The retractable arms wouldn't close properly. The kissing bridge wouldn't kiss.
The engineering of it simply didn't work. We've had open and closed bridges in our cities for like hundreds, thousands of years, and somebody decided they wanted to reinvent it. But this is really where the problem was.
It's rumored the bolts on one arm of the bridge didn't marry up with their designated holes on the opposite side by as much as 7 centimeters or 3 inches.
There's no footage of the failure, and the exact cause is still hotly debated. But the most likely theory appears to point to environmental factors.
No one's saying for sure why the two sides wouldn't meet, but one theory is that they were deforming because of an unanticipated temperature difference. Hot sun above, cold water below, causing the bridge to warp.
During construction, this temperature differential could have been causing expansion of the drawspan sections of the bridge that hadn't been predicted in the design phase.
An arm of the bridge in profile looks like my arm, thin in the middle and thicker at the end. It means there's less metal in the middle, which makes sense that any thermal effects could be exaggerated.
Take a cool expanse of water below, take hot beating sun above. We know that hot things expand, cooling things contract, and that can make things bend downwards. And under those conditions, if both sides are starting to bend downwards, they're never going to meet in the middle. And this was a massive engineering challenge to solve before the kissing bridge could finally kiss.
It took engineers 3 years to fix the bridge. And although the exact reason it failed in the first place remains shrouded in mystery, it's possible the solution was very simple.
One solution could be having wider holes or making the connecting bolts pointed or conical. That way there's more tolerance for misalignment. Once the tip is aligned, even with a small amount of warping, the conical shape would guide the decks together.
The engineering solution they came up with was to redesign the locating lug. On one side of the bridge, there's a locating hole. On the other side, a locating pin. They made the hole bigger, they made the pin smaller and pointier, making it easy for it to find a home.
It may now meet in the middle. However, the crossing still has its issues, particularly for Copenhagen's cyclists.
We bike a lot in Copenhagen, but really, this bridge is too steep. This bridge doesn't need to be this steep from an engineering perspective or design perspective. It could be much, gentler in its slope. But then you got to do these weird kind of turns, these little chicanes.
Steep gradients, slippery surfaces, and hazardous chicanes all add up to a bit of a nightmare.
This is really everything you need to know about the design of this bridge. Every time I'm here, there are new, fresh skid marks. You can almost smell the burned rubber. It has been like this for 3 years. People come over the bridge at speed, and they realize at the last minute, oh, I gotta do a quick little chicane off to the left. Uh-oh, hit the brakes. The city, after the fact, had to put up warning signs, red and white reflective material to warn people not to go straight. And there is literally a skid mark that ends right at the glass, and there always is. I've not heard of any cyclists, taking a dive over the glass just yet, but, it's gonna happen some days.
Clearly, there are several engineering lessons to be learned from this bridge. Fortunately for the people of Copenhagen, there are lots of other crossings to choose from. When building on or around water, engineers always have their work cut out. The smallest mistake can lead to the greatest catastrophe. Like here in the Golden State, where this dramatic failure threatened an entire region.
No one saw this catastrophe coming.
I had never seen it. I don't think anybody in the United States had ever seen it. It was a horrendous sight.
A disaster that spurred an industry into action.
This lucky escape revealed an engineering fail hidden in dams across America.
From the Sierra Nevadas to the Pacific Ocean, the California climate is known for one thing: sunshine.
The dry climate brings problems of its own, with vast swathes of farmland and huge cities demanding water. Keeping a ready supply is a constant challenge.
To regulate water supplies, California has a long history of building dams. One of the most crucial is the Folsom Dam across the American River. This dam was designed to do more than provide water to the surrounding area. Former regional dam manager Tom Aiken explains.
Folsom Dam is actually critically important, mostly here to the Sacramento area for flood control. But in addition to flood control, we provide a lot of the water that feeds this urban area. In fact, you'll see pipeline over here that goes over to Folsom. Pipeline over there goes over to Roseville and eastern Sacramento.
When completed in 1956, the 430-meter-long, 100-meter-high dam created Folsom Lake, holding back more than 500,000 Olympic swimming pools worth of water.
Dams are under constant pressure from the water behind. That should be no problem. It's what they're designed for. But if the water levels get too high and spill over the dam, known as overtopping, there's a risk the dam will erode and potentially collapse, causing catastrophic flooding downstream.
To prevent this from happening, most dams include a safety feature known as spillways. At Folsom, the spillways consist of 8 concrete chutes, each controlled by a gate, allowing dam operators to precisely control water levels in any conditions.
Folsom has 5 operational gates and 3 emergency gates. The emergency gates have the flip bucket there.
Like thousands of dams worldwide, the spillways are controlled with what are known as radial gates. It's a simple but effective layout, as dam engineer Steve Melovic explains.
Well, the radial gate works. It has 2 bearings and a curved plate. And imagine that the lake is right here, and a chain, 2 chains lift this gate up just like this and let the flow out on the bottom.
The curved design of the vertical section helps the gate to better withstand water pressure.
And so when the lake just rides up on the gate, this opens up and lets the water flow underneath it.
The radial gates on the spillways at Folsom operated smoothly for decades. Then, on July the 17th, 1995, dam operators planned to release water from the lake for routine maintenance. But as gate number 3 was opened, things did not go according to plan.
Our operator went up to open the gate, and when the gate got up about 2.5 feet, he said it started vibrating, a very unusual vibration. And he looked down, and at that point in time, the gate actually failed. Bolts popped, and the struts gave away, and the gate swung open like a garden gate.
Gate number 3 was severed open.
It was a horrendous sight. There was angled steel, and water was shooting out in multiple directions. So the whole face of the dam just looked like white water, a big white waterfall.
Dam operators had no way of closing the gate.
With the gate wrenched open, there was no way to stop the water pouring out over the coming days. 40% of the Folsom Lake gushed down the spillway. The big worry was that the excess flow would overtop the next dam downstream, the Nimbus Dam.
Overtopping this dam could destroy the Central Valley's last line of defense and flood the entire region. With water gushing uncontrollably from the Folsom Reservoir, it was crucial that the Nimbus Dam was prepared for the unexpected flow heading its way.
It was critically important for our operator to get down to Nimbus Dam He took immediate action, jumped in his truck, and headed down to open the gates there so we wouldn't overtop that dam. Had he not done that, then Nimbus Dam would have been overtopped, and that would have caused damage to 18 gates, plus it would have flooded the power plant down there.
Thanks to the quick actions of the Folsom Dam operator, catastrophic flooding was averted. With the imminent danger now over, engineers were left asking what had gone wrong with this decades-old, reliable system. It turned out to be a very basic but potentially lethal engineering oversight.
The investigation found that right back at the design phase, engineers hadn't factored in something called trunnion friction, basically resistance to opening at the hub.
Forensic engineer Chuck Howard investigated the accident.
There's a pin that goes into a bearing, a brass bearing, and when it's smooth and it's lubricated, it moves very easily.
A trunnion bearing system allows a shaft to rotate from a fixed point in a similar way to a ball and socket joint. In this case, the shaft is connected to the radial gate. Smooth operation of the gate relies on fully functioning trunnions. However, the trunnions at Folsom had a problem.
So think of some oxidation doing that, and that as that oxidation built up over the years, that trunnion friction increased. At the time when that gate at Folsom went up, it decided they'd had enough. And we had that one brace fail, and then it just multiplied itself to the other arms.
When they attempted to raise the gate, the corroded bearings were essentially jammed, and with the gate struggling, the force of the water from the reservoir snapped the support struts, leaving the gate wide open.
If you held on to one of these bearings like I'm doing and held onto it tight and then tried to lift the gate as the hoist would lift the gate, it makes it hard to lift the gate, right? And these beams are going to start to feel stress. They're going to want to bend because I'm holding on really tight to this bearing. So a little bit of corrosion and friction on that bearing translates to a big stress because it's a very big gate, and it caused it to buckle and for this entire part of the gate to start to move away from the dam and cause the failure.
There were 7 other identical gates at the dam. To avoid the exact same failure from happening again, all of them would have to be replaced. This time, thanks to major advances in materials technology with corrosion-proof bearings.
We ran a series of tests on this trunnion to understand that slow-moving and heavy load application of the bearing, and we learned some new things about the type of grease you should use.
It took 2 years and cost millions of dollars. But by November 1997, the new gates were in place, and the dam was fully operational again. But engineers knew there were hundreds of other dams across the country with the old-style trunnions, a ticking time bomb waiting to fail.
This epic engineering fail led to a mass inspection of dams with similar gates across the US. A program of repair or replacement was rolled out, and, in theory, the risk of any more disasters like this has been averted.
Folsom has become a case study for dam engineers worldwide. So hopefully, a catastrophic fail like that of 1995 will never happen again. Devastation as homes disappear in Florida.
It ate vehicles and boats and personal belongings. It just kept growing.
A tragic collapse in Oakland, California.
I instantly knew this was the biggest disaster I'd ever seen.
In Washington state, a revolutionary bridge becomes an epic disaster. And in the Netherlands, a cutting-edge design comes crashing down.
The top floor collapsed first, and then the second and the first.
With big builds, even the smallest mistake can be a huge disaster. From miscalculations to misunderstandings. Some with deadly consequences. These catastrophes are every engineer's worst nightmare. Sometimes in big builds, there's a delicate balance between man-made and Mother Nature. Get it wrong, and the results can be catastrophic. Like this disaster that struck a suburban paradise in western Florida.
These homes simply disappeared right in front of people's eyes.
This is obviously a huge catastrophe, an engineering nightmare.
And left a community wondering, when will this happen again?
Before you buy a house in Florida, this is something you definitely need to know about.
It was the most devastating thing I think I've ever seen in my life.
Florida, the Sunshine State, boasts the longest coastline in America's lower 48 states. But it's also one of the lowest lying and home to over 30,000 lakes. Hundreds located in the Tampa suburb, aptly named Land O'Lakes.
With year-round sunshine, endless lakes, and beautiful waterfront homes, Land O'Lakes is considered to be one of the top places to live in the whole of Florida.
Originally a group of small towns surrounded by swampland, the name Land O'Lakes was first coined in 1949, and its popularity and size soon grew.
The area's population has quadrupled since 1990, from just under 8,000 to over 35,000.
Most moved here for one reason, a dream home with a waterfront location. Realtor Christy Zimmer knows the local property market well.
It's a wonderful community to live in. It's interesting with property values in this area. We value the properties and how much waterfront they have.
To feed demand for lakeside homes, waterfront development boomed.
In the last 50 years, Land O'Lakes has gone from 350 homes to nearly 6,500. And it appears that not all of them were built on solid foundations.
On July the 14th, 2017, the residents of Ocean Pines Drive were woken by a rumbling. Christy was here visiting a friend.
It was early in the morning, probably about 8 a.m. We were able to sit in her driveway and watch the entire process take place.
A major sinkhole was opening up directly underneath residents.
You could feel the ground underneath you rumbling and just shaking, and I cannot begin to explain the feeling of the ground caving in underneath you, even from that distance. And watching these homes fall into that hole as it ate vehicles and boats and personal belongings with no regard. It just kept growing.
This sinkhole was so massive it swallowed up 2 homes, a boat, cars, and it just kept on growing. By the time it stopped, it was about the size of 4 Olympic swimming pools.
And to see the kids' toys floating in the top of the water was just heart-wrenching, knowing that they were going to come home to nothing.
That's just on the surface. It was about 50 feet deep to the bottom, which is about 8 times deeper than any of those pools.
It was the most devastating thing I think I've ever seen in my life.
For many who thought they had their dream home, this was the stuff of nightmares. Local reporter Evan Donovan covered the story.
This particular sinkhole uncovered a lot of issues for nearby homeowners that they had no idea about. Your quaint retirement life on a nice little lake in the middle of Florida suddenly getting swallowed up by the ground.
With 2 homes entirely swallowed up, 6 more condemned, and the width approaching 80 meters, the obvious question was what had caused the massive sinkhole to open up. One clear suspect was the area's geology.
Statistically, Florida has more sinkholes than any other state in the U.S. In fact, the area around the Land O'Lakes is known as Sinkhole Alley.
Florida is especially prone to sinkholes because it's largely built on limestone, which dissolves in water slowly, but it always dissolves.
And that slow but inevitable process is the reason there are so many lakes here. Geologist David Wilshaw explains.
The limestone here is very porous, lots of caverns in that limestone, and these circular lakes that we see all around us here are reflections of the ground collapsing into the limestone and creating these depressions in the land surface, which then fill with water and create the beautiful lakes we have in Land of Lakes.
While the sinkholes are actually responsible for the lakes that give the area its unique appeal, they also put its residents at serious risk.
You could say a sinkhole is like an hourglass, with material being eroded from below. Eventually, as the material slips through the cracks, there's nothing solid holding the building up, and the ground gives way with a sudden and dramatic collapse. Since 2003, there have been more than 300 reports of sinkhole activity in or around Land of Lakes. It isn't the Land of Lakes, it's the land of sinkholes.
So, sinkholes are known and expected here. And yet, despite all the evidence pointing to limestone eroding beneath the surface, geologists found that this sinkhole was the result of human activity.
Sinkholes are no surprise to this area, but here it seems that Mother Nature's not wholly to blame.
While sinkholes occur naturally in Florida, geologists believe many, like this one, are man-made. By rapidly developing the area, groundwater is extracted and used for irrigation or residential taps, creating a cavity, destabilizing the ground below. Building work above ground can weaken the limestone even further, causing the soil above the cavity to collapse suddenly and without warning. This type of sinkhole is known as a cover collapse.
The developer decided to dredge the canals to interconnect all the lakes to create more potential waterfront home sites. When they dredged those canals, they filled in areas that probably should not have been filled in at that time. And over time, Mother Nature's just decided to take her property back and turn it back into the lake.
The result? Decades later, the giant sinkhole opens up in Ocean Pines Drive. With homes and a road destroyed, engineers looked at ways to fix it. One solution used elsewhere is to simply fill the hole with a concrete plug. But here, with the land already unpredictable, completely filling it with heavy concrete wasn't viable.
There's no way this land could be used for development again. But to try to prevent it eroding further, engineers stabilized the bottom of the hole with tons of rock.
For now, the sinkhole isn't going anywhere, but it's a frightening reminder for everyone of the danger lurking beneath their feet. Journalist Evan Donovan covered the story.
It is bad luck, it is nature, but it seems like we have the technology now to figure out where it's most likely that these things would pop up, and then what we can do to sort of mitigate the impact when they do happen.
A lot of these homes were built in the 70s and 80s. Today, developers have new tools to check what's underneath, so in theory, this kind of collapse should be a thing of the past.
Geologist David Wilshaw thinks they may have found the answer: ground-penetrating radar.
And I know it looks like a glorified lawnmower, but it's a $30,000, very sophisticated-looking lawnmower. So, we use it all the time here in Florida to image the ground to try and find sinkholes. It puts electromagnetic energy into the ground, which passes through the different soil types at different speeds. And we can tell where those soil types have been disturbed. For example, if we have a sinkhole that might be forming, you'd expect to see those layers of soil dipping inwards towards the sinkhole.
While this technology can help prevent a future disaster, the demand for groundwater and land resources in Land O'Lakes continues to increase. And when you're building on shaky ground, there's always a risk. But despite the threat of other sinkholes opening up, there will always be a demand for homes with a lake view.
Losing your home is heartbreaking, but thankfully this time, no one was hurt or killed.
Pushing the limits in engineering leads to bold innovations and daring new designs. But get it wrong and the consequences can be deadly. Like this highway in California and an engineering catastrophe on an epic scale.
I instantly knew this was the biggest disaster I'd ever seen. It was like a giant had come and toppled the whole thing.
A heartbreaking tragedy that shook an entire city.
The sheer magnitude of this catastrophe turned thousands of tons of concrete and steel into rubble in just seconds.
Many were left wondering why this one structure was so completely destroyed.
I was looking at hand of God type of stuff here.
The San Francisco Bay is home to around 7 million people, drawn by its stunning, rugged landscape.
The Bay Area is one of the most beautiful locations in the world, but it's also one of the most earthquake-prone places on the planet.
The San Andreas Fault might be world famous, but it's not the only dangerous ground beneath this part of California. There are 7 significant fault lines underneath the Bay Area, with hundreds of buildings sitting directly on top of them.
In 1906, San Francisco got a big wake-up call when the largest earthquake in living history struck the Bay Area. The minute-long quake measured a massive 7.9 in magnitude, killed 3,000 people, sparked 3 days of fires, and left the bulk of the city homeless.
San Francisco was all but destroyed. People were scared. Rebuilding would take years. 200,000 refugees left the city. Many moved east across the bay to Oakland, doubling the city's population.
Despite the danger lurking beneath, in the mid-20th century the population boomed. In the 1950s, to ease congestion, construction began on a new section of freeway running through downtown Oakland. To bypass local streets, planners turned to an age-old solution. Instead of going around, they would go over.
Elevated roads have been around since Roman times and are known as viaducts. They're essentially a bridge or a sequence of bridges designed to carry a road over an obstacle, which could be a valley, a marsh, or a busy urban area.
But this would be no ordinary viaduct. The plan was to build California's first ever double-decker freeway. Essentially one long line of bridges standing on top of another, running for more than 3 kilometers. The result? The Cypress Street Viaduct.
In the 1950s, when the Cypress Street Viaduct was built, single-deck roadways were common, but building a double-deck viaduct was a first for California.
Like all structures in the Bay Area, earthquake resistance was a key factor in this groundbreaking design. Structural engineer Jack Moll explains.
The Cypress Street Viaduct was one of the very earliest examples in the United States using pre-stressed concrete, a form of construction where the concrete is cast with the steel reinforcement pre-tensioned inside the structure.
A lot of structures use concrete poured over steel bars, or rebar, to give it strength. Engineers can make the concrete even stronger by stretching the bars tight before the concrete is poured. When it hardens, the steel is released, essentially compressing and strengthening the concrete. That's known as pre-stressed concrete. It's widely used today, but back then, it was untested.
That was a very new, young technology. In fact, it was perhaps the first bridge in the United States that was built and designed with that technology. They were concerned that if the structure moved, it would develop internal forces that would cause cracking and decrease its service life. And so what was done was to build a structure that was very loosely tied together so it could move.
A fundamental element of this ability to move is steel rods embedded in the concrete where the columns meet, known as shear keys.
Shear keys are designed to allow a building to shake during an earthquake without moving too far. At least that's the idea.
In the viaduct, these were metal rods beneath the upper and lower columns designed to stop the top being shaken off.
Here, to absorb earthquake forces, they would allow some movement, but not so much that the top columns could slide off the bottom. The Cypress Street Viaduct opened in June 1957 at a cost of $9 million and was a huge success. It carried tens of thousands of vehicles a day for the next 3 decades. On Tuesday, October the 17th, 1989, Game 3 of the World Series between the Oakland A's and the San Francisco Giants saw more than 60,000 fans fill Candlestick Park. Anthony Moore, then a Cub reporter, covered the game.
So I went down to Candlestick Park in San Francisco to cover fans outside the stadium who didn't have tickets but still tailgated the game. We had barely gotten equipment out. The camera was just on the shoulder of the photographer when, boom.
Oh my God, we're having an earthquake. Wait a minute. Hold on. 911. Yeah, this is an emergency in San Francisco. What happened? There's a hell of an earthquake and we've got...
Just after 5 p.m., 60 million baseball fans saw their TV screens go black.
And we've got windows and everything else.
The largest earthquake in 80 years ripped through the Bay Area, registering 7.1 on the Richter scale.
The epicenter was over 60 miles or about 100 kilometers away, and the quake only lasted for 15 seconds, but it sent shockwaves that would leave a tragic mark on the city.
A 1.2-kilometer stretch of the double-deck Cypress Street Viaduct had collapsed.
I instantly knew this was the biggest disaster I'd ever seen. It was shocking. It was almost impossible to communicate visually or in words the scale of this devastation.
Mark Hoffman, then a lieutenant with the Oakland Fire Department, was on duty nearby when he realized a major disaster was unfolding.
We're only 2 blocks away from 14th and Broadway. That's basically the heart of downtown. When we pulled up here on 14th, I looked to the right. I saw a giant plume of smoke. Told the driver we're making a right.
From here on out to about a mile and a half, the freeway was either partially or completely collapsed.
About 25 feet up was the first deck, and then the upper deck had collapsed, pancaked onto the first deck. We were roughly located where it was intact all the way to right about there, and then was collapsed from then on, as far as the eye could see.
107 vehicles were on the Cypress Street Viaduct as it collapsed. Rescue crews and local residents worked to free people trapped in the rubble.
We had an elevated ladder that we were able to throw, got us up onto the lower deck, but on top of the collapse, and we went to work.
The rescue mission ran through the night, but despite the city's best efforts, 42 people lost their lives. In the coming days, questions were asked. When so many structures escaped serious damage, why was Oakland's Cypress Street Viaduct so catastrophically destroyed? After the collapse, investigations suggested that the pioneering use of pre-stressed concrete during construction 3 decades earlier had played a key role. Engineer Jack Moll explains.
We didn't at that time understand very well how big the earthquake forces could be in a structure of this type. So the amount of steel that was built into it was very little. So when the earthquake came along, the loose structure moved a lot. Those parts of the concrete that were inadequately protected by steel, they crumbled. As they crumbled, they lost the ability to support the weight of the structure. It started to come down, and as it moved downward, it broke other pieces of the structure, and the collapse projected along the length.
As the viaduct shook during the earthquake, the shear keys connecting the columns began to vibrate, cracking the concrete surrounding them.
Without proper support, they broke sideways through the columns. The structure collapsed.
So, the pre-stressed concrete surrounding the shear keys simply wasn't strong enough. And this wasn't catastrophic for just one section of the viaduct.
With a structure of this type, if during an earthquake, one of the elements should fail, in this case, one of the columns supporting the bridge deck, there's the potential that it loses its support, and as it begins to fall, it starts taking down the entire rest of the structure. In the case of the Cypress Street Viaduct, some very vulnerable pieces of the bridge failed first, and then as the structure began to fall, it, like a set of dominoes, took down the rest of the structure along the length.
Engineers may have overestimated the strength of the concrete, but that alone didn't explain the carnage. The disaster was made so much worse by the local geology. Earthquake engineer Jonathan Bray explains.
So the Cypress structure itself is actually founded on dense sands and stiff materials, but then it goes out across an old mud flat that has been covered with some artificial fill. And that mud in that location is anywhere from 3 to 7 meters thick. It's soft, it's weak, and that's the part of the Cypress structure foundation that shook the most violently during the earthquake.
The solid rock helped to dampen out the vibrations, but by contrast, this soft bay mud helped to amplify the vibrations by as much as 5 times. This quirk of geology made things much worse.
The effect of these huge amplification forces hadn't been factored into the original design.
When the ground comes and shakes a building, you can see that this shaking level, this period of the shaking, really causes this one to accelerate while the other ones barely move. If I shake it a little bit slower, you can see that there's very little shaking of the lower masses, but that longer mass, which is softer, tends to get amplified the greatest. When you build a structure on top of a soil deposit that amplifies shaking, you have an amplification of the forces that are placed on that structure, and therefore it causes more damage.
This combination of structural weakness and the soft geology proved to be fatal. After the disaster, the Cypress Street Viaduct was demolished and the freeway was relocated to the west along the old Southern Pacific Railroad corridor. Lessons were learned, and instead of a double-deck viaduct, engineers built a single-level bypass.
The failure of the Cypress Viaduct was one of those failures that taught us what we needed to do differently in bridge design.
One key lesson learned from the collapse was the need for a significant increase in the amount of steel used to reinforce concrete.
Typically, when we build reinforced concrete construction today, we've got very heavy amounts of binding steel that hold the concrete together, so that when an earthquake overwhelms the structure, if there's local crushing of the concrete, the reinforcement inside will hold it together and prevent a repeat of the Cypress Street Viaduct collapse.
These new breakthroughs in engineering and technology will hopefully make all structures safer in an earthquake, in the hope that something like Cypress Street can never happen again.
Cypress Street was renamed Mandela Parkway, and the Cypress Freeway Memorial at its heart is a poignant reminder for future generations of this tragedy.
In terms of total loss of life, in terms of damage to the infrastructure of the community, how long it took to rebound, what it just showed everyone in terms of potential, this, I think, was worst case.
With big structures, engineers aim high and push the boundaries with ambitious designs. But push too far and it can be a recipe for disaster. Washington State has been victim to this mistake in a very big way.
This has to be one of the most famous bridge collapses of all time.
This catastrophic failure earned its place in the Engineering Hall of Fame for all the wrong reasons.
We were seeing great chunks of concrete fall off the bridge.
With so much carnage, it seems incredible that no one was killed.
Washington State is a wild landscape shaped by powerful forces.
The Pacific Northwest has a very rugged feel from the mountains to the jagged coast. With waterways threading through the land, it's long been a haven for bridge engineers.
More than half a century ago, one crossing over the Tacoma Narrows revolutionized life for residents. Dale Wersing has lived here since the 1930s.
Before the first Narrows Bridge was built, the only reasonable way from Tacoma to Gig Harbor was to take a ferry. Your alternative was a long drive, so people in Tacoma were very excited about this improvement in their lives.
With their deep, steep sides, the 1.5-kilometer wide Narrows have long been a challenge for bridge engineers. These twin suspension bridges have stood here since 1950 and 2007. But their now infamous predecessor lasted barely 4 months after opening. The original Tacoma Narrows Bridge took almost 2 years to build. Its giant towers loomed 135 meters over the Narrows, while 600 kilometers of cables held the road deck in place.
When the Tacoma Narrows was built, it was the third longest suspension bridge in the world. Only the George Washington and Golden Gate bridges were longer.
The Tacoma Narrows Bridge might not have been the world's longest, but in engineering and design, it was way ahead of its time. Engineer Stephen Ressler explains.
Early in the 20th century, suspension bridge design underwent a kind of a revolution as a result of a radical new mathematical theory of suspension bridge analysis. Long-span bridges could be designed such that they were much more slender, much more elegant.
That streamlined, elegant effect was achieved by drastically reducing the side profile of the bridge.
Most suspension bridges back then supported the road deck with lattice beam trusses, which let the wind flow through. Here, to slimline the bridge, they used narrower, solid girders.
Using solid girders instead of a lattice structure allowed engineers to reduce the depth of the girders from around 9 meters to just over 2. Instead of through, the wind would pass over and under, and yet, crucially, the bridge would be just as structurally sound. At least that was the theory. The lead engineer claimed the Tacoma Narrows crossing was the most beautiful bridge in the world.
The bridge engineers achieved their dream of a slim, elegant structure, but there were signs of trouble. Even before the bridge opened to traffic, it was known to rock, even in gentle winds, earning it the nickname Galloping Gertie.
The bridge wasn't just swaying, it was twisting and bouncing.
Engineers tried various fixes from extra cables to dampers, but nothing would stop the swaying.
It seems hard to believe, but although the bridge did clearly move, it was deemed safe for use and opened on July the 1st, 1940. Dale was just 4 years old at the time.
One of my memories from my childhood is going for a walk on the newly built bridge, and I have a recollection of the bridge kind of undulating, moving in waves.
On November the 7th, just 4 months after opening, the wind seemed to be making Gertie gallop more than ever.
There were 3 people on the bridge when the buckling started. The bridge was twisting and jumping so violently it was impossible to stand up, so they had to crawl to safety.
The movement of the bridge quickly worsened, to the point at which the cables could no longer handle the load. Just over an hour after the rocking started, the central span dramatically collapsed, leaving little more than the main towers standing.
As I watched Galloping Gertie fall, we were seeing great chunks of concrete fall off the bridge and splash into the narrows.
Thankfully, everyone made it off the bridge before the deck failed. The only victim was a dog named Tubby, who was trapped in a car. In the aftermath, an investigation was launched to determine exactly what had gone wrong. To prevent a repeat, engineers needed to know why Galloping Gertie had collapsed so dramatically. This included wind tunnel tests, which revealed that the failure was connected to the cutting-edge slimline design.
The heart of the problem was the solid supporting girders. They were interacting in an unexpected way with the wind passing over the bridge.
Engineer Stephen Ressler explains.
What happened with the Tacoma Narrows Bridge, and is a common phenomenon on long flexible suspension bridges, is that the wind blowing across the bridge causes aerodynamic effects which result in periodic vibrations of the bridge. If I disturb this structure, it will vibrate at a certain frequency, that is, a number of cycles per second. The aerodynamic phenomenon that occurred on the Tacoma Narrows Bridge was that the distortion of the bridge under the action of the wind blowing across it caused the disturbance. That disturbance generated turbulence in the wake of the wind flowing across the bridge, and that turbulence reinforced the deformations, such that with each cycle, the aerodynamic effect of the wind blowing across the structure reinforced the size of the individual vibrations. So the vibrations simply got larger and larger and larger.
The phenomenon behind these self-sustaining and destructive vibrations was little known back then. Today, it's called aeroelastic flutter.
Aeroelastic flutter is a very complicated phenomenon, but fundamentally, if the natural vibrations of the structure and the wind work together, the flutter can get so bad that the structure shakes itself apart. And that's what happened with the Tacoma Narrows Bridge.
Learning from the collapse, engineers designed a new bridge. This time, they were taking no chances.
The solution was really just to revert back to the technological form that was prevalent prior to the design of this structure. And that was simply the use of robust stiffening trusses to stiffen the deck of the bridge. And so just as that stiffening truss was the solution to the problem of handling heavy concentrated loads, it also proved to be an entirely effective solution to the problem of wind-induced vibrations.
Engineers were able to repurpose the approach span from the original slimline structure, with the difference in depth between the old and new technology blindingly obvious. Project manager Tim Moore explains.
What you're seeing here are three of the original Galloping Gertie 1940 bridge spans. These spans were not damaged in the 1940s collapse. What's unique is when we get to the side span, you can see the 43-foot deep stiffening truss. It's torsionally significantly stiffer than the plate girder system of the 1940s Galloping Gertie bridge.
The new reinforced Tacoma Narrows crossing has carried traffic since October 1950 without the slightest hint of a gallop. It even earned the nickname Sturdy Gertie and can withstand wind speeds far in excess of those that brought down its predecessor.
On the 1940s bridge, the flutter speed has been determined through wind tunnel testing to be a speed of around 20 to 30 miles an hour. The 1950s bridge has a flutter speed that exceeds 127 miles an hour. We don't ever expect to see those kinds of winds, and therefore the structures will remain stable for their entire existence.
Over time, traffic using the crossing became so high that in 2007, a twin suspension bridge was opened, running next to Sturdy Gertie.
This disaster highlighted the risks of pushing the boundaries with massive structures and has influenced bridge designers ever since.
Sometimes in engineering, even the best laid plans can go disastrously wrong, and the smallest mistake can lead to catastrophe. Like this pioneering structure in the Netherlands, which failed spectacularly.
The top floor collapsed first, and then goes the third floor, and then the second and the first.
A building reduced to rubble in seconds.
The mistakes hidden within every level of this build triggered a nationwide panic.
The Dutch have a long history of exploration, and it feeds into all walks of life, including their architecture and engineering. Local journalist Yuwar Abbas explains.
Dutch engineers, they like to build fancy structures, not only for living, let's say, to use it, but also to make it look nice.
This is the Hourglass building in Amsterdam's Zuidas business district.
This building is a great example of Dutch innovation. When it's complete, it will house offices and a hotel, all in a cutting-edge geometric design.
But this development isn't only about the aesthetic. It's being constructed using a pioneering new technique. Instead of using standard concrete for each floor of the building, engineers have opted for biaxial voided slabs.
Biaxial voided slabs sound very technical and complex. However, the principle of this technique is relatively simple, not to mention ingenious.
When constructing a new floor slab, rubber spheres filled with air are placed into a steel framework. Then concrete is poured into that framework. The result is a slab that uses 1/3 less concrete than a solid slab.
Less concrete means that the floor slab is significantly lighter and cheaper, but it is just as strong as a solid concrete slab.
Structural engineer Professor Robert Nies is familiar with the technique.
It's a very good practical thing, because you have to reduce the weight of the floor. All this stupid concrete, which is enormously in weight, 2.5 times as much as water. So it's all pressing down all the time long. So if you can make that into air, you save enormously weight of the structure. So it's a very clever system.
With this technique, architects can create bigger spans in buildings requiring uninterrupted space.
It's an ideal method for buildings with open plan spaces, like an indoor stadium or a car park.
In 2016, architects working on Eindhoven Airport were planning to use air-filled concrete in a new state-of-the-art car park.
This is the second largest airport of the Netherlands. This demands extra space for the parking. So the parking garage here is located perfectly near the Eindhoven airport. And for a technology like bubble deck, this is the perfect application because you have wider floors and you want to use your space efficiently. Moreover, this gives you an advantage of sustainability.
In late May 2018, with the building nearing completion, disaster struck. A large section of the car park collapsed.
On the day of the incident, it was a complete chaos here. 4 floors of this building behind me collapsed. The top floor collapsed first, and then goes the 3rd floor, and then the 2nd and the 1st. And people were shocked. The biggest fear of the people were, are there any casualties?
Luckily, no one was hurt. But just hours before, dozens of workers had been on site. An investigation was launched to discover what was behind this catastrophic fail. All eyes focused on the biaxial voided slabs.
The section of floor that had caused the collapse was constructed of the bubble-filled concrete. But it wasn't the slabs themselves that were to blame. It was how they were laid.
Engineers were positioning the slabs to span a large space between 2 main structural columns. But instead of following the plans that had each end of the slabs placed on the supporting columns, they rotated them through 90 degrees. So some slabs had no actual support from beneath. This created a weak, unsupported point in the middle. The investigation concluded that the decision to rotate the bubble-filled concrete slabs by just a quarter turn was the crucial mistake.
Normally these plates are made in long plates and they are spanning from wall to wall. In this case, they decided to use it the other way, to make plates like this and in between like this. This can work, but it means that where the joints are, has to be extra reinforcement. They forget it.
This is such a simple fail. If the plans had been followed correctly, the floor would have been fine.
The report found that without reinforcement, the floor was so vulnerable that even the slightest increase in load was enough to cause it to buckle.
When this car park behind me collapsed, this was big news in the Netherlands because most of these government buildings and schools in the Netherlands use the same building techniques as was used in this car park. They pinpoint 150 buildings which required investigation, thorough investigation.
To prevent another catastrophe, the Dutch Safety Board inspected the buildings in question to ensure that the bubble-filled concrete had been installed correctly.
Until the investigation was finished in these 150 buildings, the people and employees in those buildings were instructed to be careful. For example, they were not allowed to gather in numbers. They were not allowed to dance.
It sounds ridiculous to ban dancing and office gatherings, but this reveals how worried people and organisations were about the structural integrity of these buildings.
All the buildings investigated received the all clear, and the restrictions imposed on employees were lifted.
I've no idea how much dancing typically goes on in Dutch government buildings, but now it's official, you can bust your moves without fear of causing a building collapse.
Not only that, but the use of bubble-filled concrete is more popular than ever across the Netherlands. Disaster strikes a state-of-the-art bridge in Miami.
This was a brand new construction project
How could this happen?
A bold new skyscraper in danger of collapse in downtown Boston.
The building itself would actually collapse by blowing over.
In Alabama, a radical railroad crossing with a deadly design flaw.
I knew it was going to be a really, really bad situation. There was no escape.
And a Spanish energy project that shocked everyone.
The gas goes into the fault moves, and then you have your earthquake.
With big builds, even the smallest mistake can be a huge disaster. From miscalculations to misunderstandings. Some with deadly consequences. These catastrophes are every engineer's worst nightmare. In the mission to create more audacious builds, design can sometimes dictate the engineering. But the safety and strength of any new structure should always take precedence over style. Like this bridge in Florida, and one of the worst construction catastrophes in recent history.
No one who was here could believe that it had actually happened.
A landmark project with a fatal flaw.
This bridge was meant to be a masterclass in design, but it was hit by a catalogue of errors.
It would stay as a day that we will remember always.
Miami, Florida, known for its great beaches and stunning architecture, is also a major university town.
With more than 50,000 students, Florida International University is the largest in South Florida, and it has a world-renowned engineering research facility.
With student numbers growing, FIU recruited private developers to build high-rise housing within walking distance of campus. The only problem was that walk included crossing a busy 8-lane highway. Investigative reporter Nicholas Nahamas explains that just making it to class could be dangerous.
We're now driving down Southwest 8th Street, a really busy commuter road. Crossing it can be something like the old game of Frogger. So for students who tended to live on the Sweetwater sides, for them to get to class, they had to cross this extremely busy road. Students would sometimes dart across. One girl was killed and several other students have been injured. So there was a real need for a pedestrian bridge that would connect the living area and the classroom area.
The solution seemed simple. Build a pedestrian bridge spanning the roadway.
The university didn't just want this to be a functional project. The ambition was a landmark design that both the university and the students could be proud of.
Work on the $120 million signature bridge began in March 2016. The design would be a pioneering interpretation of a traditional truss bridge, but with the revolutionary look of a dramatic cable-stayed crossing. The asymmetric design further complicated the geometry of the bridge, as engineer David Beck explains.
The layout of a normal truss system is it'd be equal, it'd be symmetrical, but however, since this was made to look like a cable-stayed bridge, with the pylon coming up to here, with cables coming into it, that the location of these diagonals is to match the cables coming down from the pylon.
But that wasn't the end of the engineers' bold plans. The 53-meter-long main span would be assembled using a revolutionary technique called accelerated bridge construction, or ABC for short.
One principle of ABC is to avoid disrupting traffic during construction. So step one is to build as much as possible beside the freeway while the road remains open.
With a major 8-lane highway to cross, the appeal of the ABC method was obvious.
Bridge spans are prefabricated on the side of the road. then traffic is stopped for just a matter of hours as the bridge is moved and lifted into place.
The engineering department actually has a center for accelerated bridge construction. However, the ABC Center and engineering department were not involved in the construction or the design of the FIU bridge.
On Saturday, March the 10th, 2018, as night fell, the road was closed, while the pre-constructed main span of the FIU Sweetwater University City Bridge was lifted from the roadside and lowered into its permanent home over the highway.
The bridge was actually constructed in this empty lot over here, and then in one night raised into place here.
The next evening, the road was reopened to traffic, but with 6 months of construction still to go, unresolved existing issues were beginning to cause concern.
More than a month before, the cracks had already been discovered in the bridge at its north end. The cracks were hairline, but they gradually became bigger and bigger until after the bridge was raised, cracks are really gaping 4 inches deep. It's very alarming.
Workers on the bridge, including senior management, raised concerns about the cracks.
In the days that followed, photographs were taken of the raised span. It appeared that the cracks were getting bigger.
2 structural engineers had been inspecting the bridge, and they believed that the cracks looked much worse in real life than in the photos.
While acknowledging that they did not know why the cracks were occurring or getting bigger, engineers determined that the cracks didn't present any serious safety concerns. 5 days after the span was lifted into place, at approximately 12:45 p.m. on Thursday, March 15th, disaster was caught on a truck dash cam. The entire 860-ton construction collapsed. Nearby restaurant owner Leonette Sardo heard the crash.
We were working at the restaurant that day, and we heard a very loud noise. As I looked over, I see that the bridge had already fallen down. When we get there, you see that gigantic bridge on top of cars. All of the alarms from the cars are going off like crazy, and we were just trying to see what we could do. The scene was completely memorable in a very bad way.
Student Aura Martinez was also devastated by the aftermath.
I was just about to order when all of a sudden the bridge collapsed. And I was very shocked. I didn't believe it. I just wanted to go and see what I could do. I jumped the border, I ran to the bridge, and the cars were stuck underneath, and there was nothing we could do.
The collapse cost the lives of 5 motorists and 1 construction worker. But why did this pioneering project, designed to safeguard lives and prevent accidents, go so badly wrong?
When we knew that the bridge was going to be built, we were so excited. It was just an enormous project that everybody was looking forward to. For it to become a tragedy instead of hope really affected us.
This was a brand new construction project in the United States of America, you know, one of the most industrialized nations in the world. How could this happen? How could a brand new bridge fall down on people who were just driving on their way to work or school?
The pedestrian bridge, designed to make life safer for Florida International University students, had tragically collapsed. The official report into the disaster highlighted a design flaw in the innovative structure.
One of the problems was that the signature design, essentially mimicking a cable-stayed bridge, dictated the angles of the support struts.
To create the illusion of a cable-stayed bridge, the diagonal supports on the truss had to line up perfectly with the cables. But this uneven zigzag pattern created a weakness at a key connection. Engineer David Beck explains.
When this structure was fabricated on the side of the road, it was picked up by transport, rotated 90 degrees, moved down the road, and then set on the pier. That night, a worker identified that there was major cracking down here at the bottom of member number 11 that evidently created a weak spot. Those cracks were reported to the engineer. They were coming back, and someone had given the orders to retension those rocks.
The idea was that tightening steel rods in the concrete would close up the cracks. But this step was not included in the design, and some believe it may have compromised the integrity of the entire structure. Investigative reporter Nicholas Nahamas covered the story.
The project's engineers thought that by tightening the rods, the cracks would close up. In fact, what they delivered was the fatal blow to an already failing bridge. By putting so much pressure on a piece of the bridge that was already under stress and cracking, they snapped it. So it's really the smoking gun, we believe, brought it crashing down.
When this area down in here exploded, the whole bridge collapsed within a second.
It seems the signature design compromised its integrity. And some believe other errors contributed to the scale of the tragedy, including the road remaining open during an unplanned phase of construction work.
You really have to take a look at it as two accidents. One is the construction accident, and the second one is the traffic accident. If the traffic under 8 lanes of the bridge were shut down, you would have only had a construction accident. The fact that they didn't close down doing this critical construction work with live traffic under it, you ended up with catastrophic failure.
The idea of the bridge was to improve the infrastructure of the campus. Instead, it left a lasting mark on its memory.
The tragedy has left a lot of people in Miami both extremely angry and bewildered. So the university went from having this big signature bridge project to a deadly disaster and tragedy on its hands, and it still needs to build a new structure across this space in order to get students across.
This marked all of us, and it would stay as a day that we will remember always.
Sometimes in engineering, what you build on top of is just as important as the materials you use. Getting them both wrong is a recipe for disaster. In Massachusetts, an award-winning design threatened to become a deadly disaster.
Huge sheets of glass falling from over 200 meters.
A skyscraper in real danger of crashing down in the middle of downtown Boston.
The tower could potentially topple into Copley Square in the Back Bay below it.
Bordering the Charles River, Boston, founded in 1630, is one of the most historic cities in the US. Boston has always had the ability to adapt and think on its feet, as local journalist Tim Logan explains.
Boston is one of the oldest and most historical cities in the United States. It's home to many great universities. It's a thriving urban metropolis. It wasn't always this way. Back in the 60s, Boston was fairly depressed. Its factories were closing. The ports that had fueled the city's economy were fading away. But what we had was big insurance companies. Prudential Insurance Company and the John Hancock Insurance Company.
These insurance giants decided to breathe new life into the city, building big and building bold. None would stand out on the skyline more than the new John Hancock Tower.
There hadn't been a skyscraper built in Boston since the turn of the century. They were changing the skyline. John Hancock decided to put their tower on this site behind me, on one of the most historic and most architecturally significant corners in Boston. And they had to come up with a design that respected all of this history, both sort of culturally and architecturally.
With limited space beside an already packed square, the architect designed a minimalist and modern glass building, 62 stories tall, that would be striking without overshadowing any of the historic buildings around it. Using more than 10,000 1.2 by 3.4 meter highly reflective glass panels with a subtle blue tint, the idea was that the tower would only have a slight contrast with the sky on a clear day.
It's actually a very subtle building in its way, but it also led to some of the design challenges that ultimately became something of a problem in the construction of the Hancock Tower.
Construction began in 1968, but as early as the excavation stage for the tower's foundation, the project hit its first major snag.
They had to dig out millions of feet of dirt all the way down to bedrock. I believe it's 140 feet down. And this part of Boston was largely marshlands that were filled in the 1800s.
Much of present-day Boston now sits on reclaimed land. As the city expanded, large tidal flats were filled with mud, sand, and gravel to create new land for development. Like one of the city's most exclusive neighborhoods, Back Bay, home of the Hancock Tower.
Originally, in the 1600s, the city of Boston covered just 800 acres. That's smaller than Central Park. Today, it's over 7 times that, with around 5,000 acres of man-made land. That's more than any other American city.
Years later, when excavation started for the foundations of the Hancock Tower, temporary steel walls were erected around the construction site to hold back the soft mixture of reclaimed land. But the walls weren't strong enough and bent inwards under pressure from the surrounding land which they were supposed to be holding back.
This inward bend of the retaining walls damaged utility lines, the sidewalk, and nearby historic buildings, including the 150-year-old Trinity Church.
There was a lawsuit, and that led to some delays in construction even before the building started coming up out of the ground.
If that wasn't enough, it was when they started going vertical that they began to encounter even more problems.
The Hancock Tower was slated to open in 1971, but engineers were facing a growing list of issues caused by the unusually long and narrow construction site. To fit within it, what would become New England's tallest tower was designed as a thin rectangle with a total height approaching 240 meters. The layout made it vulnerable to the elements. Structural engineer Stephen Ressler explains.
There were fundamental problems associated with the performance of the John Hancock Tower. The building was relatively long in one direction and relatively narrow in the other direction as a consequence of constraints of the site. Because of that geometry, and because it was a relatively lightweight steel frame, it turned out to be highly susceptible to wind-induced sway. It also proved to be particularly susceptible to twisting or torsion as a result of its unique shape.
And this twisting began to reveal a major construction problem for the tower's feature design element, the more than 10,000 glass panels, each weighing more than 200 kilograms.
Every one of these rectangular panels was essentially completely filled in with glass. The windows used were double glazed, housed in a set of metal frames with 2 glass panels. The inner face of the outermost pane of glass had a metallic coating. Unfortunately, that metallic coating proved to be the undoing of this window mounting system.
To keep sunlight out and give the tower its trademark mirror look, the glass panes were treated with a layer of chromium. This was joined to the frames with rigid lead solder. As the panes moved from the building's swaying or changes in temperature, these rigid joints cracked the glass. In turn, the panes risked detaching from the building and falling to the ground below.
Huge bits of glass that were 1 meter by 3 meters were literally popping off the building and crashing to the sidewalk hundreds of feet below.
In fact, it got so bad that police had to close off the surrounding streets whenever winds reached 45 miles per hour, or around 70 kilometers an hour.
With public safety a top priority, In October 1973, the decision was made to replace all 10,000 plus windows with panes that were more flexible at a total cost of around 40 million in today's dollars.
During the many months it took to repair the tower, sheets of plywood replaced many of the missing glass panels, earning it the nickname the Plywood Palace.
The John Hancock Tower finally opened in 1976, 5 years behind schedule and around $100 million over budget. But that wasn't the end of the problems.
So once the building opened and people started to move in, there was a new complaint, motion sickness. People on the top floors started to feel a lot of swaying in the wind and nausea.
Forensic engineer Elizabeth Mulch explains.
Every building moves, even heavy buildings move, but you don't feel that movement until the buildings get tall. Steel buildings are particularly susceptible to the kind of movement that people can feel.
The radical solution was to install a pair of 300-ton weights on the 58th floor, known as tuned mass dampers, to stabilize the building.
A tuned mass damper is a lot like a kid's feet when they're on a swing, and when they're pushing their feet forward in time with the swing, then they go faster. If they're out of phase with the movement of the swing, they can make it stop. So it's not dangerous if a steel building's moving with the wind. And again, every building moves. But tuned mass dampers are a way to mitigate the amount of movement so that everyone feels comfortable over the height of the building.
With its long, thin footprint, the Hancock Tower needed not one, but 2 dampers.
The reason there are 2 weights instead of 1 is so that they can tug in opposite directions when the building sways or twists in the wind. The effect is very much like that of a gyroscope stabilizing the tower.
But the tower's engineering trials were about to get even more serious.
Engineers discovered another totally unexpected problem that had the potential to bring the whole tower crashing to the ground.
Even with the mass dampers in place, under a certain kind of wind loading, it was discovered that the entire tower could actually fall over.
The most serious issue with this building turned out to be a significant structural deficiency. A very prominent structural engineer discovered, with the wind striking the narrow face of the building, that the building itself would actually collapse in this mode by blowing over in response to the wind.
The thin rectangular structure was assessed as being much more unstable on its narrow sides. To prevent any potential catastrophe, the solution was to strengthen it with 1,500 tons of internal steel bracing.
This solution is really fairly straightforward from a structural engineering perspective. But from an economic perspective, it would have been extraordinarily difficult and expensive because it involved adding a lot of structure to a building after it had already been put together.
Despite all its problems, the John Hancock Tower still has a special place in the hearts of Bostonians.
For all the troubles that befell it during construction and in the first few years after it opened, the huge cost overrun, the Hancock Tower stands out distinctive on the city's skyline. It's on every postcard. And it's one of the most beloved buildings in the city. And probably will be for a long time.
The Hancock Tower was and still is an innovative and bold building, and as improbable as it may sound, actually won a prestigious National Architectural Award in 1977.
Some engineering errors can lie undetected for decades. And it only takes one mistake to turn an engineering oversight into tragedy. Like this remote railroad catastrophe in Alabama, which had disastrous consequences.
When we got there, it was a horrific sight. One car hanging off the edge of the bridge, multiple cars in the water, no escape.
An engineering oversight only uncovered by a string of tragic events.
There was no warning. No one knew this train was hurtling towards disaster.
One of the worst rail accidents in US history, which led to an urgent review of national regulations. On the Gulf Coast in the southern US, with a population of over 200,000, lies Mobile, Alabama, where the Mobile River slices the state in two. Local journalist David Rayner explains why this area conjures up the true essence of the South.
We really pride ourselves in having a beautiful downtown, situated right on Mobile Bay. Mobile has one of the largest ports on the Gulf of Mexico. One of the great things about the Delta is the wildlife. It's alligators, snakes, and you got to be careful when you're in the water.
South Alabama is notorious for its swamps, and these are crisscrossed by sluggish and slow waterways known as bayous. One of the biggest is a tributary of the Mobile River, and it's called Big Bayou Cannot.
About a century ago, this slow, sleepy backwater found itself in the path of a new railroad that ran coast to coast across the US. The first Bayou Cannot rail crossing was 2 truss bridge spans stretching over 90 meters bank to bank. But in 1909, as the waterways got busier, the railroad replaced one of the trusses with a 42-meter steel plate girder span. The new span was anchored to 2 of the 3 piers beneath it, but intentionally left unattached at one end. The thinking was that if the bayou was ever needed for water traffic, the bridge could rotate or swing a full 90 degrees to allow barges and ships to pass.
So although the entire track was welded together, the end span was not bolted in place.
That might sound unusual, but it was basically future-proofing the bridge to allow river traffic to use the bayou further down the line.
But those plans were put on hold, as structural engineer Farhad Ansari explains.
The bridge was made like a swing bridge to begin with. However, the motorized part was not installed. It was basically railway tracks and girders connected to a truss part of the structure.
Although it wasn't considered at the time, leaving the end span unsecured made the bridge vulnerable to impact damage. The bayou ultimately remained closed to water traffic, and the unusual setup was eventually forgotten. On September 22, 1993, the towboat Movilla was heading up the Mobile River in dense fog, pushing 6 60-meter barges. Captain Ted Morley's simulator is set to the precise weather conditions of that night.
The evening of the accident, it was dark, it was foggy, so there was absolutely zero visibility. Because of the bayous being very swampy, you can have great visibility one moment, and then you go down to a whiteout condition the next moment. It's very disorienting to operate in if you're not properly equipped for it.
Just after 2 in the morning, the boat missed a bend in the river, and although the crew was unaware, they were now heading down the Big Bayou Cannot.
Fog is a big problem. I know I've been out on fishing trips where it was so foggy that I became disoriented. I thought I knew where I was. When the fog finally lifted, I was at least a mile from where I thought I should be. I understand fully how the captain could have been disoriented and lost his way going up Mobile River.
Big Bayou Cannot is narrow, shallow, and pretty much impassable for boats, certainly large barges, so heading into it at night was never going to be intentional.
Meanwhile, the Sunset Limited passenger train, en route from Los Angeles to Miami, arrived in Mobile to pick up passengers for the next leg of its journey. When it departed, there were 202 passengers and 18 crew members on board. Lost in the fog, the Movilla had no idea it was heading straight for the rail crossing.
So on a radar screen, we can see the bridge itself, which he interpreted as another vessel that was operating on the river. He was sounding it, trying to call the other vessel, when in fact it was the bridge for the Amtrak train crossing Big Bayou Cannot.
At 2:45 a.m., the lead barge struck the bridge at the unsecured end of the steel girder span. Despite the massive collision, the rails were not completely destroyed.
The impact force was sufficient so that it created 3 feet of displacement. So it mangled the tracks. It didn't break them.
Unfortunately, he didn't hit it hard enough to actually sever the rail, so the signal that broadcasts to the train that the bridge is out didn't actually get activated.
The train was heading at near full speed towards this track that was bent out of line by more than 3 feet, so that's about a meter. But with every signal on green, the train driver had absolutely no way of knowing that anything was wrong.
To make matters worse, the crew of the Movilla had no idea what bridge the barge had struck.
He mentioned that he had struck a bridge on the Mobile River 4 miles to the north of his actual position.
8 minutes later, with no warning, the Sunset Limited hit the deformed tracks and derailed, destroying the damaged bridge. David Adcock was a bosun with the US Coast Guard when he was woken by a call.
Early morning, September 1993, the phone starts ringing. He said, "Get up, have a train in the water." Pulling into the mouth of Bayou Canot, there was a barge almost blocking the entire mouth of the bayou. But as we came around that barge, it was unbelievable, the sight.
The first 7 cars had derailed, plunging into the bayou below.
The water was on fire. There was diesel pouring out of the engines. The lead engine, when it left the tracks, had just buried, I think, 40 feet in the mud. It makes you want to run away and not to see that. The tragedy, I'll never forget that.
At first light, journalist David Rayner arrived on the scene.
By then, the fog had lifted. When we got there, it was a horrific sight. There was still fire burning on one of the engines, and there was one car hanging off the edge of the bridge. I knew it was going to be a really, really bad situation. There was going to be a lot of people that were in those cars underneath the water, and there was no escape.
103 people were injured, while 42 passengers and 5 crew members lost their lives. And everyone demanded answers. An investigation was launched to establish exactly what had happened and whether this was just a tragic accident.
There's no doubt that the barge hitting the bridge triggered this disaster, but investigators also found that this structure was particularly vulnerable to vessel collision.
The bridge was low to the water with no lights, and the fact it was a swing bridge acting as a fixed bridge complicated things further. David Rayner explains.
The rails were welded instead of in pieces. What happened when the barge hit the bridge piling was it shifted and twisted the rail, and so when the train hit that twisted part, it derailed.
Had one of the rails snapped instead of bending, it would have broken the track circuit and the signals would have gone red. In theory, this should have given the train enough time to stop.
So there were a lot of contributing factors to this. The weather conditions, the design of the bridge, the lack of proper signaling, the total lack of familiarity with the area. He was totally disoriented. A lot of things came together and contributed to this accident.
As a result, the fatally damaged section of the bridge was replaced. In addition, the safety report recommended beacons, radar reflectors, and other devices to make future bridges more identifiable on radar, as well as other visibly identifiable markers on the crossing themselves. So hopefully nothing like this will ever happen again.
In the wake of such a major disaster, it was vitally important that engineers and emergency services learnt lessons from the tragedy.
This was the worst accident in Amtrak's history, and one that is sadly forever etched into the minds of those who were there.
You know, if you ever witness this, you will never forget. You will never forget the Sunset Limited disaster.
Major engineering catastrophes can often be traced back to a minor miscalculation in the early stages of a project. Get your maths wrong, and the disaster can run deep. like this literally groundbreaking subterranean blunder off the coast of Spain.
Spanish authorities quickly realised that this ambitious project could actually be very dangerous.
A grand plan that rocked the Mediterranean coast in all the wrong ways.
A project which was wrongly conceived and even worse developed.
On paper, it seemed like a great idea, but it hit the headlines for all the wrong reasons.
And then you have your earthquakes.
Spain has a rich mix of history, culture, and natural beauty, including its stunning Mediterranean coast. But some things are in short supply.
Spain has very little natural gas of its own. In fact, 99.9% of the gas it uses is imported, either by pipeline from North Africa or arriving in ships.
To avoid a shortfall, engineers came up with a truly ambitious solution.
Hola, buen día. Buen día.
Called the Castor Project. Journalist Jordi Marcel covered the story.
The initial idea of the Castor project was to take advantage of a dry oil well here in the Mediterranean and to store gas underneath the sea.
And it just so happens the Spanish had found the perfect place to put this bold plan into action.
Off the coast of Spain, between Barcelona and Valencia, there is a massive old oil reservoir under the seabed. The oil was extracted back in the 1970s, but some clever engineers came up with the radical idea of reusing the cavity left behind, giving Spain a gas backup plan.
The scheme was highly ambitious, as petroleum geologist Dr. Josep Guiner explains.
The Castor wells were drilled to inject the gas and use the oil field as an underground gas storage. The idea was to inject gas, stored for a period of time, and then sell the gas when there was a peak of demand.
The plan was to run a pipeline from the mainland, nearly 30 kilometers along the ocean floor to the abandoned rig, before storing the natural gas in the old reservoir under the seabed.
By pumping gas down into this natural storage chamber, Spain could have a reserve of natural gas of about 286 billion gallons, or 130 billion cubic meters. That could supply the country for 50 days.
While this might sound like an ingenious solution, it's not as simple as filling a gas cylinder for a backyard barbecue.
Gas is difficult to store safely. It escapes unless your container is perfectly sealed. So pumping it into an undersea reservoir with cracks and crevices everywhere sounds risky.
In 2012, a massive rig was positioned above the empty oil reservoir to regulate the flow of gas into or out of the subterranean cavity. But today, there's a 500-meter exclusion zone around the rig, for good reason.
We are now approaching to the Castor rig. We are being told by radio to not go further because it's a restricted area and we cannot get so close. When the company tried to just to make it function and inject gas down the earth, it was a total disaster.
On October the 1st, 2013, residents in southern Spain felt the earth move beneath their feet when a massive earthquake hit. Emilio Valls was at home in the town of Cases d'Alcanar when the full force of the quake struck.
Yo recuerdo personalmente que esto fue una madrugada que estaba durmiendo y en mi propia sentía que la casa temblaba. En esos años yo vivía solo y recuerdo que te va a caer encima porque te asustas evidentemente. Y el mismo gente me dijo que ya había llamado varias personas diciendo que les había pasado exactamente lo mismo, que había notado mucho, se sintieron los seísmos del Castor, ¿no?
Within the space of a week after the initial quake, 15 smaller earthquakes were detected, followed by hundreds of tremors.
The quakes were picked up by Estefania Blanch and her team at the Ebro Observatory, nearly 20 kilometers inland.
Este mapa, estas estaciones, esos triángulos, son las estaciones sísmicas que tenemos instaladas en diferentes puntos del entorno del proyecto Castor. El 1 de octubre de 2013, y lo que vemos fue por la noche, y aquí nos marca una magnitud de 3,9. Después de un cálculo que se hizo más profundo, se vio que este terremoto llegó a 13. Lo que observamos fue que en 2 meses, durante septiembre y octubre, hubo unos 1000 terremotos.
These were the first quakes of this magnitude to ever hit the region, and the finger was immediately pointed out to sea. Gas injections were halted and the project put on hold, while experts determined exactly what had caused the tremors. Dr. Josep Guiner believes there was a fundamental error on a critical calculation.
Well, a project like this basically depends on a single critical factor. And this factor is about pressure. You have 2 pressures. One is the pressure of the reservoir, and the other is the fracture pressure of the seal.
In normal operations, the gas would put pressure on the reservoir walls from the inside, particularly the rock cap at the top, known as the seal. If the pressure gets too high, it will literally break the rock of that seal, allowing gas to escape. That's the fracture pressure.
If this margin is very small, the volumes of gas that you're going to be able to inject are very limited.
Initial calculations estimated that the margin between the 2 figures was a safe and sufficient 20%. But Dr. Guiner believes the maths was flawed.
If you use the same data that the operating company used in this area, you reach a very different conclusion. They established that the fracture pressure of the seal was around 212 bars. And in my opinion, using their same data, my calculation gives you a maximum of 185 bar. The original pressure of the reservoir is 178 bar. So it gives you a very little margin if you accept that the 185 bar is the pressure at which the seal breaks.
The pressure of the gas building up inside the reservoir was too close to the fracture pressure of the rock seal. It caused disturbance in the ocean floor, allowing the gas to escape.
Busting the seal on the reservoir alone doesn't explain the earthquakes. However, for geologists, that was no mystery. The high point on the reservoir where the gas was breaking through was right next to the Amposta fault line.
As the escaping gas shook the seabed, this in turn triggered the Amposta fault line, causing the quakes on the mainland.
What happens is very simple. I mean, it's nothing, this is not rocket science. What happens is that you inject gas, you exceed the fracture pressure of the seal breaks, the gas escapes, the gas goes into the fault moves, and then you have your earthquake.
With the pressure required to store gas so close to the reservoir's natural limit, engineers had only one choice.
A study conducted by engineers declared that any further use of the old reservoir to store gas would most likely result in dangerous seismic activity or more earthquakes.
The only solution here was to shut the Castor station down completely.
Since the gas stopped flowing in 2013, no major earthquakes have been detected. The hope is that the region will go back to its normal stability, and Spain's hunt for a natural gas backup source will continue.
The Spanish government will have to find new and innovative ways to fulfill the energy needs of its population that don't involve the potential for disaster.
In the Netherlands, a construction crane calamity.
I heard metal to metal. It was definitely shocking.
A potentially fatal flaw strikes an iconic San Francisco bridge.
If any one structural component fails, the entire bridge can go down.
In Louisiana, mystery as a massive whirlpool drains a lake.
It's the site of one of the greatest engineering catastrophes in this country.
And tragedy strikes a Florida beachside condo.
I was coming out and saw the condominium physically collapse right in front of me.
With big builds, even the smallest mistake can be a huge disaster. From miscalculations to misunderstandings. Some with deadly consequences. These catastrophes are every engineer's worst nightmare. One basic rule of construction is to check and double-check your figures. Because when engineers miscalculate, the results can be catastrophic. Like this bridge project in the Netherlands that nearly crippled a town.
With this job, small mistakes led to a major catastrophe.
As a complex crane operation went drastically wrong.
I was, of course, very fearful. It was difficult to understand what did I see.
Every engineering student should look closely at this case. What went wrong here could so easily have been avoided.
The low-lying Netherlands are home to nearly 10,000 kilometers of rivers and canals, forming the densest network of inland waterways in Europe. The town of Alphen aan den Rijn lies at its heart. As local journalist Vera Vergunst explains.
The waterways here in Holland are very important to connect the whole country. So this one is the only one you can go from north to south, and it's used by cargo ships, sailing boats, pleasure boats, and the biggest yachts.
With so many waterways, bridges are a way of life.
So this bridge, the Queen Juliana Bridge, is the most important bridge in Alphen because it connects that side of the city to the other side, and it's the only bridge in the center you can pass by car.
It's not just about city traffic. Without this bridge, cargo and large pleasure boats wouldn't be able to take the scenic shortcut that this river offers.
About 20 times a day, traffic grinds to a halt as the Queen Juliana Bridge opens to allow larger vessels to pass through town. Back in 2010, the constant use had taken its toll on the steel, and the decision was made to replace the lifting span.
Now, this meant entire sections of the bridge would need to be lifted by crane and carried to the riverbank. The challenge was how to get the cranes close enough to the bridge.
With the banks cluttered with businesses and homes, engineers decided the best option was to work from the water. Amateur photographer and drone operator Dick van Smieren filmed the project from his canal-side balcony.
It was very spectacular to see in this area the pontoons with the big cranes on it. It was high, it was impressive.
The plan involved two massive cranes, one 700 tons, the other 400 tons, each mounted on a barge. This tandem lift would see the bridge deck lifted from a third barge. And once horizontal, slung between the cranes, the two barges would sail 100 meters to fit the bridge into the existing mounts.
I think a lot of people thought it was a pretty crazy idea to put cranes on pontoons, but I think here in Holland the engineers are like very innovative, and we trust them. So we were like, well, this will be okay.
Since I love filming and photographing, I took the drone and it showed, of course, the impressive perspective of the huge cranes and how those cranes were ready to pull the bridge and take it to its new place.
August the 3rd, 2015, lifting day. The town looked on as the cranes took the strain.
Actually, that day it looked normal, so impressive to see it.
At first, the crane stood perfectly balanced, almost as if frozen. But once the lift started, the picture changed dramatically.
But the first thing where it really was strange was when I heard metal to metal. You would not expect that in so careful operation. And then you could really see the bridge moving, touching the crane. It was definitely shocking. You see that collapse. Of course, you think there are victims. The first thing I did was calling ambulance.
Footage from a security camera reveals just how dangerous the situation was.
Four houses on the water collapsed, and the two other houses on the other side of the street also collapsed because the crane was so big. He destroyed all of the houses, and a lot of other houses were damaged by the accidents.
For the authorities, getting into the houses which the cranes had crashed onto was the priority.
Incredibly, despite 20 people being injured, no one was killed. With cars unable to cross the bridge and river traffic on hold, the authorities raced to get the bridge repaired and to determine exactly what had gone wrong. The town turned to engineering expert Jacques Ertz to analyze the accident. And Jacques turned to Dick's footage.
The drone film from Dick was really useful because it was give a nice overview from all different angles. It really helped to figure out what they were doing on the job site. We started with the data from the lifting plan. After that, we checked condition at site was exactly as what they had planned.
The key problem was in the balance calculations for the delicate and highly complex lift operation.
The preparation, it's quite a lot of engineering to be done, especially in this case with two barges, or actually three barges, and one barge with a load as well. Two cranes, wind, current, maybe even waves. So it's really complex, so you have to do really proper engineering in advance to determine if it's feasible or not.
Major discrepancies between the theory and reality quickly emerged, based on miscalculations of the rig's stability.
Especially on the small barge, there was a lot of additional equipment and material. Also, the ballast condition of the barge was not according to the plan, and all these changes reduces the stability.
The inherent instability of the barge with the smaller crane caused it to list to one side. The excessive sideways forces buckled the crane's mast, which toppled, pulling the bridge deck and the larger crane with it.
They have done some preliminary checks in the beginning of the project, but during the engineering, a lot of Small things have changed. Small errors or changes in the engineering can lead to major accidents.
Leaving the town without its only vehicle crossing wasn't an option. So the authorities planned a second lift operation. This time, nothing could go wrong.
For the second attempt, a bespoke floating crane was used. It's an expensive option, but one which hugely reduced the risk of a disaster.
The bridge was finally operational nearly a year late and thousands of euros over budget. But for residents, the reopening was a huge relief.
The town was, I think, very happy when the bridge was finally reopened, because it was really missing in the city center.
When engineers push boundaries, sometimes the danger comes from the outside. But other times, even the mightiest of structures can be threatened from the inside. Like this construction calamity in California, with an engineering marvel that came dangerously close to catastrophe.
One of America's most iconic bridges could have been one snap away from collapse.
A cutting-edge design that could have turned into an epic engineering disaster.
The design defect could have brought the whole thing crashing down.
San Francisco is home to some of the West Coast's most iconic postcard views.
I love San Francisco. It looks stunning, it has culture, amazing architecture, and of course, an endless, beautiful waterfront. In fact, the city is surrounded on 3 sides by water.
All this water means one thing: bridges. The Golden Gate is the city's most famous bridge. But there's another here that's a far greater feat of engineering. The San Francisco-Oakland Bay Bridge, better known simply as the Bay Bridge. It's the city's most important crossing, as engineer Andrew Freemier explains.
The San Francisco-Oakland Bay Bridge by itself is the biggest workhorse of all of the 8 crossings that are in the San Francisco Bay Area. And so on an average day, hundreds of thousands of people commute across that bridge. And it's very important for the community and for the economy for that bridge to stay open and operational.
When it was built in the 1930s, the Bay Bridge was the longest and most expensive bridge in the world. But in 2013, a radical, unique middle section opened. Although just a fraction of the length, it alone was California's most expensive public works project ever. With an iconic single tower topping 160 meters and a span of more than 380 meters, this is the longest self-anchored suspension bridge in the world. Bridge engineer Brian Maroney helped build this epic structure.
Here we are at the top of the tower of the self-anchored suspension bridge. If you look to the west, you see the beautiful skyline of San Francisco. And as a bridge engineer, looking at the on and off ramps and the Bay Bridge going in and out of Yerba Buena Island Tunnel, very exciting.
It's not just the view that sets this bridge apart from its peers, but the way that it works. Unlike a conventional suspension bridge, which has 2 cables anchoring it to each side of the crossing, a self-anchored suspension bridge is entirely supported by a single cable. Here, it forms an open-ended figure of 8, supported by the single 160-meter tower.
One of the most challenging parts of this entire bridge is the cabling system of the self-anchored suspension bridge. The anchorage is on the east end. It comes up the top of the tower, continuously goes around, wraps around, comes back up to the top of the tower, and then comes back to the other side of the east anchorage. The entire length is over a mile, so it's a long cable.
The cable consists of 17,000 individual wires bundled together and anchored at the Oakland end of the bridge.
We're here at the east end of the self-anchored suspension bridge, deep within, inside the superstructure. This is the splay chamber. This is basically where all of the cables come down and anchor. So the parallel wire strands, each one of them, even though it's approximately about a meter diameter main cable up on the bridge, they splay out here in the splay chamber, and you see all these parallel wire strands, and they splay out into smaller groups of wires. They get cast into what we call a socket. Then the socket is screwed into a rod, and the rod goes all the way back against an anchorage. That's a heavily, heavily reinforced steel wall, and it's screwed in tight.
This unique bridge wasn't just built to break records. The radical design is to combat something San Francisco is famous for: earthquakes. Journalist Charles Pillar explains.
We live in one of the most earthquake-prone environments in the world. There's two major earthquake faults that are adjacent to the Bay Bridge and affect the Bay Area more generally: the Hayward Fault, which is just in the East Bay Hills, and the San Andreas Fault, which is closer to the coast. Both of these are faults that have had major earthquakes in the past, and in particular, the Hayward Fault is thought to be likely to have a major earthquake, possibly quite soon.
In 1989, the San Andreas Fault triggered the massive Loma Prieta earthquake, and a section of the Old Bay Bridge slid from its supports. Engineers realized the entire section was vulnerable because it was built on soft mud. So, when the new span was built, the solution was to have a single tower standing on the only solid rock in the area.
This self-anchoring method means the cables are attached to the end of the deck rather than the ground, which means the structure has much more flexibility in an earthquake.
The self-anchoring section of the Bay Bridge was built to survive an 8.5 magnitude earthquake. But something significantly smaller almost sent it crashing into the bay. In the 1989 earthquake, the section of road deck that collapsed had been shaken from its supports. To prevent that from happening with the new bridge, the decks are joined to the legs using connections called shear keys. Engineer Brian Maroney explains.
Shear keys are devices that hold on either side of the bearing to keep the superstructure from sliding.
The Bay Bridge shear keys have two parts: a 3-meter square base bolted to the eastern pier by steel rods over 7 centimeters wide. This links to a second plate on the road deck above, allowing movement much like a trailer ball hitch. As well as coping with everyday loads, if an earthquake hits, the design allows the two parts to shake independently without causing damage. Although engineers didn't know it, long before the bridge was complete, trouble was brewing in these crucial connections.
The shear key rods were concreted in place in 2008, but the giant nuts couldn't be fully tightened until the bridge above was constructed too. This was a massive project, so the bolts sat there untightened for 5 years.
And when the nuts were finally tightened, 32 of the steel anchor rods fractured immediately. This massive fail left the bridge vulnerable.
Had an earthquake hit, the very elements designed to protect it could have led to its ultimate destruction.
Metallurgical engineer Lisa Fulton investigated this potentially catastrophic problem.
This bridge is what is known as a fracture-critical bridge, which means that any one structural component, if one fails, the entire bridge can go down.
Despite the structure's super size, the failure was caused by a microscopic problem known as hydrogen embrittlement. It's a type of corrosion where hydrogen atoms diffuse into a metal structure. As the atoms slowly recombine into hydrogen molecules, they form a gas that creates pressure inside the metal. Ultimately, the rods become brittle.
hydrogen enters the steel and has an embrittling effect on the steel. So embrittlement is when something breaks without absorbing a lot of energy.
Even under very little pressure, hydrogen embrittlement can make steel snap. With a massive force, like the shaking of an earthquake, any brittle steel would be a serious risk.
With the discovery that the shear key rods had failed, people were obviously worried that other steel bolts and even the main cables themselves might be at risk.
This bridge is an amazingly unique creature. The question is whether this self-anchored span, this unique design that is replicated at this scale nowhere in the world, whether it can withstand the strongest level of quake that could occur on the Hayward or San Andreas Fault. And Caltrans says yes. We've done our computer modeling and we feel confident of it. Of course, on the other side are many engineers who doubt it and who question it.
If the officials say the bridge is safe, you just have to trust them. But had the main cable been vulnerable, with this type of bridge, it couldn't be replaced. There would have been no choice but to tear the whole thing down and start over.
This is the cable that holds up the suspension span. It's crucial that there not be any corrosion on it.
What was not in doubt was that 32 of the shear key rods had fractured. If a quake hit, no one could be sure what would happen to the other rods, and engineers didn't want to find out. The rods couldn't be replaced, so they worked round the clock on an alternative solution to hold the shear key in place.
What we did is we created a saddle, just like a saddle that you put on the back of a horse, and then we strapped or pulled down, cinched down that steel saddle, and then pre-stressed it and tightened it.
A pair of steel clamps called saddles were fitted over the sides of the shear key, with multiple steel rods and cables holding them in place, effectively strapping the shear key to the bridge leg. Whatever happens to the rods, the shear key isn't going anywhere. Finally, in 2013, the revolutionary new eastern span of the San Francisco-Oakland Bay Bridge opened to traffic. It was 10 years behind schedule and billions of dollars over budget, but San Francisco had added another striking bridge to its collection.
This ended up being the most expensive bridge ever built in America, but it could have been one of their costliest construction catastrophes.
When engineering goes wrong, the cause of the calamity can be huge and obvious for all to see. But sometimes the simplest mistakes can have devastating consequences. Like this mystery in Louisiana and a massive lake that vanished.
A tiny miscalculation changed the entire landscape forever.
Once this epic engineering fail started, there was no stopping it.
This catastrophe quickly spiraled out of control.
It's the site of one of the greatest engineering catastrophes in this country.
Louisiana, home to the Big Easy and endless bayous, where the mighty Mississippi River meets the ocean.
When I think of Louisiana, I think of swamps and lots of water. There's the long coast beside the Gulf of Mexico. It has vast bayous threading through the Mississippi Delta and endless lakes in between.
For thousands of years, the river has dumped layer upon layer of sediment to create a vast flat landscape. Geologist Tim Dukes has been studying the ground here for decades.
We're located in what is called the Gulf Coast area, the coastal plain, generally pretty flat.
Although the state is mainly flat, geologists like Tim have found the occasional mound that hints at something precious lurking beneath the surface.
These places are irregularities in that because they're salt domes and topographically higher, significantly higher. There are literally hundreds of these salt domes that are found in Louisiana and thousands that are found in the Gulf Coast. Around the edges of these, there are a lot of areas where drilling for oil and gas can take place, and it's been pretty prolific.
Oil and gas have a dirty reputation, but they're both completely natural. Basically, the remains of billions of tiny plant and animal plankton that have been pressure cooked deep beneath the surface. The resulting stew is oil and gas. Because of the way they were formed under the ocean, oil, gas, and ancient beds of sea salt are often found together.
Over millions of years, salt forces its way up from deep in the Earth's crust towards the surface and forms salt domes. These domes create natural underground pockets that trap the oil and gas that formed below them.
In the 1970s, prospectors were drawn to a salt dome on the western edge of the Mississippi Delta, the so-called Jefferson Island, on the banks of Lake Peigneur. Tim was here in 1980 when engineers were searching for oil.
We're located on the shores of Lake Peigneur. There was a drilling rig that was located out more or less in the center of the lake, and they were drilling supposedly around the edges of this salt dome.
Michael Richards Sr. was working on Jefferson Island at the time.
When I came to work here in 1969, we used to mow grass between here and the pilings. There was a grove of pine trees right here.
On November the 20th, 1980, as the rig drilled into the lakebed, the drill jammed solid, and Michael grabbed his film camera.
Soon after the drill bit became stuck, the whole rig started to tilt. The rig workers knew that something was seriously wrong and evacuated the rig. After they reached the shore, it soon became clear they'd had a lucky escape.
The rig quickly disappeared through the lakebed, and a giant whirlpool formed where it had stood just minutes earlier.
Once a whirlpool had formed, the spinning water rapidly eroded a hole in the bottom of the lake. Although small, it was big enough to suck in the whole lake.
Michael continued to film.
We were standing on the porch on the second floor of this house that you see here that's sunk about 30 feet, looking down on the lake and watching the barges rolling around, a tremendous vortex. And then at one time there were 3 different vortices, each one turning and swirling.
The lake was rapidly being sucked underground, but the force of the whirlpool soon started dragging more than just the water within. In addition to the water, about 65 acres of Jefferson Island also disappeared through the lakebed.
The land in the bottom of the lake was peeling off in great layers like a cake. And behind us, the water was liquefying the soil. And in that direction where there were trees, the trees were holding, the roots of the trees were holding the soil. So the soil slipped and the trees laid down. You can still see the tops of some of those trees today.
Michael discovered that filming on location could prove deadly.
Sheriff's Department came in and told us it's time to go. So we left. And not long after that, the house and all this land slipped in. The progress started moving in this direction.
With Lake Peigneur no longer a lake and a huge part of Jefferson Island missing, everyone was left asking, where on earth had it all gone?
Jefferson Island was the surface evidence of a salt dome, which is why rig workers were looking for oil trapped beneath the salt. But as they knew all along, there was also a massive salt mine being excavated beneath the island. In fact, it was about the size of a skyscraper.
The salt mine was at considerable depth, several hundreds of feet. I think the deepest level was down to 900 feet, and it was an active mine at the time. They were pulling out salt. This is an example of what they were after.
It turns out that instead of discovering oil, the rig had inadvertently drilled through the roof of the salt mine.
Because of the safety conditions that were present and the procedures that they had established, all of the miners were able to get out without anybody being injured or killed.
This explained where all the water had gone, but not why the rig had drilled into the salt mine in the first place. After all, it had been known about for 60 years. According to geoengineer David Wilshaw, it was all because of a very simple but catastrophic mistake.
What happened is basically they got their calculations wrong about where to put the drill rig and where to drill the oil exploration well. They were out by a few hundred feet. So they never anticipated drilling into the salt. They were looking for the oil and gas deposits that sit around the salt dome.
When deciding where to drill, the engineers used a method called triangulation. Basically, angles from two or more fixed points are used to locate another point. The problem was they made a mistake in their calculations and drilled in the wrong place.
That small error might have made the difference between finding oil and this massive disaster. Thanks to modern technology, it's a mistake that would be unlikely to happen ever again.
Today we have GPS. Back in 1980, it wasn't so simple. They didn't have the satellites that we use. I mean, we could probably avoid doing that just using our phone today, but you can't turn back the clock. You can't see what the technology they had there. Would it have been avoidable if it had more, obviously precise instruments? I'm sure it would have been.
This minor miscalculation not only wrecked an oil rig, it also brought a watery end to a fully functioning salt mine. But it was an unexpected new beginning for Lake Peigneur.
The suction created by the whirlpool was so strong, the canal that used to flow from the lake into the Gulf of Mexico reversed, basically refilling Lake Peigneur with seawater.
After a considerable amount of time, the waters came back up, all the barges popped back to the surface, and the lake kind of achieved its present level.
Lake Peigneur is now 20 times deeper, and Jefferson Island is significantly smaller.
All of this land slipped in. It's unbelievable, the magnitude of this catastrophe.
With this blunder, there really was no solution. The disaster permanently changed the landscape. The sea refilled the lake and the mine was lost. It just goes to show that when it comes to engineering, getting your calculations correct really is essential.
Some engineering fails lurk hidden for years after the construction crews have left the site. But with others, the fail strikes before the job is done. Like this condominium in Florida, and an engineering error with truly tragic consequences.
This real-life disaster was set in motion right from the drawing board.
Saw it actually physically collapse right in front of me, and you just saw a huge, huge ball of dust.
A fatal failure that forced the engineering industry to re-examine the rule book. Florida's seafront city of Cocoa Beach is sandwiched between the Atlantic Ocean and the Banana River. Famed for its long sandy beaches and one of the world's largest surf shops, this town actually owes its existence to America's space program. Local Florida engineer Julie Keller explains.
Close by to this area, we have the Kennedy Space Center, which brings in a lot of science and engineering people and needs the availability to house them.
In the 1980s, with NASA's shuttle program in full swing, Cocoa Beach was busy building.
There were building booms back in the 80s and the 90s, and anytime you have a building boom, there's always a need for construction to be done faster and at a quicker rate.
In December 1980, to keep up with demand, work started on a new 5-story condo, the Harbour Quay. Although it was never completed, it would be built like many other condos across the country.
We are headed to the site where the original Harbour Quay condo was supposed to be built. This would have been a prime piece of real estate to put a 5-story condo on. What we have here is an example of what the Harbor Quay could have looked like. So this building is typical of the area. It's a condo that's 5 stories high.
Each level would be made up of large flat slabs, held up by columns. To maximize internal space, there would be no additional horizontal beams. The slabs would be strong enough to support themselves.
Concrete is great for construction. It's very strong as a supporting block, but when it's used as a floor or roof panel, it has to be self-supporting. That calls for serious reinforcement.
Setting steel bars inside concrete is key to structural strength. The concrete resists squeezing or compression, while the steel resists bending or tension. But to work properly, the exact height of the bars is critical. With Harbour Quay, the plan was to use a process called reinforcement chair design.
So what we have here is an example of what you would see on a typical construction site where the slab is being poured. And you would have these form boards, so it would make the mold of where the concrete's gonna go. The location of this bar is critical in the placement of the slab because all the calculations are based off of where this bar is.
The idea with the chair system is to hold the rebar at exactly the right height. If those measurements are out by even a couple of inches or centimeters, the whole thing can come crashing down.
3 months into the project, on March the 27th, 1981, the construction team was pouring concrete to create the roof 5 stories up. But shortly after 3 p.m, the build went drastically wrong. Kent Fay was 20 at the time, working as a lifeguard just across the street.
On that day, I was leaving work to head over to have my paycheck cashed over at the local bank. And as I was exiting, was coming out and saw the condominium, Harbor Quay condos that they were building, saw it actually physically collapse right in front of me. And you just saw a huge, huge ball of dust.
The collapse happened so fast that there was no warning for workers.
I quickly ran over there. I got up on the scene. I was dealing with people that were severely, severely injured. There was a young man on the ground that was actually in shock. They went and got him up and had him help me start attending to people that were injured.
Residents and construction workers rushed to the scene to join the rescue mission, quickly followed by airmen from the nearby Patrick Air Force Base. 23 workers were injured, but despite the rescuers' best efforts, tragically, 11 died. The disaster left the community reeling and demanding answers. The obvious question was why had the Harbour Quay condo collapsed without warning? Within an hour, a team from OSHA, the Occupational Safety and Health Administration, was on site to investigate.
According to official reports on the accident, investigators found clear evidence in the wreckage of what had gone wrong.
The investigation discovered a number of failures, most notably in the reinforcement chair design. Engineer Julie Keller explains.
The reason that this is critical on this particular condo is that the steel not being in the right location was found to be because these chairs were not the right size. The chairs were not the right size because the engineer signed off on the shop drawings showing the chairs in the incorrect size. And that led to the steel being under so much stress that every time you put another floor on it, there was additional stress on the condo. So it led to a brittle failure.
Brittle failure is when concrete cracks suddenly and without warning. As structural engineer R.N. Silapan demonstrates.
In this test, we are going to be determining the flexural strength, the bending strength of concrete. Right now, we have applied a load of over 5,500 pounds. Now it's way over 6,500. These concrete specimens are expected to break with a bending strength of about 500 or 600 psi. As you can see, this beam was tested to failure. However, this is not how it is in the field. In the field, when we're actually constructing a building, you would have reinforcing steel in there, which greatly enhances its capacity.
But the brittle failure in the concrete wasn't just the result of the steel being positioned incorrectly. The original design didn't call for thick enough concrete in the first place.
Even though this bar should have been down here, the slab was designed to be 8 inches thick. So that's what the engineer had done in design. But the American Concrete Institute has a code which says that a flat slab supported on just columns should be 11 inches thick. So the distance between the compression and where this bar should have been, that critical number that was in the calculation, should have actually added 3 inches, not just the inch that was lost due to the chair size.
Typically, in order to increase the bending capacity of beams and slabs, the steel is placed in the lower portion of the cross-section. But in Cocoa Beach, it was placed almost at the midpoint, which effectively does not contribute to increasing its bending capacity, because as you can imagine, when this beam bends this way, the bottom is in tension and the top is in compression.
Concrete works really well in compression. It does not work well in tension. A teacher a long time ago told me that if you join your hands together, you can see the example from if you push on your hands, you see your skin wrinkles on top, and that's compression. So you can see that happening, and then you look under your hands and you can see the skin stretching, and that's tension. And that's where the cracking forms, and that's why this needs to be in the correct location in order to do its job.
It seems that there were multiple miscalculations. The chair size was out, the thickness of the concrete was wrong, and the calculations in the original drawings were based on rebar that was 1/3 stronger than the steel used in construction.
The calculations were wrong on every floor, so as each was being completed, the problem was being compounded. It was just getting worse and worse.
Ultimately, these factors combined as the 5th floor was being poured, leading to a failure known as punching shear.
With the rebar set too high, the bottom of the panels were being overstressed. When the concrete fouled, the panels fell, but in effect, it was the support columns punching through the concrete.
This type of failure happens in reinforced concrete slab structures. Where the columns support the slabs, they're subjected to very high forces. In this case, the slabs failed at these crucial points, and with no support, the structure collapsed.
They continued to build, and then when they put the 5th floor on there, it just failed suddenly.
There were mistakes at every stage, but by getting the numbers wrong at the design stage, this project was doomed from the start.
Although it was too late for the workers who lost their lives, the Harbour Quay condo collapse led to more rigorous enforcement of engineering and construction codes in Florida and across the United States.
It's critical that engineers learn from tragedies like this to help prevent anything like it from happening again.
skyscraper threatens to rain solid rock down on Chicago.
A small piece were to fall from this building, it would cut through the air like a knife.
Tragedy strikes a groundbreaking Vancouver bridge.
When I got there, it was chaos. There were rescuers combing through the wreckage of the bridge.
A Danish demolition catches everyone by surprise.
Everybody was in shock.
And in California, a railroad calamity with devastating consequences.
There was the engine laying on its side, and I observed numerous cars in the river.
With big builds, even the smallest mistake can be a huge disaster. From miscalculations to misunderstandings. Some with deadly consequences. These catastrophes are every engineer's worst nightmare. When engineering goes wrong, the cause of the calamity can be huge and obvious for all to see. But sometimes gigantic projects can be threatened by the smallest of flaws. Like this building in Chicago, where a beautiful addition was an ugly catastrophe in the making.
This could have been deadly for people on the streets below.
A layer of heavy marble covering the outside was a lethal disaster waiting to happen.
We're up there on the side of the building. We are shocked at the condition of the marble.
This building was designed to have high impact, just not like this.
The Windy City has long been famous for its bold architecture. With a skyline dominated by massive skyscrapers, the city has been home to the world's tallest building more than once.
For more than 100 years, Chicago and Manhattan have battled each other for the title of the greatest skyline, which usually meant the tallest building.
By the 1970s, thanks to huge leaps in structural engineering, Chicago led the world in skyscraper design. Master stonemason Robert Gerskis spent 3 years working on one of the city's tallest towers.
All right, here we go, ladies and gentlemen.
Although few know the story, Chicago's Aon building has a very dramatic history.
Chicago traffic helicopter 1 by X-rays.
Completed in 1973, this 83-story skyscraper was the Standard Oil Company headquarters, known locally as Big Stan.
Beautiful, beautiful. Very nice.
When built, it was Chicago's tallest building and the 4th tallest in the world.
This is the building right here, formerly known as Standard Oil Building, 137 feet off the hard deck all the way up to the top. Right now, we're approximately 1,200 feet above ground level, and the views are spectacular. Totally awesome.
Big Stan wasn't just super tall. In engineering terms, it was a trailblazer. As architectural historian Rick Keel explains, it pioneered a new structural system.
The Aon Tower actually has the frame of the building and the support of the building in the outside wall. And the outside wall forms a giant square tube that goes up into the sky.
For decades, most towers were supported by columns spread evenly throughout the building. But for Big Stan, architects placed steel columns in tightly packed rows around the outside, known as a tube frame, with a central core of columns.
That tube is then tied across between the floors to the center elevator core, which gives it more strength.
Tube-framed towers could resist greater lateral forces from high winds or earthquakes than their predecessors, allowing them to grow taller. With Big Stan, the columns were long, slender triangles running the full height of the tower, interspersed with narrow windows. But the architect had bigger plans beyond the revolutionary steel skeleton.
As well as innovating the internal structure, the architects wanted to create an iconic exterior that truly shone in the skyline.
That shine came from one of the most ambitious cosmetic jobs since the Great Pyramid of Giza. All 83 stories of steel would be covered with top-of-the-line Carrara marble from northern Italy. As material scientist Laura Powers explains, marble has a long history in construction when appearance is a priority.
Carrara marble is a wonderful stone. It was Michelangelo's marble of choice for sculpting because it is so pure, it's very predictable when you're working with it. Because it is such a special stone, when someone wants to make a statement, they'll use Carrara marble.
Marble can be highly polished and solid blocks will last centuries. But structurally, Big Stan didn't need any more support, and so the outside was purely aesthetic.
To achieve the designer's intended look, Big Stan took advantage of the latest engineering advances in rock cutting. The plan was to cover the triangular columns with thin sheets of marble, just over 3 centimeters thick, running from street level to the top, 83 stories above. In all, it took 43,000 panels, each weighing as much as a motorcycle. In 1973, when Big Stan opened its doors for business, it was the tallest marble-covered building in the world. But just a decade later, the shine began to fade. Routine inspections revealed that the slick marble coat was cracking and in danger of crashing down to the ground. This is where restoration specialist Robert Gerskis came in. He captured this unique footage as he assessed the damage.
We're up there on the side of the building. We are shocked at the condition of the marble.
The fear was that the sheets of rock, as heavy as 2 men, could have fallen from 80 stories up.
As early as the construction phase, there were reports that the marble was not secure.
It's reported that on Christmas Day in 1973, one of the slabs fell from Big Stan, and it pierced the roof of the neighboring office. The fact that it happened on a public holiday might have been a blessing in disguise.
This is the actual piece from the Aeon buildings. Full panel, typical panel is like 4 foot by 5 foot. This is about 11-pound piece right here. 1,000 feet up in the air, all the way down to the ground. This would do some serious damage.
So, why was the same type of marble that had lasted over 500 years in Italy struggling after less than 20 in Chicago? It seems thin sheets of marble and the Chicago climate were a bad combination. Structural engineer Michael Scheffler analyzed the damage in the 1980s.
Well, it had proven the test of time in Italy. Italy has a very benign environment. Chicago has a much different climate than Italy. In Chicago, in the winter, you can get below 0, and you can get up to 100 degrees. And this had a profound effect on the material's behavior.
The problem was something called thermal hysteresis, which basically means an irreversible bending or bowing out of a panel caused by temperature change.
With the building known as Big Stan exposed to the extremes of Chicago weather, the outside of the panels were repeatedly heated or cooled more dramatically than the inside. This gradually and permanently altered the internal structure of the marble, causing the panels to bow outwards.
They were beginning to warp and pronounced bowing outward as much as 1.5 inches at the center of the panel in a 4-foot 2-inch height.
But thermal hysteresis wasn't just bowing the panels. As they deformed, they became more vulnerable to extreme weather.
To make things worse, that weakness was allowing water in, which was doing even more damage as it froze and expanded in Chicago's winters.
Carrara marble is composed almost entirely of calcite. Because the calcite in this marble expands in one direction more than it expands in another direction, it breaks the contacts between the crystals, so water can get in. And in a climate like Chicago's, when water gets in and subsequently freezes, the expansion of that water can tear the stone apart. These two images from the microscope show Carrara marble. The image on the right is showing Carrara marble that has never been exposed to thermal cycling or to freeze-thaw cycles. And the one on the left shows Carrara marble that has been through thermal cycling. This is similar to the marble cladding on the Aon building. So in the damaged marble on the left that has been through the cycling, the heavier blue lines are showing microcracks that are attributed to freezing and thawing distress.
Many of the panels were experiencing cracking and spalling at their connections. It was revealed through testing that the material had lost, in some cases, as much as 90% of its strength.
Not only did it spoil the clean lines, but there was a real risk that the panels could literally pop themselves off the building.
In the 1980s, with the cracking on the marble facade getting worse, something had to be done to protect the people below. A very temporary solution was found until a complete redesign could be put into place. Stone restoration specialist Robert Gerskis explains.
This building was a total challenge because we had to put on straps on over 43,000 pieces of marble. If it wasn't for the straps holding on to marble on the side of the building, we would have a huge problem. Pieces probably would fall off.
The ultimate solution was just as bold as the original design. Robert was one of the master stonemasons tasked with replacing all 43,000 heavy marble panels.
This job was just massive in its undertaking. This is the largest, probably the biggest recladding job, the tallest recladding job in the world at the time.
The audacious plan was to recover the entire building in a much tougher Chicago weatherproof stone, granite.
We started recladding in 1988. We had to take off 43,000 pieces of marble and replace it with 43,000 pieces of granite, all done on the outside, and the building is still occupied. They did not shut down the building. So the people that worked on this building had to be the best of the best in the business.
Replacing the heavy panels more than 300 meters up in high winds was more than just a technical challenge for Robert and his team.
And sometimes we had to contend with very, very high winds. It was very, very scary. You had to be aware of your surroundings. And with that being said, courage is learning how to manage your fear.
By 1992, after nearly 4 years, the biggest renovation on one of the tallest buildings in the world was finally complete. None of the precious marble went to waste. It was crushed and used to landscape a nearby oil refinery.
Replacing the thousands and thousands of panels is said to have cost $80 million, nearly half the original construction cost. But nearly 30 years later, the cladding is still going strong.
While the drastic solution was expensive, it was a huge success. And since Big Stan's original high-class cladding catastrophe, architects and engineers no longer use Carrara marble for external coverings anywhere in the US. With big engineering, overcoming gravity is always a key consideration. But when your very stability is under threat, every calculation is vital. Like this bridge in Canada, which was hit by a disaster that left a nation reeling.
This was the worst industrial accident in Vancouver's history.
An engineering catastrophe with devastating consequences.
Had I been there that day, I wouldn't be here today.
This tragedy left a lasting mark on everyone involved.
If I wake up, I can still see that, even after 62 years.
Vancouver, on Canada's Pacific coast, is a bustling seaport. It was established in 1792 by George Vancouver, around the natural harbour he named the Burrard Inlet.
The Burrard Inlet is a shallow fjord carved by ice that separates downtown Vancouver from the Pacific mountain range to the north. It's a sheltered inlet and ideal for shipping.
To keep things moving on and off the water, bridges have long crossed this busy shipping lane.
There have been bridges across this stretch of water since the 1920s, but all have proved problematic.
The main flaw was with the section between the main supports, the central span of the bridge.
The first bridge was hit by several ships. One even got wedged beneath it, ripping away its center span.
Repaired and reopened, the new bridge had a center lift span, which brought problems of its own.
The new span had a lifting mechanism to allow ships through, but became legendary for its traffic delays. In 1 year alone, the central span was raised over 5,000 times.
By the 1950s, it was clear that a completely new bridge was needed. Luc Lessard moved to town to work as a foreman on the new crossing, called the Second Narrows Bridge.
In 1957, I moved from Quebec to Vancouver. The beauty of Vancouver, when I arrived, I was amazed. The purpose of building a new bridge, the Second Narrow Bridge, was because the traffic increased, plus the boat and the ship coming underneath, they were getting higher and bigger all the time, and they need more water clearance.
The best solution for both increased traffic and larger ships was a cantilever bridge.
A cantilever is effectively a bridge where each span is only anchored or supported at one end, while the other end projects out like a long arm across the water until it meets the section from the other side.
Yet this one was a little different. Many cantilever bridges stand on large supporting piers with the steelwork pointing skywards. But here, to get maximum height for shipping, this one was effectively flipped upside down, with the road deck running on top.
The new design did away with both the problems of its predecessor. It would be high enough to allow large ships to pass underneath, while traffic could continue to flow on the road above.
At the time, Peter Hall was a young draftsman when he was asked to film the construction.
I didn't own a movie camera, and never having used one before, I borrowed one from one of the fellows in the drawing office.
Building this towering structure was no easy feat. Luke and his team of ironworkers were often doing back-breaking work more than 30 meters in the air, and Peter was right up there with them.
The work of a bridgeman or an iron worker is a very dangerous job because most of the time we work on the air. Any fall, we know that be our life. And those days especially, we did not use a safety net or cable or tie down. We were completely free walking on any piece of the bridge.
Back then, men were walking across steel beams high in the air with no safety nets, no harnesses. This was a seriously dangerous occupation. These workers put their lives on the lines every day.
One of the biggest challenges for the ironworkers was that this type of bridge is unstable during construction.
The benefit of a cantilever bridge is that once complete, it's strong and stable enough to cross a large expanse of water. But the downside is that they're tricky to build.
With this upside-down cantilever, Vancouver's second Narrows Bridge couldn't support itself until each span was complete. So workers installed temporary structures called falseworks to support the span. Once a span was complete, it was fully self-supporting and the falsework would be removed.
This was going to be a jewel in the crown for construction in Canada. But then things went very wrong.
As Vancouver's new bridge took shape, on June 17, 1958, foreman Luc Lessard and his team were lifting a 55-ton section into place. Less than an hour before quitting time, without warning, the span collapsed. "79 workers, including Luc, fell more than 30 meters into the water."
We heard a big noise. So the bridge went down underneath our feet. First thing I remember, I was on the bottom of the ocean, 35 feet below the top of the water. Then I finally saw a light coming up from the sun through the water. I managed to get above the water. My leg and my arm was broken.
Peter Hall was lucky. He'd been called to the office earlier that day.
June the 17th, 1958. Started out like any other day. I was able to see the bridge from the top of the hill. And as I looked at the bridge, it was in the water. When I got there, it was chaos. There was bodies in the water, bodies trapped in the steelwork. I just couldn't film a lot of what I was witnessing. A lot of the people that were being brought off the bridge, I classed as friends.
Despite breaking his arm, leg, and his back, foreman Luc was one of the lucky ones. 18 of the 79 workers that fell that afternoon perished. In the wake of the tragedy, the official report concluded that there was a design and calculation error in a crucial part of the falsework. It seems the layout of the temporary arm beneath the fifth span of the bridge was fatally flawed.
The steel was bracing the heavy span of the bridge until a new section was fitted, but the exact layout of the falsework wasn't stable enough to support the weight of the incomplete bridge above.
As the new section was being moved into place, the falsework gave way, taking that whole section of the bridge with it. Bridge engineer Daryl Matson explains further.
The steel had lots of strength, but it lacks stability. There is no set calculation method for falsework short of it has to be big enough to hold the load and it has to be stable.
The heart of the problem was using a row of beams as a base for the falsework.
This is very much like if you take and you stack a whole pile of blocks one on top of the other. There's not really a strong connection between the blocks, and eventually they'll fall over. This is the same thing where we have the bridge sitting on top of a block, which is this column, sitting on top of another block, which is the beams. The problem with this is that there wasn't any stability to that lower block. Like, it wasn't even like I have a block that's this big that takes a bit to roll. They're very thin webs that just rolled over and flopped over.
This was the worst industrial accident in Vancouver's history, and one which perhaps could have been avoided with a relatively simple solution.
Had they put bracing in at 4 locations, one on either side, either truss, and one at the support of the foundation and one at the support of the column, had they put 4 sets of bracing in, that's all it would have taken.
It's easy to say with hindsight, but it seems like a relatively minor adjustment could have prevented a major catastrophe.
The bridge was rebuilt and finally opened in 1960. In 1994, to honor the workers who lost their lives, it was officially renamed the Iron Workers Memorial Second Narrows Crossing.
Often in my mind, at night, I can see what was happening. I can still see that, even after 62 years.
120,000 vehicles drive over the bridge every day, which is both a tragic reminder and a testament to some truly courageous men and all that they've achieved.
With big engineering, the devil is in the details. Numbers are checked and double-checked. But sometimes even the best laid plans can go awry. Like this precision project in Denmark that took everyone by surprise.
When you're using more than 20 pounds of high explosives, you really hope you've got things right.
In 2018, a landmark demolition blown completely off course.
It stopped, and then it was going the wrong way, and everybody was in shock.
Experts and residents were left wondering what had gone wrong.
It's safe to say this demolition did not go to plan.
Vordingborg, in the south of Denmark, is an ancient port town and home to some iconic Scandinavian architecture.
The picturesque old ferry town of Vordingborg has buildings that date back to the 14th century. The Danes know how to build things at last.
As the shipping industry grew, so did the port, which was relocated to a new site across from the town's waterfront.
In recent years, the port has undergone massive development. The ambition is for the town to be one of the largest grain exporters in Europe.
The waterfront has long been towered over by a giant silo. The 53-metre tall structure was built strong to be able to contain the massive weight of hundreds of tons of grain. Like most silos, it was built as a cylinder.
The cylinder distributes forces evenly around the outside, allowing them to withstand much greater pressure than square shapes.
As the new industrial port was being developed, the old harbour, with its standout silo, was also in line for a makeover. Local journalist Kim Eriksson covered the story.
There's a lot of development in Vordingborg area with new bridges and new railroads. The silo hasn't been used for many years. Before it was used for animal feed. Because of development of the area, it was decided to demolish it.
A strong and stable cylinder is ideal for storage. But when the time comes for demolition, they're complicated structures to bring down.
Most buildings are held up by supporting columns that can be blasted away and the whole thing collapses like a concertina. But silos have solid walls with no natural weak points for blasting.
There was an added layer of complication. The silo stood next to the town's cultural centre and library. It was critical the tower fell in the right direction. So, like felling a tree, demolition experts chopped a wedge in the side, planning to force the silo to fall away from its neighbours and into a specially prepared landing zone.
Demolition by implosion might seem like the easiest way to knock down a structure, but with such a tall cylinder, the smallest mistake could escalate out of control.
Silos are very strong as complete structures, with the forces all nicely balanced. But like all cylinders, as soon as you remove a piece that disturbs the balance of the entire structure, it becomes unstable and unpredictable.
The blast was so complex, explosive experts spent 6 months preparing. April the 9th, 2018, Demolition Day. With cameras rolling, engineers cleared the exclusion zone.
On the day of the demolition, everything seemed to be okay, and there was a big safety area, and there was 2,000 people, I guess, over here and over on the other side of the sea. Everybody was very excited about it.
At 5 o'clock, the explosives were detonated.
When this explosion happened, the silo actually went the right way for a few seconds. And then it stopped, and then it was going the wrong way, and everybody was in shock.
Not only had the silo fallen the wrong way, the force of the impact had crushed the end of the library and cultural centre. Thankfully, as firefighter John Hansen discovered, the exclusion zone had kept people safely out of danger.
There was no people at this time in the building. Everyone who worked at the building have gone to home for holidays. It was good luck that nobody was hurt at the time.
The disaster was the talk of the town, and with the cultural centre in ruins, residents wanted answers.
With all that planning, it should have fallen neatly into the landing zone, but clearly something went horribly wrong.
So, why was the silo blown so spectacularly off course? Professor of Engineering Per Gulterman has a theory to explain the chaos.
What I have here is a model of the Vordingborg silo. We have removed some of the concrete and we are going to blast it. I'll use my blasting finger here. We'll remove that, and this is what was supposed to happen.
The initial blast went as planned, but the precise way the silo started to collapse made the difference between success and failure.
What did happen was that these parts here started to be crushed, and when this uncrushed part hit the ground floor, that's when it started to go all the other way back, because all this concrete here has been destroyed.
Instead of immediately toppling, the silo slumped backwards, and as the top of the wedge hit the reinforced base, the kick made it fall in completely the wrong direction. And while the report into the disaster is still ongoing, Per believes the demolition could have been done differently in the first place.
One thing was, for instance, to take it down in steps. Instead of taking the whole thing in one go, he could have taken it in 2 or 3 goes. But of course, it would probably have cut 3 times as much and taken 3 times as long.
While it might not have been as spectacular, taking the silo down piece by piece was probably the best way to go.
Thankfully, no one was hurt. The cultural centre has been repaired, and Vordingborg's dockside has a large clear area for new development. When you're pushing the boundaries of engineering, catastrophe can hit before the build is even complete. But sometimes trouble can lie lurking for decades, waiting for the right moment to strike. Like this engineering failure in Northern California, on one of the nation's most hazardous stretches of railroad track.
Cantera was the most disastrous, one of the most costly, and it affected a lot of people.
An epic miscalculation that nearly destroyed an entire ecosystem.
I could see fish floating in the river, belly up, as an indication of what had happened.
Almost every living organism along a 40-mile stretch of river was wiped out.
In the late 1800s, railways became vital to America's prosperity. As the Southern Pacific Network grew across the western states, engineers faced some of the nation's toughest terrain.
The West Coast Railroad has connected Southern California with the Pacific Northwest for about 100 years. The route runs right past one of the tallest volcanic peaks in the US, Mount Shasta. It's stunning and a real headache for railroad engineers.
To avoid the mountainous terrain, the track was forced down into the Sacramento River Valley. Train historian John Signor worked on the railroad for more than 20 years.
One of the big obstacles for this part of the railroad was getting up and out of the Sacramento River Canyon. The railroad follows the Sacramento River up canyon in basically what's called a water grade on about a 1.7% grade. They got to a point where there wasn't any way to continue following the river. So they got to Cantera and they made a loop. They did a 180-degree curve and started up the canyon wall at the same gradient. The curvature that was there was pretty extreme, and it is for a modern railroad even today at 14 degrees. It's a pretty sharp curve.
The result? One of America's most challenging sections of rail track, the Cantera Loop. Not only is the curve very tight, this is the steepest climb in California's railroad system and demanded extra locomotives to overcome gravity. These were housed in a rail yard 8 kilometers south of the loop, in the small town of Dunsmuir that had sprung up with the arrival of the railway. But as local resident Louis Dewey explains, there was more to Dunsmuir than just a railroad siding.
One of the main reasons it was originally popular with tourists is because the train stopped here. And Dunsmuir is the hub of what used to be a blue ribbon trout stream.
With its great climate, superb fishing, and crystal clear mountain waters, Dunsmuir became a top tourist destination. In fact, the official city slogan is, "Home to the best water on earth."
For more than 100 years, Dunsmuir was one of California's best-kept secrets. But one night in the early 90s, the town became famous for all the wrong reasons. On the 14th of July, 1991, an 1,800-meter-long freight train was traveling up the west coast from the San Francisco Bay Area to Portland.
The train was headed north up the twisting Sacramento River Canyon, and about 9:40, they were approaching Cantera Loop. The train had 97 cars, 11 loads, 86 empties, and 4,294 tons.
Thousands of trains go through Cantera Loop every year. But this time, something went disastrously wrong. The lead locomotive and 7 cars derailed and fell into the Sacramento River.
It's a 14-degree curve.
Railroad engineer Gary Mahon was one of the first at the scene.
As I pulled up here, there was the engine laying on its side, and I observed numerous cars in the river. It was dark. I noticed the tank car partially in the river, but I had no idea what was in it.
What was in the car was 86,000 liters of a highly toxic herbicide called metam-sodium. Although no one knew it yet, this was very bad news. Attorney Donald R. Bitblit later worked on the case.
Metam-sodium is classified as a biocide, which means it kills any living thing. When it mixes with the water and turns into a combination of hazardous substances that would go off into the atmosphere.
Few people have heard of metasodium, but it's one of the most widely used pesticides in the United States.
The so-called best water on Earth had been contaminated by this toxic train load. Hardware store owner Ron McLeod witnessed the devastation unfold.
When I looked at the river, it was kind of a greenish-brown color rather than the clear water that we typically see. And I could see fish floating in the river, belly up, and it was an indication of what had happened.
Almost every living organism between the loop and Lake Shasta, 40 miles or 60 kilometers away, was poisoned. The river was so polluted, it was nearly 3 days before scientists were even allowed near the water.
In the coming days, more than 1 million fish died.
The river was closed, of course, immediately. People that had been coming up for 20 or 30 years as a family didn't come up the next year. And they didn't come up because, of course, they couldn't go do their fishing.
Luckily, no one was hurt, but this was the worst environmental disaster in California history, and a catastrophe for Dunsmuir. But thousands of trains had navigated the Kantara Loop for years, so questions were asked. Why did this one come off the rails so spectacularly? An official report concluded that the derailment was, in part, caused by the configuration of the 97-car train. With too many empty and light cars at the front, when it took the steep uphill curve, the rear of the train pulled back, causing a phenomenon known as stringlining.
Imagine this string is the train going round the curve. So long as the forces are balanced, it stays curved. But if the heavy weight at the back pulls against the front, then there's a giant tug of war, and bang, the lighter trains in between are pulled off the track. That's why it's called stringlining.
With the imbalance in the load, the train was primed to derail, and bad luck made sure that it did.
Here's a simulated train approaching the Kantara Loop. This is the car of the chemical metam sodium, an agricultural chemical. And the train was heading for the loop, and a curve oiler caught one of the locomotive wheels, and it slipped, then bent on it, dumping the car of metam sodium in the river.
Railroad engineer Gary Mahon thinks that as well as the weight distribution, a fault in the lead locomotive might have tipped things over the edge.
It was reported that the engine that was derailed and laying on its side had not been working properly. It was surging, which meant it was jerking the train. And unfortunately, it did that just as they started around this curve. If that engine surged and there was enough power up there to stringline the cars off the track, had it been running right, maybe the derailment would not have happened.
The restoration and cleanup led to the largest environmental settlement in state history. To keep it from ever happening again, a barrier was built to prevent cars from being stringlined into the river, and new regulations on train configuration were implemented.
Following the investigation, the Union Pacific limited the length of trains traveling along the canyon, reduced their speed, and upgraded the locomotives pulling the train.
Finally, action was taken to get the Sacramento River and Dunsmuir back on track.
The accident still ranks as the largest hazardous chemical spill in California. But thanks in part to a 3-year fishing ban, most species in the river have completely recovered.
Hopefully, lessons have been learned so something like this never happens again.
An epic crane catastrophe wrecks a Milwaukee ballpark.
You knew that there were people up on the structure that couldn't have survived.
A bridge in Washington state sinks like a ship.
When the Hood Canal Bridge rolled over, that was a real eye-opener.
A stadium roof comes crashing down in Connecticut.
This came within hours of being one of the biggest calamities in the history of American structural engineering.
And a devastating dam disaster stuns the UK.
This engineering catastrophe cost lives.
With big builds, even the smallest mistake can be a huge disaster. From miscalculations to misunderstandings. Some with deadly consequences. These catastrophes are every engineer's worst nightmare. Engineering catastrophes can strike at any time. Some oversights take years to develop into a problem. Other failures can turn into tragedy in an instant. Like this construction disaster in Wisconsin in the US.
This was a unique project with unique problems.
A build that pushed the limits to the edge and beyond.
The margin for error here was just too small.
This disaster resulted in terrible tragedy.
The cables started to squeal. There were a couple of loud bangs. I looked at Lance and I said, time to run.
Milwaukee, on the western shore of Lake Michigan. In its early days, the town served as a trading post. But in the 1840s, settlers arrived from Germany and began to do what they do best: brew beer.
Milwaukee is known as Brew City. The city's passion for brewing dates back nearly 200 years.
Beer is not all that this city is passionate about.
Its love of baseball runs just as deep, with their major league team aptly named the Milwaukee Brewers.
And this is the epic home of the Brewers, Miller Park. It's been a mecca for the team's fans for decades, like local journalist Jim Nelson.
People love coming to Brewers games and tailgating in the parking lots surrounding Miller Park, cook out, drink beer, play Frisbee, have a great time.
Built in the 1990s, the mammoth Miller Park was one of the largest construction projects in Wisconsin history. But engineers weren't just building an average ballpark. In a region with unpredictable weather, the goal was to draw bigger crowds throughout the entire baseball season.
Milwaukee has warm, humid summers, which are perfect for baseball. But the season starts in spring and runs all the way through to autumn, when the weather is much less predictable.
The only way to guarantee constant play in Milwaukee's erratic weather was a closing roof.
The retractable roof allows certainty for days like today, when you're coming to a baseball game and you know they're going to play.
Closing roofs are nothing new, but this one would be unlike any other in the world.
The engineering solution was a pioneering fan-shaped retractable roof that could sweep closed from either side to mimic the shape of the baseball field below.
Engineering consultant Christopher Pinto worked on the stadium.
This was a totally different take on retractable roofs. No one had really done something like this before in the United States, to create a fan-shaped roof of 5 different moving panels that could all move separately, that all stacked over one another.
In 1999, 3 years into construction, the time came to install the unique roof. This epic lifting job demanded an equally epic machine.
This was a heavy lift and called for one of the world's largest construction cranes, known as Big Blue.
Big Blue, a 170-meter tall heavy lift crawler crane, capable of elevating up to 1,500 tons, was the monster machine brought in for the job. Not only could this crane lift the massive loads required, it could also maneuver the complex roof sections into place with precision.
A fundamental rule for lifting heavy loads is for the crane to maintain equilibrium. Basically, it has to be perfectly balanced.
Big Blue maintained its perfect balance until July the 14th, 1999, when its team faced one of the most challenging lifts of the project.
Big Blue had been on site for 11 months and had successfully hoisted 10 roof sections into place. But this large curved panel was one of the heaviest components and a really complex lifting job.
The roof sections to be lifted that day weighed more than £1 million.
The epic lift caught the attention of crane enthusiast Bob Winkle and amateur photographer Lance Wallace.
I'm driving on the freeway, I'm trying to look at it while I'm driving, but I can't focus on the road either.
And we pulled up by the old park.
So this is about where we parked, and I started shooting pictures. And we were standing next to about 10, 15 other spectators.
The lift was also being filmed by a safety team that was carefully monitoring every aspect of the operation. With a lift like this, safety is paramount.
With every load, calculations are done to ensure that the height, the distance, and weight of the lift all allow a safety margin. And one other crucial element to the equation is the wind.
The day was pretty windy. It started out in the morning, they were having some heavy gusts, and there were questions as to whether they were going to do the pick. And when we came back through at 4 o'clock in the afternoon, they had it up in the air, and that's why we had to stop and actually see what was happening.
Suddenly, something unexpected began to unfold.
On the drums for the cables, you could hear that, and they started to squeal. There were a couple of loud bangs. They were primarily explosions. And at that time, I looked at Lance, and he said, "What was that?" And I said, "Time to run."
The massive crane started to fall. Big Blue had collapsed, smashing into the stadium below.
Its center window, the third one, is where primarily everything went through.
During the collapse, there was pieces flying through the air. It was like tension being released in the metal and just small explosions that just kept happening.
The scale of the damage was devastating, and not just to the structure of the stadium.
When the crane fell, I personally thought that, yeah, people had to be injured and we had to have deaths, because seeing one of the baskets get swung out of the way, and he was actually saved, but you knew that there were other people up on the structure that couldn't have survived.
Most of the construction team narrowly escaped with their lives. But a second crane helping to direct the lift was also forced to the ground. Tragically, 3 men lost their lives. After the catastrophe, engineers examined the scene to discover what had gone wrong. Investigations revealed a combination of factors had caused the collapse, including a last-minute change to the crane's position.
Stability is an absolutely critical part of crane operations. It's vital that the ground is sufficiently strong to support the crane.
Contractors noticed ground cracking around Big Blue, so they moved the crane to more stable ground. But an existing part of the roof was now blocking the path of the new panel.
The crane moved to a new position to facilitate the lift, but the roof structure had to be lifted higher than initially planned, to about 350 feet or 100 meters above the ground surface.
Lifting the roof section higher than planned increased its exposure to the already high winds. Far from ideal, given the section of roof that was being raised.
The size and shape of this load was a major factor in the accident. It had a surface area larger than 3 jumbo jets, and it was curved like a giant sail, all of which made it very vulnerable to the wind, with a phenomenon engineers call the wind sail effect.
The unusual load, combined with the wind, was more than Big Blue could handle.
The crane was subjected to sideways forces that it simply wasn't designed to withstand.
With a crane so close to its safety limits, only one thing had to go wrong to trigger a snowball effect, and there was nothing anyone could do to stop it toppling over.
Big Blue was completely destroyed in the accident. As plans were laid to continue construction, engineers were determined to learn lessons from the tragedy to ensure that nothing like this could ever happen again. The 1999 collapse of Big Blue set the construction of Miller Park back by an entire year. High winds combined with the increased height of the lift and the sail-shaped load pushed Big Blue off balance, and the excessive sideways forces broke the crane in two. But the ambitious build had to continue.
Clearly, no one wanted a repeat of the tragedy, so the roof design was modified and a different crane brought in to finish the job.
Miller Park opened for its first game in April 2001. Positive change did come from this tragedy. Crane safety was forever improved.
The investigators proposed a raft of safety measures, including changes to the planning processes, positioning of the observers, and better monitoring of the wind conditions at key points on the crane.
Big Blue set a new precedent in regulations that now safeguard construction workers worldwide. To this day, the 3 steel workers who died during this terrible accident are remembered by the city of Milwaukee. Engineers have to take into account everything that the elements might throw at them, but sometimes even the most solid structure can fall victim to Mother Nature. Like this bridge in Washington State that was destroyed by a string of failures.
When designing any structure, engineers have to consider Mother Nature.
A vanishing roadway that cut a vital transportation link.
I have seen many interesting things in my life, but when the Hood Canal Bridge rolled over, that was a real eye-opener.
This was the perfect storm, and it revealed a catalogue of engineering errors.
Northwest Washington State is an unspoiled wilderness.
This is a pretty remote and wild part of America, surrounded by mountains and buffeted by the Pacific Ocean. The landscape is splintered by waterways, carved out by ice thousands of years ago.
With all this water, dozens of communities have long depended on bridges. Norma Tipton has lived here for decades.
It's great to live here because I think it's one of the most beautiful areas in the world. We do rely on bridges a lot because there's so much water around.
And this is one of the most unique. The William A. Bugg Bridge. When it first opened in 1961, this was one of only 3 permanent floating bridges in the world, and it was an immediate hit with the locals.
It's the only link for people who want to get from Jefferson or Clallam County over to this side of to Seattle, which is, of course, the biggest city in the area.
Although officially named the William A. Bugg, this bridge is better known for the piece of water it spans, the Hood Canal.
The name is misleading. Hood Canal isn't actually a canal, it's a fjord, a narrow, deep valley cut by a glacier and then flooded by the ocean. It's about 1.5 miles or 2.4 kilometers across, but a massive 50 miles or 80 kilometers long.
At the time, nearby Seattle was home to the world's longest floating bridge, successfully spanning Lake Washington. But crossing the Hood Canal was a whole new challenge.
The fjord is 347 feet, or more than 100 meters deep. That's far too deep to build a bridge with legs. At that length, they would need to be impossibly wide to be strong and stable enough. and building a suspension bridge would be astronomically expensive, and so a floating bridge is what made the most sense.
The bridge would be supported by a series of 23 concrete pontoons, held in place with cables and anchors on the seabed. Although made of concrete, the pontoons float because they're hollow like a barge. The bridge deck sits above on elevated trusses. It may sound like a simple idea, but it was hugely ambitious, as State Bridge Engineer Patrick Clark explains.
The canal at that time was unusual, and it was the only floating bridge that had an elevated roadway all the way across. And the reason for that, the waves are much bigger on Hood Canal than they are on Lake Washington. So with the high elevated structure, traffic's able to travel along with wave spray basically passing underneath.
And it needed its elevated status because despite being deceptively calm, on some days this fjord can be anything but, as winds roll in from the nearby Olympic Mountains.
Although a long, narrow fjord might seem like the perfect sheltered harbour, in certain conditions the Hood Canal is almost the opposite. It acts like a giant wind tunnel, focusing high winds along the valley, which whip the ocean up, creating huge waves, and the Hood Canal Bridge lies right across their path.
As well as withstanding these unpredictable conditions, this floating bridge had to be engineered for another purpose.
The US Navy has had a base on the Hood Canal since the Second World War. It's now used by the Pacific Submarine Fleet. So, when the bridge was built, for reasons of national security, it had to be able to open wide.
While most opening bridges lift or swing, this one retracts or withdraws, referred to as a drawspan. The design incorporates two floating sections in the center of the bridge that can be withdrawn back towards each shore. When fully retracted, a 180-meter gap in the middle allows large naval vessels to pass.
The drawspan is a great solution for letting marine traffic through. But in an area of high winds, strong tides and currents, you're left with two very long floating jetties, each of them much more vulnerable to sideways forces than if they were permanently connected.
For 17 years, the bridge battled Mother Nature and slashed journey times across the Hood Canal. But an unexpected weakness was about to be dramatically exposed. On February 13, 1979, a storm rolled from the Pacific Ocean into Washington's Hood Canal.
I think that this was a once-in-a-lifetime windstorm for this area. I don't remember any nearly as severe as that. And the sky was quite dark, and there were big white caps all over the canal, and the trees were waving like crazy, whooshing wind through.
To protect the bridge, the drawspan was opened.
And when you build these big, heavy drawspans, they draw a lot more load. But when the storms start to come up, we shut it down to traffic, and we retract the drawspan back onto each side, so we leave a 600-foot opening. It relieves the pressure from the wind and waves on the bridge.
Experts calculated that hurricane-force winds were blowing up the fjord, exceeding 120 miles, or nearly 200 kilometers an hour. There was also a strong current flowing in the opposite direction. Working together, they battered the bridge.
The pounding appeared to be more than the bridge could handle.
I had a friend who lived near here, and she called me and said, "Norma, can you see the bridge?" And I said, "Yes." She said, "It's going down." So I walked over to my big window and looked out. It just rolled over.
At around 7:30 a.m., the floating bridge broke free from its anchors, rolled over, and sank.
It went, it was really a few seconds, but we could really see it.
The bridge was at the bottom of the fjord. The crossing had been closed before the storm hit, so luckily no one was hurt. But in a region known for its extreme weather, why had the bridge failed so catastrophically?
With nearly half of the bridge's 23 pontoons sunk, residents and officials were left asking, how did this happen?
Investigations revealed that the perfect storm, both in terms of weather and engineering failures, had hit the bridge.
So when the storm came on, they had much more significant wind and wave forces on here, and then you had the tide going against the wind caused the seas to stack. And it started to drag these anchors. And when you start to drag these anchors, the bridge starts to go out of alignment and it loses its support.
At this point, another part of the bridge became a problem: the walls on the sides of the maintenance deck.
On the top deck, there was these barriers added on there for safety of the workers. Well, it wasn't anticipated that the water would come on so rapidly that the water couldn't drain through the drains fast enough, and it actually filled between the barriers.
All that trapped water began to find its way through the maintenance hatches.
These hatches were larger hatches that really weren't designed for real high pressures because it wasn't anticipated.
The pressure burst the hatches, allowing water to flood into the pontoons.
You get more water in your pontoons, you start to lose flotation, you get top heavy, you lose your transverse support, and the bridge started developing cracks, and then so it's a progressive failure.
The final straw in this epic fail came when the cables connecting the pontoons to their underwater anchors finally snapped. The Hood Canal Bridge may have been underwater, but leaving local communities cut off wasn't an option. A new bridge had to be built, and this time it had to be able to survive whatever Mother Nature could throw at it. State engineer Patrick Clark helped rebuild the bridge.
We're confident that the new design addresses those storm loads that we saw in 1979. The anchors were made much larger.
The new anchors are 3 stories tall and 46 feet. That's nearly 15 meters wide. They're basically vast buckets filled with rocks.
Each pontoon now has 3 anchors attached by cables twice as thick as those on the wrecked bridge. In addition, the new maintenance hatches are now firmly watertight, so the maintenance decks are no longer an issue.
The solid concrete barriers were removed and they were replaced with cable rails. The new bridge should be able to survive those kinds of storms. That's what it was designed for.
The fix cost $150 million, and in 1982 the bridge reopened stronger than ever.
Once the Hood Canal Bridge was rebuilt, we all celebrated because we did a lot of traveling that way, and it was just a great relief to everybody.
Here it's clear that engineers learned their lessons really well. Anchors that couldn't drag, stronger cables, submarine-grade hatches. The list goes on and makes you pretty confident that this bridge isn't going to be caught by surprise again.
Engineers always want to be ahead of the game, but with new innovations and technologies come new risks. Sometimes the gamble doesn't pay off. Like this disaster in Connecticut, where grand plans for a city's revival came crashing down to earth.
This came within hours of being one of the biggest calamities in the history of American structural engineering.
This lucky escape for a stadium full of people highlighted the limitations of computer-aided design.
Computer analysis designed to keep the building safe actually put thousands of lives at risk.
A very lucky escape for a stadium full of people.
Hours later, it was no more. And I don't know if I've ever really gotten over that.
Hartford, Connecticut, founded in 1635, is one of the oldest cities in America.
Hartford has the oldest public art museum and the longest-running newspaper in the U.S. Mark Twain wrote his classic adventures of Huckleberry Finn here. The town has a rich history, but in the 1970s, it had fallen on hard times.
Redevelopment was seen as a way out of the urban decay in the hope of reviving this once great and historic city. In the early 70s, 4 major projects were greenlit, and the centerpiece was a brand new stadium. the 10,000-seater Hartford Civic Center. Local journalist Tim Jensen explains how the stadium hoped to reinvigorate the town.
In the mid to late 70s, the Civic Center was not only the place to go for exciting sports action, but also it was the major concert venue between Boston and New York. Superstars from around the world performing in concert right here in the capital city of Hartford.
To embody this newfound optimism, the roof of the Civic Center would also be a superstar structure, using new and cutting-edge technology.
The icing on the cake was a state-of-the-art roof designed using what was, at the time, pioneering technology, computer-aided design, or CAD.
These days, CAD is used to design everything from household objects to spacecraft. But in the early 1970s, it was in its infancy.
CAD allowed Hartford's engineers to come up with an innovative new support structure for the 90 by 110 meter roof called a space frame. Structural engineer Stephen Ressler explains.
This model is a representation of the structural system that was used for the Hartford Civic Center roof. As you can see, those individual pyramid-shaped modules were tied together with structural connections in order to make this more elaborate, geometrically complex structural system.
The structure used 2,300 steel trusses connected to form a series of inverted pyramids designed to evenly distribute the weight of the roof. For added strength, the whole roof was supported by steel cross-sections known as bracing.
They did that in the form of these diagonal elements that intersect the top chord members right at their midpoints. By adding these diagonal members that frame into the top chord, they caused it to be, at least in theory, 4 times stronger than it would have been without these diagonal braces.
To save time and keep workers safe, the entire roof was built on the ground and then jacked up about 80 feet or 25 meters into the air.
The roof was the size of 2 football fields, and yet it was supported by just 4 pylons. It really was an engineering marvel and gave everyone in the crowd an unobstructed view of the action.
The cutting-edge new stadium opened in early 1975, attracting large crowds to music and sporting events. January the 18th, 1978 was no exception.
A huge college basketball game was played. The University of Massachusetts visited the University of Connecticut. Over 5,000 excited fans found their way to the Civic Center that evening.
Little did they know a disaster was about to unravel. A huge snowstorm descended on Hartford. Suddenly, the entire roof of the Civic Center collapsed. 1,400 tons of twisted steel and concrete fell onto the 10,000 seats below. Thankfully, it was after 4 o'clock in the morning and the building was empty.
It's lucky that this happened in the middle of the night. Just 6 hours earlier, the stadium was packed with 5,000 people watching a basketball game. Who knows how many could have been killed?
No one was hurt in the catastrophe. But what had caused the cutting-edge computer-aided design to collapse? In the days that followed the Hartford Civic Center disaster, young engineer Jeffrey Coleman was sent to assess the wreckage.
My first view was from the hotel next door. The roof structure was all twisted and wrapped together in various directions. It was a twisted mess. Buildings aren't supposed to fall down. And here I was standing in the midst of an incredible tangled wreckage. I was 24 years old at the time, and it was a real sobering experience.
Jeffrey looked at the obvious culprit, the snow, but something didn't add up.
At the time, the building code would have required the roof to carry 30 pounds per square foot of snow load. Live load, we call it. At the time it collapsed was 26 pounds per square foot of snow load. So the roof collapsed at a load less than what it was designed to withstand.
An official investigation found that the computer calculations had seriously underestimated the weight that the roof could handle.
When you look at engineering failures, you'll often find a well-intentioned decision followed by an unintended consequence. And that was the case here.
A computer model is effectively just a very fancy calculator. You get an answer based on the data that you put in. It's how those results translated into the real world that appears to have been the problem.
When entering the data into the computer program, engineers had failed to recalculate their numbers after a change was made in the original design.
The computer had calculated a design based on a flat roof, but the roof had to be slightly pitched so that water, or in this case snow, could drain off.
Flat roofs have an unfortunate characteristic of collecting water. The water pools, and that adds considerable weight to the roof and also causes drainage problems and leaks. And so the designers had to provide just a little bit of camber on the roof, an outward slope that would cause the water to drain outward. The designers added these small posts at each of the joints, and then the roof deck was built as a series of panels that were then placed on top of those short posts. Unfortunately, those posts ended up being part of the problem associated with the collapse of the structural system.
The dimensions of the new posts were not fed into the CAD system, meaning the computer's calculations were inaccurate.
By raising that roof up, those stubs no longer adequately braced that top chord in the horizontal direction.
As they lifted the now sloping roof into place, there were signs that it was struggling to cope. Under the weight of water or snow, this state-of-the-art structure was visibly sagging.
The deflection, or basically sag of the roof, was double what was expected. It would seem a clear warning that the structure wasn't behaving as the computer had predicted.
Despite all these warning signs, the designers continued to insist that there was absolutely no problem with the design and that they had the ultimate confidence in their computer analysis results.
When construction workers and spectators can see that the roof is sagging, maybe it's time to turn off the computer and get out the calculator.
The engineers' faith in the computer calculations caused them to doubt the evidence in front of their eyes.
The changing shape of the roof once it had been installed hadn't been taken into account and wasn't something the computer had been asked to calculate either. It turns out this made the roof highly susceptible to buckling.
While the bracing in the center of the structure was still strong, the warped roof had critically weakened the side bracing.
Because of the design deficiency associated with the lack of proper bracing on the exterior compression members of the space truss, these members were severely overloaded, and under that snow, they buckled like this, causing a transfer of load to the adjacent module and the chain reaction buckling of all the adjacent top chord members. This.
This triggered a cascade effect, buckling yet more members until the whole lot came crashing down.
In the wake of the 1978 Hartford Civic Center disaster, the city's mayor promised to rebuild the Coliseum, bigger, better, and crucially stronger. Today, even the heaviest snowfall is no match for the new and improved roof.
We actually designed the roof structure to withstand 35 pounds per square foot of snow load, as opposed to the code required 30. So we increased the load just to give everybody a comfort level in that regard.
The entire process of designing and constructing the new roof took just 21 months. And on October the 15th, 1979, the Hartford Civic Center was reopened and back in business.
The design might not be as clever, creative, or cutting edge, but the Coliseum's new roof has been built to last and is still going strong after 40 years.
I haven't been up here in 40 years. Looking down from this vantage point, you can see the seats where the spectators would be. You could see the arena, and you can imagine thousands and thousands of pounds of structural steel descending on those people.
One of the most important lessons that we as engineers have learned from the failure of the Hartford Civic Center roof system is that even while the computer is an extraordinarily powerful tool that gives us capabilities that we simply wouldn't have if we had to do our calculations manually, We must always have to apply common sense and good engineering judgment in order to ensure that the results we're getting from the computer actually translate into safe structures on the ground.
If heavy snow ever hits this roof again, all sports fans need to worry about is keeping their eyes on the game.
When engineering goes wrong, the cause can be staring us right in the face. But sometimes there can be more to a fail than meets the eye. Like this dam in the mountains of Wales, and a disaster that went down in history.
This dam was doomed from the very start.
You can hardly imagine the scene in the valley with the remains of the dam.
An engineering fail that destroyed a village.
This catastrophic failure forced a change in the regulations.
Wales is a rugged land. Its mountains and streams are rich with myths and legends.
Wales is known for ancient Celtic folklore, grand castles, and natural beauty. But there's another side to the country. It's long been an industrial powerhouse.
A driving force behind all this industry comes from the mountains, as the rivers flow to the sea. A century ago, to harness that untapped energy, engineers started building dams to feed hydroelectric power stations, like this one in the village of Dolgarrog. Geologist Jonathan Wilkins explains.
This is a good location for the generation of electricity because the terrain gives a very, very rapid drop in height between the reservoir and the floor of the valley where the power station is situated. Well, this is the generating hall from Dolgarrog Power Station. In front of you, the large blue pipes are bringing water from the reservoirs, and the big square boxes are the alternators which are supplying power to the national grid.
Key to a constant supply of electricity was a large reservoir of water. First built in 1924, the 120-metre-long Coty Dam held back millions of gallons of water, which was used to power a nearby aluminium works. But just a year later, disaster struck. In the autumn of 1925, North Wales experienced unusually heavy rain, putting a massive strain on the Coty Dam. But no one was prepared for what happened next. Dolgarrog resident Daffyd Williams knows the story well.
There'd been raining for several days. Water was sort of accumulating on the dam above the village. And then later on that night, the dam burst, bringing thousands and thousands of gallons of water down.
The water gushed over the dam's crest, and although no one in the village knew it, the dam was minutes from total failure.
Suddenly, the Coty Dam collapsed, sending a raging torrent into Dolgarrog.
Right now we're standing in the path of where the boulders and the water came down, bringing 1.74 million cubic meters of water. Nothing had any hopes of surviving in all this.
In an attempt to warn the villagers, the church bell was rung 3 times, but it was too late.
The flood quickly overwhelmed the village, carrying debris, including huge boulders that weighed hundreds of tons.
This is one of the boulders that came down that night. I'm about 5'9", and this is not the biggest of them. This is small comparison to some of them.
The result was completely devastating to the village and to its inhabitants.
This is the piece of pipe that came down with it. As you can see, it's all crushed. You can see how it's mangled up. You can imagine if the boulders can do that to a piece of metal like that, what we do to buildings and people living there.
Tragically, 16 villagers lost their lives, including 6 children. Engineers had to figure out what had gone wrong and how to protect the villagers from future tragedy. As the floodwaters receded from the village of Dolgarrog, it was clear that the Coty Dam had failed. But engineers soon discovered the real cause of the tragedy lay upstream.
The Coty Dam wasn't the only dam in the system. There was another, older structure further up the mountain, the AGI Dam. At the time, it was used to regulate flow into the reservoir downstream, and it was this dam that had failed first.
But what had caused the Agi Dam, built only 14 years earlier, to collapse so catastrophically? Author John Lawson-Rieh believes it's all down to the construction.
It's absolutely rubbish. The construction of it is dreadful. And they were always patching it up. And you can see the patches here, some of the patches. It's rubbish. It just falls apart. And it's no wonder that it was causing problems.
One key error was in the foundations. In the original construction, it seems these hadn't been dug down to the bedrock.
You have to remember, this dam was built more than 100 years ago, so engineering knowledge was nothing like it is now. But with foundations that didn't reach the bedrock, this dam was destined to fail at some point.
We're coming up here to the place where the wall had been breached. There'd been a washout underneath it where the undermining of the dam would have taken place. That this had caused the dam wall to actually collapse at a major force, sending billions of gallons of water down into the valley to the Coity Dam. Now, Coity Dam was just a headstock. It was not intended to take a large quantity of water.
As the water spilled uncontrollably downhill, it gushed into the Coity Dam, overlooking Dalgarog, and the dam overflowed, known as overtopping.
When a dam overtops, it's game over. Once water hits the downstream side, it can be a matter of hours before a total collapse.
As local geologist Jonathan Wilkins explains.
The water rushing across would have poured into the valley, eroded the downstream side of the dam, and once the erosion of the downstream side of the dam was severe, the concrete itself would have been exposed and weakened and liable to failure. At that point, you can hardly imagine the scene in the valley with the remains of the dam and all of the debris, the floodwater, rushing down the quite narrow river valley, down quite a significant gorge in the trees which you can see in the distance.
With both the Agi and Coity dams destroyed, there was only one solution.
The Coity Reservoir was fairly quickly repaired because its design was sound. It had simply been overwhelmed by the water that arrived from the Agi Dam. The Agi Dam was never rebuilt because I think it was realized that the design was fatally flawed. In order to make the Coity Dam safe, they installed spillways and ways of handling water which came over the crest of the dam in a way that did not lead to erosion of the downstream side of the dam.
Tragedies like this highlight engineering oversights. The crucial thing is that engineers learn from these mistakes so that new structures can be stronger and safer.
Today, the Coity Dam stands solid, both generating valuable hydroelectric power and protecting the village of Dalgarog from another catastrophe. The events of 1925 will always be remembered.
This is a memorial we set up to remember that night with the names of the people who lost their lives. A lot of the villagers still come here and to remember it, very emotional about it. They can come here and they can sort of ring the bell to remember what happened that fateful night, you know, when the church bell was being washed down by the river. The only good thing that came out of this, that new legislation came out on dam building and dam inspections.
The disaster led to the Reservoirs Act of 1930, which changed the rules when it came to dam construction and safety in the UK.
If there is any consolation here, it is that the investigations into Dalgarog led to big changes in dam safety. Since the disaster, there has never been any loss of life due to dam failure across the UK.
catastrophe strikes a major interstate in Connecticut.
It just collapsed. It fell right into the river.
In Montreal, a showcase Olympic stadium turns into an epic disaster.
We were the center of the world, and it was not finished.
In Liverpool, a busy freeway with hidden flaws that could collapse at any moment.
That is not currently fit to function.
And a Dutch disaster as a huge levee fail floods a town.
The water here was up to my knees here.
With big builds, even the smallest mistake can be a huge disaster. From miscalculations to misunderstandings, some with deadly consequences. These catastrophes are every engineer's worst nightmare. Engineers are always coming up with original and innovative ways to combat the elements. But sometimes even the best laid plans can go disastrously wrong. Like this catastrophic collapse in Connecticut on one of the state's busiest roads.
It was a very fast and inexpensive way to build a bridge like this.
A crossing calamity that ended in disaster.
Every time I go over it, I'm thinking about the tragedy. It always sticks in my mind.
Just 65 kilometers north of New York City lies the town of Greenwich, Connecticut. About an hour's drive from Midtown Manhattan, it's a popular place to live. As journalist Jim Cameron explains.
Greenwich is a very affluent community just outside of New York City, where people will live and then commute.
Taking commuters into the Big Apple is one of the longest freeways in the US, I-95, running all the way from Florida to the Canadian border. And it crosses through Greenwich via the Mianus Bridge.
It's officially known as the Michael L. Morano Bridge, but like many bridges, it takes the name of the water it crosses, the Mianus.
The current Mianus Bridge has been standing since 1992 and carries more than 90,000 vehicles a day. It's a relatively straightforward girder design, but its predecessor, built in 1956, was an altogether much more innovative construction. The original bridge section crossing the Mianus River was a cantilever design made up of 5 sections spanning a total of 196 meters. Sitting on piers, it had 2 anchor spans at each end, a main span in the middle, and 2 suspended or hanging spans on either side, held in place using a system known as pin and hanger. Structural engineer Stephen Ressler explains.
The pin and hanger assembly, as you might guess, consists of pins and hangers. There are actually 2 hangers. You can see one of them here. It's a vertical piece of steel that's connected to the associated cantilever span on top and connected to the suspended span on the bottom by heavy steel pins that run completely through the girder. The hangers are retained in position by steel retainer washers, which are bolted in place both on the top and on the bottom.
One of the reasons for choosing this bridge design comes down to Connecticut's climate. Warm and humid summers combined with very cold winters meant Mianus needed the capacity to expand or contract, depending on the weather.
We have these wild fluctuations in temperature, as high as 100 degrees in the summer, as low as below 0 Fahrenheit in the winter.
The cold will cause contraction and the heat will cause expansion. And engineers know this, so they include clever design solutions to counteract this phenomenon.
The pin and hanger assembly actually has an important practical function as well, in that it allows for longitudinal movement of the bridge in response to changes in temperature. As a consequence of those changes in temperature, the steel members that constitute this structure would have expanded and contracted. And as you can see, the pin and hanger assembly does a nice job of accommodating that longitudinal movement.
But bridges in temperate climates aren't required to use the pin and hanger design. For the Marianas Crossing, it may have come down to the bottom line.
They chose hangers because it was a very fast and inexpensive way to build a bridge like this.
For decades, the Marianas Bridge was just part of the daily trek for millions of commuters a year.
If you're driving in a truck between New York and Boston, you're probably going on this highway, over that bridge, over the Marianas River.
On June the 28th, 1983, at 1:30 in the morning, 2 tractor trailers and an automobile were on the eastbound section of the Marianas Bridge when the impossible happened. The entire 30-meter span of the suspended section collapsed dramatically and without warning, falling more than 20 meters into the river below, taking all 3 vehicles with it.
It just collapsed. It fell right into the river.
This failure was so sudden. There was no warning. The section of the bridge deck just dropped.
Another car was unable to stop in time. 3 people were seriously injured, but even more tragically, another 3 lost their lives. Attorney Richard Silver witnessed firsthand the devastating scene.
When I went to the scene to view the tragedy, which it was, there was masses of steel. The section of the bridge collapse was in the water. The trucks were visible. You could see the awful impact of these vehicles going over the bridge.
The disaster shook the town. Some had escaped tragedy by just a few feet.
The drama was horrendous. After the bridge collapse, I interviewed a number of people who drive over that bridge every day, who luckily had been able to stop before the disaster. And of course, what went through their mind, it could have happened to me.
In the wake of the disaster, an investigation looked into what had gone wrong. An inspection of the wreckage revealed that the pin and hanger connections were heavily corroded. But what had caused them to rust so badly?
Like anywhere that has regular cold winters, road surfaces are regularly salted during the winter to keep them safe for motorists. When it rains, the salt washes from the road surface and onto the bridge's structure. Salty water and steel can be a recipe for disaster.
To reduce the risks of corrosion, a drainage system was built into the bridge to carry not just salty water, but debris away from the pin and hanger system into a gutter to minimize the danger. But the investigation revealed that this crucial design feature had been compromised.
So about 20 years after this bridge was originally built and constructed, it came time to resurface the roadway. And that meant laying new asphalt. But in the process of doing that, they plugged up some of the drainage holes that were crucial to water in the winter from salt water being able to drain off of that bridge. By plugging up those holes, water found its own level and it drained down past the supports, the pivot and the hinge that were holding the bridge in place. And it caused the pins that were literally hanging that bridge in place to start to rust.
Corrosion accumulating behind the upper retainer on the pin and hanger assembly right here started to pry the retainer off of its pin and ultimately did in fact remove the retainer. It forced it off of the pin. At this point then, continued corrosion resulted in the hanger itself being forced off of the pin. And when that process was complete, this hanger became physically disengaged from the structural system and was no longer participating in holding up the suspended span.
Investigators believe that this displacement could have occurred weeks or even years before the collapse. Now engineers had to figure out how to fix the problem. After the tragic collapse of the Mianus Bridge, investigators found that a potential problem may have been hidden for some time. A fatal flaw that went undetected until it was too late, and was possibly triggered by just one very ordinary event. Structural engineer Stephen Ressler explains.
The critical moment, 2 heavy trucks happened to have driven onto the center span at the same moment, and that particular extreme loading was enough to cause the remaining pin and hanger assembly to fail. Once that second pin and hanger assembly also failed, the center span could no longer carry load, and the entire suspended span collapsed down into the Mianus River.
The investigation found accelerated corrosion caused by a lack of drainage and excess salt was the most probable cause of the disaster. Many also believe that if the corrosion had been spotted earlier, this tragedy could have been avoided. The collapse cut off the main artery between Boston and New York, rerouting 90,000 vehicles a day and causing month-long traffic jams. So when it came to the new bridge, engineers weren't taking any chances.
The bridge had to be rebuilt, this time without a pin and hanger system, but with a continuous girder and floor beam design.
They replaced it with a girder structure that sits on pylons in the river, so rust is not going to cause that bridge to collapse.
Not only is the Mianus Bridge more solid than ever, its failure alerted engineers to a problem that could be pervasive across the country.
It reawakened concern about the safety of bridges, and that there was now a requirement that they be inspected more often.
Some estimates suggested that at the time there were about 60 pin and hanger bridges in Connecticut alone, and around 2,000 across the US.
Throughout the entire country, there was an examination of these pin and hanger assemblies. It's to my knowledge that this design was not utilized again.
When it comes to big engineering, sometimes innovation can really pay off. But other times it can turn to catastrophe. Like this cutting-edge construction that put Canada on the map for all the wrong reasons.
We were the center of the world, and it was not finished.
A space-age design that suffered from a failure to launch.
This was a construction that went way off track and more than $1 billion over budget.
And a revolutionary roof that 4 decades later still can't cope with Canadian winters.
This is one engineering catastrophe that doesn't look like it's ever going to get fixed.
Located on the St. Lawrence River, Montreal in Quebec is one of North America's most diverse and European-inspired cities.
Montreal is Canada's second largest city and widely considered the country's cultural capital. It's a real melting pot, with more than 60% of the population speaking French.
In 1967, Montreal hosted the International Expo or World's Fair. With over 50 million visitors, it was widely considered to be the most successful World Fair of the 20th century and really put the city on the map.
So when it came to hosting the world's most diverse event, Montreal had that certain je ne sais quoi. And on May the 12th, 1970, it was awarded the 1976 Summer Olympics. The city had bold plans for a show-stopping stadium. As urban planner Sylvain Lefebvre explains.
This is the Olympic Stadium. It was very audacious from an engineering point of view.
The groundbreaking stadium would hold up to 76,000 people in stands supported by 34 self-stabilizing cantilever arms. Looming large over the structure at a 45-degree angle and 175 meters tall would be a modernist tower, 3 times the height of the Leaning Tower of Pisa.
We had this magnificent stadium and very ambitious from an engineering point of view, with the biggest and tallest inclined tower in the world.
And their ambitious plans didn't end there.
The centrepiece of any Olympic Games is the stadium. Montreal wanted a landmark statement, especially when it came to the roof.
Like a lot of Canadian cities, Montreal can experience very harsh and snowy winters, typically lasting around 5 months. So to make use of the stadium all year round, a roof was essential. But Summer Olympic mandates require the athletic events to take place in the open air. So designers came up with a bold and revolutionary idea: a retractable roof.
Retractable roofs on stadiums are commonplace now, but back then, this technology was very much in its infancy.
The retractable roof would consist of an orange and silver membrane larger than a football field, weighing around 70 tons, and supported by 26 steel cables. The plan was for the enormous fabric roof to fold away like a giant umbrella inside the huge tower. Because of this cutting-edge design, the material had to be both flexible and strong enough to stand up to Montreal's snowstorms, yet light enough to be suspended across a huge area. The material they chose was Kevlar. At the time, Kevlar was a relatively new, super strong and very light synthetic fiber. But it had never been tested on this scale before.
Kevlar is great if you want to stop a bullet, but maybe in hindsight, not so brilliant if you want to build a retractable roof.
Even before construction had started, things began to go wrong.
The stadium was meant to be a real showstopper, but it was plagued with problems right from the start.
Despite Montreal being awarded the 1976 Summer Olympics in May of 1970, the final designs for the ambitious stadium weren't submitted until more than 2 years later, meaning work on the site didn't begin until late April 1973.
The delays meant they now had less than 3 years to pull off one of the most ambitious projects of its kind.
By July 1976, the landmark tower was only 72 meters high, less than half its intended height, and the revolutionary roof was nowhere in sight. But the Olympic Games wouldn't wait.
The eyes of the entire world were on Montreal and its show-stopping stadium. There were 73,000 people in the stadium, including the Canadian Prime Minister and even the Queen of England. The only thing missing was the roof.
This was the first time in Olympic history that the stadium wasn't ready on time.
When we had this overture open ceremony for the stadium, we were the center of the world, you know, all on TVs and everything, and it was not finished.
After the Olympics, the stadium was used for a variety of events and sports and became home to baseball's Montreal Expos. But incredibly, it wasn't until more than a decade after the Olympic athletes had all packed up and gone home that the tower was finished and the retractable roof hoisted into place. Although it looked impressive, it was far from perfect. Architect Pierre Utras explains.
It was made of Kevlar, coated with vinyl. But this roof had some, would say, design flaws. The roof as a whole would tend to lift up under wind load and sink down under dead weight load like snow. There was what was called trampoline effect under the wind.
This trampolining effect meant that in order to remain stable, the roof had to be pulled very taut. But this was creating issues of its own. The roof didn't just have major wind problems, it was ripping too.
There were certain circumstances where the roof would lift up and then come down suddenly and break at the stress point, and once a rip starts, there's no way to stop it.
Despite all its problems, authorities persevered with a clearly failing retractable roof for more than 20 years, before repeated tears finally kept it closed for good. But the city wasn't giving up on its stadium, and they were determined to try again. In 1998, the retractable roof was finally replaced with a new fixed one at a cost of $26 million. This time, instead of Kevlar, they used Teflon. But designers failed in this material choice as well.
The new roof was meant to fix the problems of the past, but it still proved a massive headache.
The problem was that the new fixed Teflon roof still had to connect with the original roof's framework.
This actual roof is made with fiberglass reinforced Teflon. On the stadium, the structure itself is made of cable. And since of its very large area, it is subjected to movement. And unfortunately, fiberglass reinforced Teflon cannot stretch.
This time, although it looked like they got the right material for the job, it was still being held up by the original structure that was designed to support the more flexible Kevlar.
In 1999, just a few months after installation, one of the Teflon panels collapsed under the weight of snow, while 200 people were preparing for a car show on the stadium floor below. Luckily, no one was seriously hurt, but this wake-up call meant that authorities decided the stadium would be closed down when only 3 centimeters of snow was forecast. Not ideal in a city that can get 5 months of snow a year.
In the winter months, Montreal averages around 15 inches or 40 centimetres of snow. So to build a stadium roof with a snow load of just over an inch or 3 centimetres seems crazy.
The roof has been holding for 20 years, but the stadium is closed down in the winter. Stresses sometimes can make micro openings of the mesh of the canvas itself.
And hundreds of holes were opening up in the roof every year.
Once the rip count got close to 8,000, they knew it was time to go for another roof.
Yet again, millions had been spent on a roof that simply couldn't stand up to Montreal's harsh winters. Despite its troubled past, and while sadly no longer home to the Expos, the Montreal Olympic Stadium still hosts a wide range of events from all over the world. So, in 2017, the Quebec government decided that the stadium should get its 3rd new roof, this time at a cost of $250 million, the original budget of the entire 1976 Olympic Games. With all the repairs, alterations and delays, costs have literally gone through the roof, rising to well over $1 billion.
Despite all the problems, overruns, and disasters, the city still deserves a stadium and a roof they can be proud of.
The stadium may have been one of Canada's most expensive and biggest engineering catastrophes, but the bold architectural design of the Montreal Olympic Stadium still stands out on the nation's skyline. Although the roof remains a work in progress, hopefully this time it will at least keep the snow at bay.
Even now, the new roof has been delayed and isn't due to be completed until 2024, almost 60 years after the city hosted the Olympics. For this particular construction, it has definitely been more of a marathon than a sprint.
When it comes to big engineering, sometimes problems can lay hidden for years. It's only once the flaw is discovered that we realize we were in danger all along. Like this elevated roadway in the UK, threatening to collapse into a historic downtown.
It might look solid, but it's a disaster waiting to happen.
A freeway with fatal flaws that remained hidden in plain sight for decades.
Engineers had suspected the problem for years, but no one saw this catastrophe coming.
And a city's bold decision to protect its residents. Liverpool in northwest England is one of the UK's most historic and celebrated cities.
Liverpool is famous for being the home of the Beatles, but there's much more to this city. It's long been a key trading port with its heart down by the docks.
In the 1960s, as the Beatles were taking the world by storm, the city was also on the rise, and it needed an infrastructure allowing it to grow into the future, as local government official James Noakes explains.
Liverpool in the 1960s was a real hip and happening place. It really was a place to be. And so as part of that, people had this vision of an almost sci-fi approach to how we dealt with transport. And that was large motorway infrastructure right in the heart of the city.
To get with the times and ease congestion, authorities came up with a radical idea. Instead of going around the city, they would go directly over it, with not one, but 2 elevated freeways, known as the Churchill Way flyovers.
In order to take cars away from the mouths of the tunnels underneath the river, a plan was devised at the beginning of the 60s to build 2 huge concrete structures.
Each of the 2 240-metre-long elevated freeways were made up of 10 concrete spans, creating a continuous 7-metre wide deck, held up by a series of single concrete columns, 1.5 metres in diameter, supporting nearly all of the weight. But the supporting columns simply wouldn't be strong enough to hold deck spans made of solid concrete. So engineers' plan was to make the insides hollow.
Engineers built wooden molds and poured concrete over them, creating hollow decks with the wood left inside.
This wasn't inherently a problematic design, but it did have some risks. Because the bridge design didn't call for manhole covers, which would allow the inside to be monitored during and after construction, if the wooden boxes were compromised while the concrete was being poured, the structure could become too heavy for the supporting columns to hold. Opened in 1970, the elevated freeways quickly became integral to the city's transportation network. Built to have a lifespan of around 70 years, after just 10, there were already signs that both roadways were struggling to cope.
In the 1980s, engineers inspecting the viaducts found crumbling concrete and signs of rust. Worrying with any structure, but particularly with bridges or viaducts carrying heavy traffic over busy roads.
But a much more menacing and potentially fatal problem was lurking within the bridge spans. And without a means for internal inspection, engineers wouldn't realize the danger for decades. Sometimes potential dangers are hidden in plain sight, like here in Liverpool, where for 45 years, an ever-present danger was a part of commuters' and pedestrians' daily lives. Yet, in 2016, new legislation was passed, requiring internal inspection on all major highway structures. It was finally time to go inside the Churchill Way flyovers.
Engineers drilled through the concrete to inspect the insides of the decks, and they got a bit of a surprise.
During the initial construction, as the concrete was poured, some of the wooden boxes creating the hollow decks had burst, allowing more concrete to pour in than engineers had ever calculated for.
No one knew it had happened, but the extra weight was putting huge, unexpected strain on the structure.
The decks that had been carrying traffic over the city for decades were much heavier than the concrete piers were ever designed to cope with. These elevated freeways were ticking time bombs. On September the 28th, 2018, the roadways were closed while over 140 detailed safety checks were carried out. The conclusion was damning, as engineer David Slevin explains.
The assessment of the structures has concluded, based on the condition of the inner webs of the unseen parts of the structure, that it's not currently fit to carry the actual highways loading that it would need to carry to function as the highway that it needs to be.
What they found was truly shocking. Corrosion, poor quality concrete throughout, and worst of all, serious cracking. The structure was so damaged that it couldn't be strengthened and was beyond repair. Churchill Way was closed for good.
They calculated that the structures could safely support their own weight, but not the traffic that had been thundering over them for decades. It's a miracle that they're still standing.
The city had avoided a major catastrophe. But with two fatally flawed and potentially dangerous freeways running directly over the city, the next problem was how to get rid of them.
Traditional demolition on a structure like this would look like large excavators with large breakers, lots of noise, lots of dust, lots of vibration. It's not a practical option to do traditional demolition on this structure because we're in a city centre environment.
Putting some of Liverpool's most historic buildings at risk wasn't an option, so alternative methods had to be explored.
The vibration risk is something that's been considered from the outset of this project. The selection, we have multiple controls with numerous noise, dust and vibration monitors throughout the surrounding buildings.
The solution experts came up with was as surprising as the original construction itself. Rather than demolition, they opted for deconstruction.
What we've devised as engineers is a series of cuts and removals of individual sections. They're cut in situ as they sit on the current structure. They're lowered to the ground, cut to smaller sections and taken away.
To minimize disruption, the 50-year-old spans would be slowly taken down in 24-meter sections. Each span weighing hundreds of tons would be temporarily supported before being cut free and moved onto a special transporter, where it would be lowered and taken away to be demolished. The goal was for the bridge deconstruction to be completed by the end of 2019.
The viaducts will soon be gone, but hopefully planners will see an opportunity to bring the space to life in a whole new way.
Whatever they come up with, Liverpool's engineers certainly have an interesting road ahead. Engineers need to understand the reliability of their building materials and how they will react under all conditions. If they fail to consider a scenario, no matter how unlikely it may seem, a catastrophe is in the making. Like this engineering disaster in the Netherlands.
For a famously low-lying nation, this was terrifying.
A fail that almost flooded an entire town.
With 600 homes in Wilnis, the thought that this levee could fail was almost inconceivable.
The water here was up to my knees here.
The Netherlands is famously flat, with a large percentage of land actually at or below sea level. It's been carefully engineered to sustain a population of 17 million. They have a saying, God created the world, but the Dutch created Holland. And they did it all with levees or dikes. Engineer André Collowin explains.
The Netherlands are built basically in a marshland. The name says it's Netherlands, it's low country, and without dikes we wouldn't exist.
Dikes are a form of man-made levees that are designed to channel water through canals, protecting the land that surrounds them. Holland's dikes date back to medieval times, but in more recent years they required an overhaul.
This desire to control the flow of water is rooted in an event which traumatized the entire nation.
Following a huge storm in 1953, which killed 2,000 citizens, the Dutch government, vowing to be better prepared next time, began investing billions of dollars in an unparalleled network of dams, levees, canals, pumps, and storm surge barricades.
Control of water is of extreme importance to the Netherlands. 2/3 of the country is protected by dikes.
The updated system keeps the nation safe and dry.
If these defenses fail, there's nothing to protect the people's homes from the water.
Many of the nation's dikes were created as a byproduct of fuel mining. But this isn't your average fuel source.
Peat is often thought of as the forgotten fossil fuel. It's found in wetlands such as bogs, fens, and swamp forests. But when it's dried, it burns long and slow.
Peat is essentially a buildup of decaying vegetation and organic matter. It forms over thousands of years, resulting in a material that can be used for many different purposes.
The Dutch have been digging up peat since the 17th century, firstly as a form of fuel, and then as animal litter, and most recently to help cultivate their gardens. These peat mines were then often converted to dikes or small levees.
Just like the dikes in the sleepy town of Wilnis. Local journalist Peter Bakker is a lifelong resident.
In Wilnis, it's a sleepy city. Nothing happened normally here. A tough area for doing some reporting work.
However, in August 2003, the serenity of sleepy Wilnis was disturbed.
It was 2 a.m. I woke up and there was something happening in Wilnis. I look at my pager, I jumped up my quad and go to Wilnis.
When Peter arrived at the canal, he was shocked at what he saw.
There was a lot of people on the streets. A lot of water was streaming out of the dike, and it was like an ocean. A lot of water, every water was here, was going down to the village. It was very strange.
The sleepy town of Wilnis had been rudely awakened by a raging flood. The entire town was under threat. Although exactly what caused the disaster wasn't clear. In a town only made possible by dikes, controlling water flow was critical. Peter Heidemer is a local who lived through the ordeal.
I lived in that house and I heard voices during the night, a lot of commotion coming from our neighbors who are living there. So I walked upstairs to the highest level. Because of the moonlight, you see shattering of water. And that's actually really strange because there is no water here normally. I walked out of my garden and after a few steps, the water was here, ankle height, something like this. And I walked further. When I was around the corner, the water here was not ankle height, but it was already up to my knees here. It's like a lake, and that's really frightened me.
By now it was realized that a large section of Wilnis's dike had catastrophically collapsed. Local resident Hanny Visser remembers that day.
I was looking out my window and I said, wow, water, what's this, what happened? Certainly the houses here till the end, the big houses, they had the most damage. And the bungalows, of course, because everything was underwater.
Things were going from bad to worse until local contractor Koos van der Vaart spotted the problem.
I came here, there was a lot of water floating into the houses here below. I speak someone from the fire department and I said, no way we can stop that water here because the water was flooding all the time. We have to be quick, because this side was already destroyed. But that side, we have to be quick to avoid more damage.
Koos came up with an ingenious plan to stop the flood by creating a makeshift dam upstream from the collapsed dike.
This was the bridge where we can stop the water. It was strong and narrow, so we have the possibility to stop it. We take iron plates and clay, so we could make a watertight emergency dam.
Koos's makeshift dam worked out, preventing further devastation. Finally, the flood levels began to fall, and the townspeople began to return to their homes and assess the damage.
After those 2 days, we came back and we found out you see dead fishes laying in your garden.
Some residents were more fortunate than others.
We were actually really lucky. We didn't have water inside our houses, only in our garden.
For many, the situation was much worse.
The houses are flooded, also the basement, the first floors, and luckily there's nobody hurt and nobody died.
As the waters began to recede, the people of Wilderness felt very lucky. They were terrifyingly close to losing their town and possibly their lives.
In the wake of the devastation, investigators began to explore what had happened. The answer was far from straightforward. And although some suspected the Wilderness Dyke had been compromised, it had a reputation of being unbreakable.
What added to the initial confusion was that this dike had recently proved highly effective when handling some of the heaviest rains Holland had seen in years.
1 year before the disaster happened, the dike was overtopped because of heavy rain, and it did not fail. It was just safe enough. So everybody thought, well, okay, it's water relief, it's safe enough.
So what had caused this veteran levee to crumble? When building the dike, engineers had taken water into consideration, but not the sun. In recent months, Holland had experienced a period of unusually hot and dry weather.
The combination of drought and sun dried out the peat. Cracks then formed within the peat layer, and when the water finally arrived, it traveled through the cracks under the peat.
Not only was the peat no longer watertight, its integrity had also been weakened.
Investigators worked out that the dried peat was about 20% lighter than normal peat, and the pressure of the water underneath it forced the peat to break off and lumps floated to the surface. This weakened the dike enough to make its collapse inevitable.
The water flowing through the cracks in the dried-out levee caused it to erode. With constant pressure, the dike began to crumble, resulting in a total failure.
The failure at Wilderness was a huge surprise to everyone involved in dikes, because normally all causes of failure of dikes were known to be by water, not by drought.
Ironically, it was too little water rather than too much that caused this catastrophic collapse. In the aftermath of the flood, Wilderness's dike needed to be rebuilt. This time, engineers chose not to put all their faith in peat.
The solution to this type of problem is putting a blanket of clay on the peat dikes, preventing the drying process, and also giving some extra weight to the dike.
Clay is less porous than peat and exhibits a higher load-bearing capacity, ensuring stronger foundations for the new levee. Not only that, extra reinforcements were added in the center of town.
Before all the problems, the dike was only of peat. Now we have a beautiful dike with concrete and steel, and I think we have the best and the safest dike in all the Netherlands.
While it took months for the town to recover, there were no fatalities, and that's largely down to Kostel's quick thinking.
We were successful. We stopped the water at this place. Me and a lot of other people who also worked a long night.
In Montreal, a vital highway crossing collapses with tragic consequences.
There were cars falling into the abyss.
like boom, down.
A cutting-edge skyscraper threatens to rain shrapnel down onto the city 120 meters below.
Just imagine what that would have done to your head.
A legendary space mission with an engineering catastrophe more than 300,000 kilometers from home.
Houston, we've had a problem.
And in France, an historic village that's literally at breaking point.
Toute ma vie, tout est foutu.
With big builds, even the smallest mistake can be a huge disaster. From miscalculations to misunderstandings. Some with deadly consequences. These catastrophes are every engineer's worst nightmare. All structures, no matter how well built, must be regularly monitored to ensure their safety. However, some engineering oversights are only spotted after it's too late to act. Like this disaster on a downtown overpass in Canada.
This catastrophe happened in the blink of an eye.
A perfectly cut piece crashed down onto the cars below.
A concrete construction that hid a deadly flaw.
Unfortunately, this was a disaster just waiting to happen.
A stark reminder that engineers don't always get it right.
This was just one oversight after another, which ended in tragedy.
Montreal is the largest city in Canada's Quebec province. Founded by French settlers in the 1600s, today it's home to more than 4 million people and a hub for commerce and culture. As local journalist Amanda Pfeffer knows well.
Joie de vivre, that is what people come to Montreal for, and it's why people love living in Montreal.
Montreal is a cosmopolitan city with a real European flavour and has all the things you might find in Paris. Great food, fine wine, but like any big city, it also has the curse of ever-increasing traffic.
Montreal is built on an island and fast-growing, which means that the roads and construction causes gridlock on streets all over the city, wherever you may live.
In the 1960s, city planners designed a new road system to help alleviate downtown traffic. A key part of the project was a brand new overpass on Highway 19 that would be one of a kind. The side spans had raking columns with short cantilevers. This allowed the middle span, made of pre-stressed concrete, to be suspended across the road without the need for a central support. Expansion joints above each cantilever would allow the structure to flex under the influence of Montreal's drastic temperature fluctuations. The de la Concorde overpass opened to traffic in 1971 and was hailed as a great engineering success.
57,000 vehicles use the overpass every day, and building it helped ease the city's traffic problems.
Engineers built the bridge to last 70 years. But little did they know the design concealed a deadly weakness.
Vulnerable areas of the bridge were taking a daily pounding.
By the 1980s, the overpass had begun to exhibit visible signs of concrete degradation. After a series of patch-ups, an in-depth inspection was carried out in 1992, during which some damaged concrete was removed. Yet the greatest threat remained undetected. On September the 30th, 2006, drivers using Montreal's Highway 19 noticed that something wasn't quite right with the de la Concorde overpass.
Members of the public have reported seeing cracks and large gaps in the deck support. And one driver apparently even called the police to report seeing a chunk of concrete the size of a suitcase falling to the road below.
An inspector from Transport Quebec came, called in and said that an inspection needed to take place. That inspection was put forward to the Monday. An advisory went out to media organizations telling motorists to watch out for falling debris. The highway was not closed.
Despite clearing away and loading the fallen pieces of concrete into the back of their pickup, the highway official decided that the bridge presented no immediate threat or danger.
The overpass and the highway underneath remained open until the follow-up assessment could be carried out. Meanwhile, the concrete continued to show signs of rapid deterioration.
Motorists were starting to see the roadway begin to sink into the structure, and a large bump. They could feel the bump on each side.
Suddenly, disaster struck. The southbound section of the overpass collapsed.
A perfectly cut piece of the slab on top had come off and crashed down onto the cars below.
Dr. Claude Giroux was nearby and heard the collapse.
There was a big hole here. Underneath, I saw that truck, and then I saw a car underneath with the whole mass of block and the cement there.
Emergency crews were trying to see whether anybody underneath that concrete was still alive.
Tragically, the catastrophe resulted in 5 fatalities. In the wake of the disaster, the people of Montreal demanded answers. Further investigation revealed that the structure's design was inherently flawed.
The design was considered innovative at the time, but it also meant that it was nearly impossible to carry out a thorough inspection.
It was built to be very difficult to inspect, in fact. You would have to actually drill core samples into the bridge to see if there was rusting or problems with the rebar, that kind of thing.
The overpass's design prevented proper inspection of the abutments and cantilevers, the exact points that carried the full weight of the bridge. It was here that the catastrophic failure occurred.
The De La Concorde overpass effectively collapsed under its own weight in what's known as a shear failure.
A shear failure occurs when a load exceeds the material's shear strength, causing a sliding failure parallel to that load. An inspection showed that the shear strength of the overpass had been compromised at critical points.
Although it happened instantaneously, this catastrophic and tragic failure was a result of years of deterioration.
It seems the engineers who designed the structure underestimated how quickly the points below the expansion joints would degrade.
This error in calculations resulted in a huge amount of stress on the corners of the cantilevers. It essentially created a weak zone that just couldn't handle such a large load.
It was discovered that the rapid degradation at these weak points was caused by the effect of Montreal's climate on the concrete.
It should be no surprise that winters in Montreal can be very harsh, with plenty of snow and ice. Authorities use a lot of salt on the roads to make them safer, but incredibly, engineers hadn't taken that into account when choosing the concrete.
For decades, salty water had been entering the structure around the expansion joints above the cantilevers, into inclusions in the concrete. Seasonal freezing and thawing caused the concrete to crumble at an unpredicted rate. This all culminated in sudden diagonal shear fractures across the cantilevers on both abutments. The result? A total failure of the overpass. Not only that, experts deemed the quality of the concrete used to be substandard, as it lacked sufficient rebar reinforcement at the cantilever abutments. Professor of Structural Engineering Lofty Gisani explains.
It's a shear crack which developed here. It's a diagonal crack, and this is a typical crack. We observe it in beams without steel reinforcement in shear. So this crack has been observed only 30 minutes before the failure of the bridge. And this crack, because of the absence also of the shear strengthening, it can widen quickly and make a brittle failure in shear.
The overpass on Boulevard de la Concorde was built in 1970 and was expected to have a lifespan of around 70 years. But by using poor quality concrete, tests showed that engineers had effectively halved its lifespan.
Now engineers were tasked with fixing this gaping hole. The government inquiry into the de la Concorde catastrophe of 2006 concluded a combination of design choice, substandard materials, and environmental conditions had all contributed to the tragedy. Not only that, but the inspection and restoration in 1992 had significantly compromised the structure.
Not only did the 1992 inspection not fix the problem, but by removing much more concrete than they had planned, it actually made things a whole lot worse.
The current practices for structures that are exposed to freeze-thaw calls for the installation of a waterproof membrane to prevent the infiltration of salt-laden water, which can damage the concrete. But this was never installed, even during the extensive bridge repairs in 1992.
Engineers have argued that the works carried out in '92 should have also included reinforcement of the cantilevers and abutments of the overpass.
According to experts, the sheer reinforcements would have strengthened those critical areas of weakness and controlled the internal cracking. And then just maybe this collapse could have been prevented.
The de la Concorde tragedy prompted an inspection of similar structures in the area.
As well as having exactly the same flaws as de la Concorde, the Deepwater overpass was in fact built in the same construction project. It was close to traffic less than 3 hours after the collapse and subsequently demolished.
It wasn't just the Deepwater overpass that came under the microscope. Multiple bridges across Canada were closely inspected.
I believe there were like 300 inspections that took place after this bridge collapsed. Half of the bridges needed further inspection, and a quarter of them actually needed major repair, as it turned out.
Hundreds of millions of dollars have been invested in the infrastructure, and over 100 overpasses have been closed to all trucks in excess of 20 tons to make sure something like this never happens again.
Today, Canada's Highway Authority remains committed to the safety of all drivers. But the legacy of the de la Concorde catastrophe endures.
There was a real rethinking of what we take for granted, which is that our bridges are safe, that our infrastructure is safe, and that when we drive underneath them, we won't be crushed by them.
Every time I go on a bridge now, I know that bridge can fall. Or if I go underneath a bridge, I just go right through, because that can happen to anybody.
When it comes to groundbreaking engineering, everything from the foundations up has to be built to last. Getting the basics wrong can lead to disaster. Like this statement skyscraper in England, where 14 million tiles were in danger of raining down from nearly 120 meters.
Just imagine what that would have done to your head.
A record-breaking tower that was a huge headache for engineers.
This was meant to be a statement building, but instead, it nearly turned into a public health hazard.
And a show-stopping construction that could become a downtown disaster. Manchester, in northwest England, is considered one of the UK's cultural and industrial powerhouses.
It was right at the heart of the Industrial Revolution, and in the 1950s was a pioneer in the technological revolution. It's a forward-looking city.
In the 1960s, this pioneering city was about to become home to the UK's tallest building, the CIS Tower. Architectural expert Dr. Richard Brooke explains.
The CIS Tower was built in 1962 to house a cooperative insurance society. I wanted a symbol for power and progress and something that really captured their modern and forward-thinking outlook.
For inspiration, architects looked across the pond, where big, bold buildings were in plentiful supply.
The architects went to the US seeking inspiration, and they found it.
It drew on American precedents from Chicago and New York. This was constructed from steel, so it's more akin to its American cousins.
While it would be nowhere near the size and scale of its American counterparts, for the UK, this building was a real high flyer.
At 25 stories high, this would be the UK's tallest building.
The key idea was to improve the office space by removing the services, so elevators, cables, pipes, all that lot, into a separate tower. So you basically have a clean office space with a service tower bolted on the side.
The building had 3 parts: a modest 5-story office block, a much taller 19-story glass-walled office tower, and rising above both would be a 25-story service core. With no windows needed on the service core, designers decided to cover the entire surface with a mosaic made up of 14 million 1¼ centimetre square tiles.
Every statement building needs something to shout about, and 14 million tiny tiles all the way up the service core is one heck of a statement.
The CIS tower was absolutely unprecedented at the time, and the architects were absolutely enthralled by its design quality. But they really wanted this to be a symbol of progress and success.
Opened in 1962, the CIS tower stood tall in this industrial heartland. But shortly after opening, the gloss was literally coming off this brilliant design.
The tiles were meant to shimmer and sparkle. An unexpected turn of events started to take the shine off the building.
Within just 6 months, some of the 14 million tiles were beginning to plummet down to the sidewalk below. And at nearly 120 meters high, toppling tiles in the middle of downtown Manchester, no matter how tiny, had the potential to do some serious damage. As concrete expert George Ballard explains.
You've seen what happens to your windscreen, your windshield, when a stone flies up and you're doing 30 miles an hour, 50 kilometers an hour, it chips the hardened glass. Just imagine what that would have done to your head. These are vicious and dangerous as they fall.
One of those tiles falling from 25 stories could reach speeds of over 100 miles an hour. You would not want to be standing underneath that.
Luckily, there were no recorded injuries, but this groundbreaking facade was in serious danger of losing face. And as tiles on Manchester's CIS Tower continued to fall from the sky, people wanted to know how this groundbreaking building had become a runaway disaster. It turned out this titanic tower was shrinking. George Ballard explains.
With the CIS tower, if we start just with the concrete tower itself, when it's constructed, the concrete itself shrinks as it cures, and it shrinks by about 1 millimeter per meter. And that is over the entire length.
This might not sound like much, but with a 120-meter tall building, as it dries, the concrete can shrink by nearly 18 centimeters.
That happens over a period of 9 months to a year. But the tiles, however, are fixed very early on in its life, and so they're put on and they're put into compression by the shrinking tower.
The tiles were fixed into place very early on in the construction phase, but no one had taken into account concrete shrinkage.
As the concrete dries, it loses excess water, which results in a small reduction in volume known as shrinkage. If something, such as tiles, prevents that natural shrinking process from occurring, cracks can form, damaging the adhesive holding the tiles in place. But that wasn't the only problem.
If I take, for example, the tiles here, they're similar to the ones on the CIS tower. On a cold night, the whole building cools down and it shrinks somewhat. Then the sun comes out, it shines on these tiles, they absorb heat, and they expand. They're trying to push against the building. They try and push very hard, and Eventually, if there's any loose tiles, a damaged tile, any of these may cause it to pop off.
Shrinkage is a well-known problem in concrete buildings. It seems an obvious solution had been overlooked.
Normally, in buildings, this is well understood and it's catered for, and every now and then, a movement joint is put in to allow the building to expand and contract. And that would have released a lot of the stress that developed in these tiles.
An expansion or movement joint is designed to hold a structure in place, while safely allowing some expansion and contraction of the building due to shrinkage and changes in temperature. Unfortunately, a lack of expansion joints built into the CIS Service Corps' design significantly contributed to the failure of the multi-million-piece Mosaic.
Without expansion joints, the tiles had no room to adapt to the ever-changing weather. They couldn't contract or expand, and so they literally popped off the wall.
By April 2003, the tiles were falling off faster than they could be fixed. And after more than 40 years of a failing facade, it was time for a change. The solution was as radical as the original design. The entire 25-story service core would be resurfaced in the largest solar power project ever undertaken in the UK.
The fix was the largest use of solar panels on a building in Britain. More than 7,000 of them cover the entire service core, absorbing the free Manchester sunlight to generate electricity.
Solar engineer Dr. Daniel Davies explains.
And essentially, this is a sheet of glass. The solar cells are encapsulated behind with a polymer skin and an aluminium frame. So the materials that are exposed to the elements are glass and aluminium, which are widely used in construction. So we connect 4 or 5 panels together. On the co-op tower, I think it was 7, built into a cassette, we called it. And that cassette is lifted onto an aluminium structure fixed onto the outside of the building.
On the 3rd of November 2005, the then Prime Minister of the UK, Tony Blair, switched on the UK's largest solar power tower project.
The tower now generates roughly enough power to make 10 million cups of coffee a year.
And the old Mosaic tiles are now safely out of sight and out of engineers' minds.
The remaining mosaic was kept in place behind the new solar panel cladding with a wire mesh, but in all likelihood, it will never see the light of day again.
Despite its initial problems, the CIS Tower remains one of the tallest buildings in Manchester and still one of its most distinguished. And engineers might have been green with their first Mosaic design, but their solution turned out to be even greener.
Engineers turned a massive building blunder into an engineering triumph, and in the process did their bit for the planet.
While the initial failure may have been costly, the new solution is making money while the Manchester sun shines.
Twice, this building was ahead of its time and finally turned disaster into triumph with true engineering innovation.
And this time, the building and the city is all the better for it. When engineers push the boundaries above and beyond, the results can be groundbreaking. But when the stakes are high, even the tiniest oversight can end in catastrophe. Like this infamous disaster that was out of this world.
Apollo 13 is famous for the explosion halfway to the moon. But what few know is that it was primed to blow long before liftoff.
This oversight came to light at a critical moment.
On Apollo 13, we did things that we shouldn't have done.
Any explosion is scary, but when you're halfway to the moon, there would be no one to come to the rescue.
The shocking engineering truth behind this epic fail.
Houston, we've had a problem. We made a bomb. We thought we lost him.
Florida, the Sunshine State, with its beaches famed for swimming, surfing and fishing. But there is one beach which is renowned for something very different: NASA's rocket launches. Emre Kelly is a space reporter.
There are typically thousands of people here during a launch. You can look all the way down to Cocoa Beach, probably even see Satellite Beach down there, which is where Buzz Aldrin lives. And you can hang out on the beach all day with your family and friends, and then watch a launch too. These days, a landing.
Yet the space missions wouldn't be possible without the tireless efforts of those thousands of kilometers west in Space City. Tracy Lamb is COO at Space Center Houston.
People love to hear about heroes, and we had so many heroes during that time.
In the 1960s, NASA captured the world's imagination with the Apollo program, an epic endeavor to reach our closest neighbor, the Moon.
When I think about truly cutting-edge engineering, NASA's quest to reach the Moon is right up there with the best of them.
The people that worked during that era, they had never done something like this before. So they had no recipe book, they had no go-by how to do this or do that. They created all of that during that time frame.
At the time, NASA wasn't the only group of engineers with their sights set on the Moon. The Soviet Union had their eyes on the same prize. Alex Stuckey is an investigative reporter.
During the Cold War, the United States got so much funding to go to the Moon because it really was like, we have to win this war effort. We have to get to the Moon first.
The competition was fierce.
In 1957, the Soviet Union launched the Sputnik satellite, something we had never done, and that really sort of kicked off this race to the Moon.
Cy Liebergott worked for NASA during the race to the Moon.
We never looked at it as a job, and we were young and we were fearless, and we were ready to go to the Moon because we just wanted to beat the Russians. And the reason that we were willing to do all that stuff for the first time ever was because nobody ever told us we couldn't land humans on another planet.
NASA's efforts were famously rewarded in 1969 when they succeeded in putting the first man on the Moon.
It's one small step for man, one giant leap for mankind.
The ambitions of the Apollo program didn't end there, with engineering prowess knowing no bounds.
When these crews went to space on Apollo 13, any Apollo mission, they were doing a lot of their work on pen and paper with some really basic computer systems, guidance navigation systems. Today, the iPhone in your pocket is thousands of times more powerful and capable than what they had. And they were manually piloting these spacecraft to the surface of the Moon.
In 1970, NASA planned another lunar mission. Apollo 13 was meant to be the third landing on the Moon. But by now, events back on Earth had stolen the spotlight.
Budgets weren't tight, but war, Vietnam, there was political strife involved, and some people didn't necessarily think the Apollo program was worth it.
After a successful launch on April the 11th, the crew's journey to the Moon was suddenly jeopardized when an engineering catastrophe struck more than 300,000 kilometers from Earth. Cy Liebergott ordered a cryogenic stir of the oxygen tanks, a routine operation that ensured the contents of each tank could be measured accurately.
In zero gravity, we found that the cryogenic material would stratify in layers of different densities, and we would get a fakey reading. Once a day, after the crew woke up, we'd have them stir to cryos. And there was these little 4 switches on the main display console, and they'd flip them up and run them for about a minute, and that's done. No big deal.
In zero gravity, the oxygen would separate into layers that made it hard to know exactly how much was in the tank.
I decided, being a good flight controller, that I wanted more data. I wanted to stir the cryos again, just to make sure I knew where we were.
Without warning, an oxygen tank on the spacecraft exploded.
Here, O2 tank 2 is here, and the explosion shocked this upper shelf, causing the feed valves, fuel cells 3 and 1, to shock closed. And then below here were the 2 hydrogen tanks. And the pressure that created blew the whole side of the spacecraft off.
Houston, we've had a problem. Roger, main B under.
The remarkable series of events that followed allowed the crew to safely return to Earth. But that's only half of the story.
When people talk about Apollo 13, the drama nearly always centers on what happened after the explosion. But what is less well known is that it was inevitable and had actually been set in motion years earlier.
The problem stemmed from the design of one specific part of the spacecraft.
After launch, the Apollo spacecraft had 3 main elements: the moon lander, the command module where the 3 astronauts slept and worked, and the cylindrical service module, which, as well as a rocket motor, carried most of the power and life support systems for the trip out and back.
The service module, the big part connected to the command module, essentially malfunctioned and an oxygen tank ruptured.
The service module comprised of 3 levels containing the vital life support elements for the spacecraft. 2 tanks of liquid oxygen, 2 tanks of liquid hydrogen, along with 3 power cells.
It was a replenishable battery, and it produced electricity and pure drinking water. You can't beat that.
The most essential elements for life support in space are oxygen and hydrogen. Each Apollo mission carried pressurized cylinders of both. Used in different ways, they could provide power for heating and lighting, or air for breathing.
So what had caused this essential life support unit to malfunction? The investigation into Apollo 13 revealed that the oxygen tank that exploded had previously been installed on Apollo 10 back in 1968.
The moon missions were highly experimental throughout, and the technology was constantly being improved.
When repurposing that tank, the thermostatic switches inside were compromised.
Although no one knew it, there was internal damage that paved the way for the explosion on Apollo 13.
This undetected damage turned into a major issue when NASA engineers were preparing the tank for reuse on a later mission.
In space, Apollo 13's electricals were designed to run on 28-volt power, but for testing on Earth, they used 65 volts. Nearly all the components were upgraded to operate on both voltages, but crucially, thermostatic switches in the oxygen tanks were overlooked. When the tank was being flushed, it overheated and the insulation melted on the electrical wiring. That's not good when your tank is holding pure oxygen.
This fail lay hidden, only to be revealed in a dramatic display out in space.
When Sy gave the order to stir the tanks, which was the 3rd time on the mission, the lack of insulation on the wires caused a short circuit, creating a spark. That was all it took to cause the explosion, and the rest is history.
As it turns out, the timing of the explosion proved critical to the survival of Apollo 13's crew.
If the failure couldn't have happened at a better time, it was going to happen. And if it hadn't happened when I asked for that extra stir, it might have happened when the crew woke up in the morning. It could have happened and when they powered up the lunar module, using up its valuable consumables. Could have happened when they were down on the ground doing the same thing. And they were dead. They were dead.
The tank exploding exactly when it did was incredibly lucky. Any earlier in the mission and the astronauts would have run out of power or oxygen long before they made it back to Earth. If it had happened later, after the lunar lander had separated, 2 astronauts could have been marooned on the moon with another lost in space.
After Apollo 13's harrowing return to Earth, NASA, along with engineers around the world, learned valuable lessons to make future space exploration safer.
A lot of new technologies came from Apollo.
The microchip wouldn't exist if it weren't for the Apollo program, which is sort of important. Just all kinds of, supercomputing capabilities existed because of Apollo, and that's how we got to the moon.
Although Apollo 13 failed to land on the moon, this unforgettable mission served as a critical lesson for both NASA and humankind. When an engineering oversight reveals itself, the outcome can be sudden and disastrous. However, some fails can result in a catastrophe that takes years to unfold. Like this engineering fail in France that is slowly but surely tearing a community apart.
It's a disaster that's divided a town.
Residents can only watch in despair as their homes crumble around them.
C'est leur maison parce qu'elle était trop endommagée pour pouvoir vivre dedans.
Village life would never be the same.
Toute ma vie, tout est foutu.
Lochviller, in northeast France, dates back hundreds of years. Guillaume Urquhart is a local journalist.
Ici, nous sommes dans le centre-ville de Lorvillers et comme vous pouvez le constater, il y a seulement des habitants qui sont soudés entre eux depuis plusieurs générations, qui vivent ici, qui s'entraident. Et il y a beaucoup d'agriculteurs aussi, c'est une commune rurale, donc les gens cultivent la terre pour leur bétail, mais également pour produire des céréales.
Lochviller is a tiny little town in deep rural France. Traditionally, Lochviller's residents have been farmers, but city dwellers looking for a slower pace of life started moving here in recent years.
As the town's population grew, in the early 2000s, a series of new homes were constructed.
Donc, nous sommes ici dans une rue de Lorvillers avec, vous voyez sur votre droite, des maisons anciennes qui ont pour certaines 200, 300, 400 ans. Et ici à droite, vous avez ce nouveau quartier qui a été construit il y a une dizaine d'années avec de nombreuses constructions de maisons neuves.
In 2008, one Lochviller resident invested in a green form of energy that would tap into the power right beneath their feet.
Donc l'habitant de la maison a décidé de s'équiper d'un forage géothermique pour avoir du chauffage dans sa maison. Donc il a mandaté une société spécialisée dans le creusement du sol pour percer un trou afin de capter l'énergie dans le sol.
Geothermal energy is on the rise. The appeal is clear. It's renewable, unlimited, and unlike fossil fuels, it doesn't pump out greenhouse gases.
Geothermal energy involves the drilling of a borehole deep into the earth. The naturally occurring heat underground can then be tapped and drawn to the surface, providing a free, zero-emission method for heating a home. This form of energy may seem simple and effective, but here, engineers inadvertently created an issue that would very quickly become a nightmare for the entire town. In late 2008, residents of the town of Lochviller started to notice that something wasn't quite right underfoot. Jean-Baptiste Cameraire lived here when things began to go wrong.
At the beginning, we noticed that some houses were moving at some cracks. There was something else. The soil, the ground were moving, and we were wondering why and where it was going.
Initially, the cracking in structures was difficult to spot, but as time passed, the damage spread, and before long, local residents' lives were being seriously impacted by the phenomenon.
So this is my garage. This is the place where we first noticed a crack in our house. And now we have it was very small at the beginning, and now we have something huge that goes from one side to the other. As you can imagine, it's very difficult to live in a house like that when you know that it's moving and it may one day fall. You don't want to finish the house because you know that everything is lost. It's very hard from a psychological point of view.
A movement of just a couple of inches might not sound like much, but it's enough to wreak havoc on the structural integrity of a building.
Donc le phénomène des mouvements de terrain de l'Orvillers a une double incidence sur les maisons. Les constructions neuves ont plutôt tendance à pencher, produisant de la gîte, alors que les constructions anciennes, comme on le voit ici dans le reste du village, ont tendance à se fissurer. C'est-à-dire qu'au fur et à mesure des années, des petites fissures s'agrandissent et lézardent complètement les maisons qui menacent ruine aujourd'hui. Pour remédier au phénomène, certaines personnes ont pris des préconisations pour éviter que leur maison ne s'effondre. On voit la maison derrière moi, le propriétaire a dû planter des pylônes en métal pour soutenir les fondations. Il y en a plusieurs qui ont déménagé, effectivement, qui ont quitté leur résidence, leur maison, parce qu'elle était trop endommagée pour pouvoir vivre dedans.
In desperation, the people of Lockville sought the help of experts to determine why their town was coming apart at the seams. An investigation into the damage revealed that the source of the problem lay under their feet.
The town is built on a mix of anhydrite and clay. Now, anhydrite is a material which, when it comes into contact with water, can swell up to 60% larger than its initial volume.
When engineers drilled the geothermal energy borehole in 2008, they pierced the water table around 60 meters below the ground surface.
Anywhere on Earth, if you drill down deep enough, you're going to hit something known as the water table. This is formed when water trickles down from the surface and settles at a certain level. This level will vary in height from place to place, but it is always there.
The water was released into the anhydrite underneath the town.
Anhydrite is like a baby's diaper. Add water and it will expand.
By drilling into the water table, they exposed the bone-dry anhydrite to an unlimited supply of water. So it simply started swelling up like a sponge.
François Villeret, head of the Department of Industrial Risk Prevention, explains.
Donc l'anhydrite se charge en eau, deux molécules d'eau qui viennent se greffer sur les molécules de sulfate de calcium. Et au moment de cette combinaison chimique, on a un gonflement du matériau de l'ordre de 60% de son volume initial. Et donc, l'eau qui remonte ici vient créer ce phénomène de gonflement sur les anhydrites qui se trouvent dans cet horizon-là, et les anhydrites créent une pression.
This reaction put pressure on the ground from below, causing it to swell upward and move sideways.
The process is slow but constant, and as long as water is present, the anhydrite will continue absorbing it, forcing the ground above to bulge and warp.
It's incredible to think that drilling one small hole could cause all this damage. But that's the power of Mother Nature.
And Lockville's nightmare is far from over.
The swelling of the anhydrite is relentless. If nothing is done, the cracks will continue to grow.
To save their homes, the people of Lockville are looking to engineers for help.
The engineers needed to figure out how to separate the water table from the anhydrite layer in the ground.
Finally, a plan has been devised to potentially solve the problem.
Pour éviter que l'eau ne remonte, on va creuser un deuxième forage à côté du forage à l'origine du problème. Et puis on va venir pomper dans ce forage. Et en venant pomper dans le forage, on va créer une dépression. Et donc, l'eau de la nappe ne pourra plus remonter jusqu'à la strate géologique de l'anhydrite. Et ça, c'est la solution qui est à l'étude en ce moment et qu'on pense pouvoir mettre en œuvre avec des premiers travaux en 2020.
You'd never have thought that the best solution would be a second borehole, but it's got to be worth a try. If the engineers can't stop the water rising into the anhydrite layer, then the whole town could face ruin.
Hopefully, in the near future, engineers will be able to stop this catastrophe in its tracks.